নকলে হৈছে সেইটো মই বুজি পোৱা নাই
নেটটো স্লো থাকে নেটটো স্লো হ'ব চাগে
নহয় মোৰ কম্পিউটাৰটো স্লো এইটোতো মই এটা অনেক কৰিব পৰা নাই
এইটো
হ'ব কিন্তু কি হ'ব তাতে সেইটো ভিডিঅ একচেপ্ট কৰি দিব নোৱাৰে তাতে
তাত তেতিয়া হ'ব পঢ়া বনাব লাগিব ছাৰ সেইটো শুনকচোন
সেইটোতো কৰিব নোৱাৰি এতিয়া
নোৱাৰিলেও তাত হেৰি কৰি দিব পাৰিম
কি
একচেপ্ট ৰিজেক্ট কৰি এইবিলাক ছাৰ এইটো হ'ল
সেইটো খুলিছিলোঁ
হ'ব ছাৰ এটা খুলিলে ধৰিম পঢ়া কৰিব লাগিব ছাৰ
সহজটো কেনেকৈ কৰিব পাৰি
আকৌ কেনেকৈ কৰিছিলোঁ
জইন হৈ আছে
ছাৰ সেই হেৰিটোকে ছাৰ যিটো আমাক ইমেইলত লিংক দিছিলে সেইটোকে খোলকচোন ছাৰ এইটো একাউণ্টটো হেৰি আৰু
কিন্তু সিটো মই ইয়াত কেনেকৈ সেইটো অলৰেডি তাত কৰি থোৱা আছিল
কৰি চাওকচোন ছাৰ
আৰম্ভ কৰি দে
আৰম্ভ কৰি ৰ এইটো বস্তুটো প্ৰব্লেম আছে ন
কোনটো
কেনেকুৱা স্ল' লাগিছে নে
মোৰটো বহি কৰ মোৰটো অন হৈ আছে
নহয় নহয় সেইটো মেইন কম্পিউটাৰটো তাৰমানে যিটো আছে সেইটো হেৰি আছে চাহিনে সেইটো যিটো বহিব চাহিনে বহিব পাৰে ন
বহিব পাৰে বহি আৰম্ভ কৰি দিয়ক
মানে
নহ'লে মোৰটো বহি চাওক মোৰ লেপটপটো অন আছে একেটাই কথা নহ'ব জানো আৰু সেইটো পাৰে যদি সেইটো
দুটা মানুহে পাৰিব নাই
জইন
এইটো ইয়াত
নাই ছাৰ খুলি দিব
এইটো মিউট কৰি ন এইটো মিউট কৰি ন এইটোতো মিউট হৈ আছে এইটো মই
এতিয়া মই ছাৰ ইয়াৰ পৰা মই হেৰিটা পঠাম ছাৰলৈ যাই চাওঁ
তাত নহ'লে মোৰ এইটো হেৰি কৰি থোৱা তাত মোৰ এইটো এদি দি কৰি থোৱা এইটো ইণ্টাৰনেটটো খুলিবলৈ চোৱাচোন
আহিব ইয়ালৈ
internet নাই না মই নটবাই কৰিব লাগিব
সেই এইটো কোৱা
তোমাৰ মই ক'ব নোৱাৰিম ন
মই কৈছা
এইটো অংক মই তাতে কৈ দিমগৈ আৰু পিছতো অনেক কৰিব
সেইটো অন কৰা
This will be held both online as well as offline. Poster presentation session outside the seminar hall of the department. And first of all, I would like to thank all the speakers for those who participate in the conference. Next, I must thank the Registrar Dr. Briandas and other administrative officers. Along with this, I welcome all of you, all colleagues and students, those who are online as well as offline, to this conference. I hope this one-day conference will be successful with 7 invited lectures as well as oral and poster presentation. With this, I would like to thank you and welcome once again to this conference. Thank you so much.
Thank you, sir. Now I would like to call upon Professor Bipul Sharma, who is the Faculty Coordinator of InSCIgnis, to let us know more about the Science Festival.
Okay, so thank you, Sahin. A very good morning to all. So let me start with the word InSCIgnis. The name of the event, InSCIgnis, was first adopted from the Latin word InSCIgnis, okay, where the letter C is absent. So InSCIgnis means extraordinary growth. It's a rapid growth. So there is a tree, and it has been observed that that has somehow got extraordinary growth, but that has come from the Latin. And the C, the letter C was added to the word InSCIgnis to take the abbreviation of SCI, that means science. So the overall meaning of the InSCIgnis we have taken as extraordinary growth of science. And this year, Tezpur University is celebrating the 9th edition of InSCIgnis, one of the biggest science fest of Northeast India to celebrate science in its true essence. And this is on the occasion of National Science Day. And this time, it is in a 3-day venture. So we have started with half day at the beginning, then it was a 1-day program. And last year it was a 2.5-day program, and this year it has it is celebrated for the 3 days consecutively, and today is the last day of InSCIgnis. The fest has been providing opportunities to everyone to learn and live the moment, as InSCIgnis 22, which is hosting a plethora of events involving competitions that aim at bringing out the fun side of science, along with fascinating workshops and discussions on contemporary topics. InSCIgnis 22 was inaugurated on 27 February, just 2 days back, in presence of several beautiful minds of the nation, Padma Shri Biru Balarabha, Padma Shri Dr. Arup Kumar Datta, Bhatnagar Awardee Dr. Vinay Kumar Soikia, along with few other notable guests, and our own Vice Chancellor, Registrar, the Dean, School of Sciences, and other deans, the heads of the departments. So it was a beautiful moment on 27th morning. The fest is showcasing several brainstorming quizzes, the Northeast regional level science exhibition, astronomy events, departmental events, and many more fascinating events to ravish the minds of nearly 1,200 people in this ardent venture. So few online events are pragmatic to grasp participation from over 10 foreign countries. So this is very good achievement for us. I think we have received around 16 foreign countries participation in 2020. And InSCIgnis for the first time is hosting 5 national conferences organized by the respective 5 departments under the School of Science today, and that is happening today in all science departments. And these 5 conferences are now witnessing over 800 participation. So, and we are here now with a theme on sustainability, medicine and clean energy for the Department of Chemical Sciences in Tezpur University. With these few words, and as the coordinator of InSCIgnis 22, I am pleased to welcome Professor Sadin Kumar Mandal, FRSC and Bhatnagar Awardee, Professor Rahul Banerjee, FRSC and Bhatnagar Awardee, Professor Parthasarathy Das, FRSC, Professor Utpal Gautam, Dr. Napaam Sabapandit, Dr. Bobita Baruoti, Mr. Arvinda Agarwala, esteemed speakers, oral and poster presentations from the participants, and all presents in both online and offline mode of this national conference on the topic sustainability, medicine and clean energy. So thank you for accepting our invitations, and I look forward for a lively interactive sessions the rest of the day. Thank you. Thank you very much. Yeah, I think we can move on to the next session.
Thank you, sir. With this, we begin today's seminar. Our first guest speaker is Professor Swadhin Kumar Mandal. Professor Swadhin Kumar Mandal completed his PhD from Indian Institute of Science, Bangalore. Then he went for his postdoctoral fellowship.
ইয়াতো পাইছা দুটা আছে নাই গুগল
Then he went for his postdoctoral fellowship to University of California, USA, and then University of Göttingen, Germany. He has been honored with various dignitary awards and recognitions such as Shanti Swarup Bhatnagar Prize 2018, Friedrich Wilhelm Bessel Research Award 2020, etc. Presently, he is a professor in the Department of Chemical Sciences, ISR, Kolkata. And I will now hand over the screen to Swadhin Kumar Mandal.
Good morning. Am I audible? Yes, good morning. Okay, good. So, first of all, my congratulations to the department for celebrating the 25th anniversary of the department. My congratulations and best wishes to the department. So, I wish that we start organizing more and more seminars on this topic, and as well as, we should now probably time that we should come out from the online mode. So, I think that makes a lot of sense. I don't know, this is early morning for Tezpur University. Students are there around. So,
Yes, it is normal good morning. It is normal good morning. Yeah. I think for
always
English.
try to talk, without seeing the I'm talking to.
Yeah.
It's always a challenge.
Yeah, I think our Professor Mandal, our students are, I think, sitting in the seminar hall.
Okay, good.
Yes. So all are here, I think.
That is, that's my reward.
Yes.
All right.
Okay, but the good to have you, sir, here. Yeah, we are privileged.
Thank you. Let me share my slides.
Sure.
It's some time.
Webcam মই আনিব দিছো মোৰ
আপোনাৰ লেপটপ লগাই থোৱা আছে ক'ত আছে সেইটো ভাল নেকি দি দিয়ক
Is visible now?
Yes, it is visible.
Yeah. First of all, let me thank the organizer for inviting and giving me this opportunity to present some of the work, which I believe that it's of course a process towards sustainability. I'll try to convince you that why this is a process towards sustainability in course. So today I have titled this presentation from CO2 acquisition to catalytic reduction of metal-free approach. Let me begin by telling that I don't claim that we are near to the industrial process or something, but we can obviously claim that we are trying to build up a concept where we can do certain reactions without using metals. More the time it passes, we are more and more understanding the use of certain metals could be harmful to our environment. So right now, this is a very emerging topic that how do you mimic transition metals without using metals. So we are working on the lab scale processes where we try to understand that how CO2 can be activated, which is very important for any kind of catalytic transformation. So this is rather more academic than that of application oriented. Of course, we do believe that we can proceed step by step towards real life application. So I would like to draw attention to the students especially. The global energy balance. This is the slide I built up from the site of International Energy Agency Paris, who maintains a very up-to-date site. The global requirement of energy, if you look at it, where from in terms, you can recognize that a major chunk of energy comes from oil, coal and natural gas. I mean, almost these three together, it makes more than 80% of total energy what we use every day, right? And you understand that for getting energy out of oil, coal or natural gas, whenever you get energy, you get CO2 as byproduct, right? So it's a gift for getting energy. So no wonder when we proceed towards more and more civilized time era, so we will be requiring more and more energy, and as per today's requirement, so we will be emitting more and more carbon dioxide, and that is evident from this data, which talks about last 20 years CO2 emission in gigaton scale, and again this data is available in IEA Paris. Right? You can see that there is a steady increase of total amount of CO2 every year, and this will be increasing like this, right? Now, what scientists are trying to do is that they are trying to tackle this problem in a variety of ways. Out of that, I will mention these two major pathways. One is that if you can utilize, you can capture the CO2 and you can store. So generally storage is planned like under the sea level, below the seabed. And of course there is a question now coming up that storage needs extra effort, energy and cost, because you have to build a pipeline, and also such a huge storage raises the question that how it affects the ecosystem of many aquatic environment. If you start storing so much of CO2 under the seabed, because it will slowly, it might be hydrolyzed, and pH of the seawater might change, and that will affect greatly the lively animals. And the other concept is that can we utilize CO2 after capturing towards various value-added chemicals? So I will be talking about this utilization, that's CCU, carbon capture and utilization. So you can capture CO2 and then you can create some of the valued chemicals. So you are basically, I'm talking about greenhouse gas to valued chemicals. A gas which is not wanted by the environment and to convert to chemicals which is extremely necessary. Let's say fine chemicals, polymers. So I just got this data, I mean, very recently published a very nice ACS practice journal. I got this data from this source. You can see that major chemicals that are currently synthesized for carbon dioxide industrially today. You can create a lot of fine chemicals out of carbon dioxide. So, for example, salicylic acid, yearly 90,000 tons can be prepared from carbon dioxide. Urea, 175 million tons, which is very essential chemicals. And you know that methanol is considered as fuel. 2 million tons can be prepared from CO2. Cyclic carbonates, 40,000 tons. Polycarbonates, polyethyl carbonates. So, there are several chemicals can be produced from CO2. Of course, this number looks very high. I'm expressing in tons, but nevertheless, I must tell you that this number is actually negligible in terms of the amount we are emitting CO2. You know, I mean, so if you look at the current status, it's just about 8% of CO2 is chemically converted to what we are emitting. And there are a lot of challenges that one has to address to fully address this problem of CO2 to value-added chemicals if we want to increase the amount of CO2 to value-added chemicals. One thing, of course, you have to consider that thermodynamically carbon dioxide is a very stable molecule with linear geometry and zero dipole moment. And it always requires metal-based catalyst most of the time. I would not say always because there are some metal-free catalysts coming up. That's what today I'll be talking about. So it primarily requires metal-based catalyst to activate CO2. That very often requires harsh condition, means high temperature, high pressure of CO2 you have to use. And then these metal catalysts are very often, they're toxic and expensive. For example, palladium, ruthenium, rhodium, if you want to use, they're extremely rare, so they're expensive and they're also toxic to us. And this process, as you can understand, that is an energy-intensive process. So you require special condition to convert. So what our proposal is that can we go metal-free? Whole process. Can we do carbon dioxide to value-added chemicals? Can we discover new chemical reaction not using metal at all? So that's something we are working on. And if you ask me that why metal-free, I would remind you that the chemical periodic table that was published by the European Chemical Society in the year of 2018, which is a color-coded periodic table, you can see that this talks about 90 natural elements that make everything. Whatever is built up in the world, this is made up with these 90 elements. And if you look at this color, you can understand that, this green color signifies that these elements are plentiful. Carbon, nitrogen, oxygen, chlorine, aluminium, silicon. Now you might ask you a question that the smartphone, what you are using, what are the elements you are using? If you look at this, this is also showing. The smartphone used, this is the symbol of smartphone, what you are using. You can see that the yellow, orange and red, they talk about limited availability, yellow colored elements in this periodic table. And orange signifies that rising threat from increased use, and red is serious threat. So you can realize that there are several elements you are using in your smartphone So I think everybody changes their smartphone within every 5 years. So every time you are throwing a smartphone, you are actually destroying some amount of red or orange colored elements. Those will not be recycled. So we need to be careful in what we are using today to make whole process, whole world sustainable. For example, helium. Helium is a red colored element. Now if you are using helium too much today, there might be coming next, after some time, we might end up with a situation that where we don't have helium, so that a patient who needs immediate MRI might not get helium and the imaging cannot be done. I mean, that's a very odd situation, you can understand. So this periodic table by Chemical Society and European Chemical Society tries to, sensitize the chemist that one should require to use or utilize very carefully, and encourages to use the elements which are not red, orange or yellow color. It's green colored elements. So that is primarily one of the motivation. What we wanted to do, we wanted to build up our catalyst only with carbon, nitrogen and oxygen and maybe hydrogen. Okay. So these are the material, these are the elements we use in designing our catalyst. So all are green elements. So now if you want to do that so-called metal-free process, we need to learn how originally metal-based process or how carbon dioxide is fixed and it can be activated. So you can learn from nature. A lot of things you can learn from nature. One is that in nature there are a lot of metal carbonates which exist. Metal, we need to know how metal actually interacts with carbon dioxide. For example, in nature we have magnesite, dolomite, calcite. These are all metal carbonates. So metal interacts with carbon dioxide, it gets hydrolyzed, then it deposits and they are rock stable. It's a natural process. So there are a variety of ways we need to learn how metal interacts with carbon dioxide if you really want to mimic carbon dioxide activation and avoid metals. First you have to learn that. And how CO2 is captured during photosynthetic process is also something one has to pay attention. So these are two things. If you look at it more carefully and more closely, then you can understand that metal can interact with a variety of ways with carbon dioxide. For example, metal can interact with the acceptor orbital on the carbon dioxide, CO2. If you look at the molecular orbital diagram, you will realize carbon is housing mostly LUMO. So a metal filled orbital can interact with carbon empty orbital, or oxygen filled orbital, HOMO, can interact with the empty metal orbital. So both are eta 1 type of bonding, or both can interact in a synergistic manner, that is donor and acceptance can be possible. Oxygen can donate electron and excess electron density can be donated back to carbon empty orbital, just like carbon monoxide interacts with the metal, or it can also bind with ether to fashion. Okay, so this is all these ways metal can interact in a variety of ways with carbon dioxide, right? So now, if you look at the nature, how it binds, so then you can see that Rubisco is the enzyme who is responsible for carbon dioxide fixation. Where if you look closely, you can understand that lysine-bound amine, you don't need any metal actually. That is taught by nature. That amine interacts with carbon dioxide to make this bonding. NH2 acts, the lone pair NH2 acts the nucleophile to bind with carbon dioxide, and then magnesium comes in the photosynthetic process and does all other next course of reactions or conversion. So this also shows that you don't need a metal, but just the amine lone pair is good enough to fix the carbon dioxide that nature tells. It's nucleophilic activation. So that is something very fascinating to design your metal-free catalyst. So I'll be talking about nucleophilic activation of carbon dioxide. Avoiding metal is very much possible. For example, carbenes are great nucleophiles which are low valent carbon centered. That also can, instead of amines that can bind with several carbon dioxide and carbon dioxide atoms are known with several carbenes and also several bases, nitrogen bases, and here is the carbenes also it can bind. Now regarding carbene, which is the topic of this talk, actually how we use carbene for binding carbon dioxide activation and then further reduction. Let me a little bit talk about carbene. Carbenes are very reactive species, low valent carbon species, where this carbene center can act as a donor center, which can bind with the metal, and when it binds with the metal, it can generate great catalyst like Grab's catalyst. For example, Grab's 2 utilizes carbene, N-nitrocyclic carbene, which is largely responsible for the Nobel Prize by Robert Grubbs. And also Grab 3 used this kind of carbenes, which is called abnormal carbene, where the carbene center is not between the two nitrogen, but between one nitrogen and one carbon. This carbene center is created, and that's called abnormal carbene, which we call as a normal carbene when carbene center is created between two nitrogen. And this is called abnormal when a carbene center is created between one nitrogen and carbene. Now, this is the first abnormal carbene which was created by E. Bertrand in 2009 in a science paper. This is the first isolation of abnormal carbene, and before that, this type of carbene was not known. And in fact, we realized after this, we extensively use this carbene for various catalysis, and from main group chemistry, from transition metal chemistry, and also lately we got interested in molecular activation of CO2, N2O like gases. And in fact, 1 year back, we wrote a review with E. Bertrand on Chemical Society Review, where we captured all the applications which we developed, and Bertrand was the person who synthesized this molecule. So this whole chemistry is captured in this review. You can always go and see this review of what are the chemistry that we developed. Now, why this abnormal carbene could be very interesting for CO2 capture, let me explain. So if you look at the paper and theoretical calculation by E. Bertrand in 2009, which talks about that if you look at the HOMO of a NAC, which is abnormal NAC, and take a normal NAC, and compare the HOMO, you can understand that HOMO is more highly energetic than that of a normal NAC, which was used in Grab's catalyst, normal NAC, by the way. Now, this abnormal NAC, HOMO being highly energetic, we anticipated that this could be utilized for CO2 capture because this will be very reactive. And in fact, it is indeed. When you isolate this carbene, you cannot even store under nitrogen atmosphere. You have to store inside a glove box at minus 20 degrees centigrade. If you keep it inside the glove box at room temperature, it even decomposes within 7 days, which is kind of boon because it's a very reactive species. It can very quickly, we anticipated that can capture carbon dioxide and further conversion could be possible. So in 2016, what we did is that we treated this particular carbene, isolated carbene, at room temperature with CO2, and then it shows that it forms immediately adapt of CO2, which it can, of course, isolate, characterize carbon 13 and all these things. And this adapt we take and treat with a boron hydride, then it gives boron methoxide, and boron methoxide, and these are all done at room temperature with atmospheric pressure of carbon dioxide, and then boron methoxide, the moment you can prepare, then you can do water hydrolysis to get methanol. So you can convert carbon dioxide to methanol, and the time we reported in 2016, so this was the best catalyst, I would say, best catalyst for in the homogeneous condition. It gave 6,000 PON. So the mechanistic pathway, we could look at this, I'm not going to discuss too much in details, but how it goes is that CO2 interacts with the CO2 carbene, and then there is a boron hydride forms an adduct with CO2 boron, and then CO2 gets inserted to give a boron diformate type of product, and then further this boron diformate was crystallized, crystallographically characterized, and also Professor Anand did a calculation to understand full mechanistic cycle before we propose and come up with this proposal of this catalytic pathway. This is the X-ray structure of this intermediate, which shows that boron diformate is the intermediate which goes through. And then boron diformate further reacts with boron, gives you boron formate and creates the NaC, and which is now catalyst is regenerated, then takes CO2, and then boron formate can be converted to step-by-step boron methoxide. Well, so what we did is that boron into carbon dioxide we took at room temperature, atmospheric pressure, we could convert carbon dioxide to methanol, all completely metal-free. Now, slowly we moved on and started questioning that whether CO2 from air conversion and capture is possible or not. In fact, this is not something we thought first actually. Of course, there is already a plant set up in Iceland which can convert huge amount of course they use metal-based catalyst, 5 million liters of methanol per year they can produce from CO2 produced in the flue gas in an adjacent geothermal power plant. Okay, so it will be very interesting if you can capture carbon dioxide from air, because you know that carbon dioxide concentration in air is still low, about 400 ppm or below 400, around that. So what we noticed that one of the boron carbene adduct which we prepared while I was studying, it was kind of a by chance observation, serendipitous observation, when we treated boron carbon adduct and then somehow it got exposed, this boron carbon adduct with the air, then we started seeing sharp color change from yellow to green, and then slowly we could actually grow a crystal, and this crystal showed the presence of carbonate which is captured by the carbon dioxide, captured from air, carbon dioxide captured product. So that shows that then once we saw this is happening by exposure to air, then we actually prepared this complex and intentionally exposed with the air, and then we have grown the crystal, and this crystal structure shows that CO2 is incorporated in the form of carbonate. That shows that carbon dioxide can be fixed from air by this metal-free adduct, carbene boron adduct, to give you this carbonate adduct. Now this carbonate adduct, of course, you treat with boron, you can get boron methoxide, which is nothing but methanol, and also you can convert to HCOONA by treatment with sodium hydroxide, which is nothing but formic acid. So this kind of shows that you can capture carbon dioxide from air, and then you can convert to methanol as well as formic acid. And however, this reaction we could not do it, in catalytic fashion. That would have been great if we could have done carbon dioxide to methanol or formic acid catalytically. But we could not do it because our catalyst decomposes on exposure to air. Now, what we are trying to, I guess I have 5 minutes time about, right? Yes, please. Okay. So, what recently we are working on the CO2 we are developing as a reagent for various organic synthesis or metal-free. What this reaction talks about that CO2 can be used as a formulating reagent of amines, and that has used traditionally ruthenium, rhodium based, and later on there are some metal-free catalyst was also developed at the same time about 2012 by Kanta et al. From France. They used that CO2 can be used for methylating agent. But what was not known in literature before our report, that although amine can be formulated, but amide was not been able to formulate. So we use CO2 as a formulating reagent for amides by using this highly reactive carbene catalyst. And in
was not at all known catalytically before our report, and we have shown that this particular process can create certain anti-fungicide molecules by doing formulation of amides catalytically all metal. That we reported in 2018. And very recently, what we did also, instead of carbene, we used phosphonidine. Phosphonidine is actually low-valent congeners of carbene, which is a phosphorus 1 compound. Phosphonidine is having a 2 lone pair, unlike phosphorus 3, which is having a lone pair of electrons. There is 2 lone pair of electrons. We use this phosphonidine as a reagent, as a catalyst for doing the amide formulation using phosphonidine as catalyst. This is the first report where you used phosphonidine, that is a low-valent phosphorus compound, which is very reactive species catalyst, to do the formulation of amides. This we reported last year, and we also worked out the mechanisms, which I am not just taking you through at this moment. So, and then also we very recently developed how we can use carbon dioxide for metal-free methylation process. One is formulation. Another very important reaction is methylation in organic synthesis, where we use something called mesoionite N-heterocyclic olefin. This is olefin, this is the carbene, this is the abnormal carbene, and this is the N-heterocyclic olefins. Now what we argued is that if you create an abnormal or mesoionic N-heterocyclic olefin, this negative charge stays with this carbon, and this carbon center can act as a nucleophile to do your carbon dioxide activation. And this has got very high nucleophilicity as compared to carbene and abnormal carbene. So this DEP parameter, Tolman electronic parameter, tells that this is a very highly nucleophile. Then what we did is that we used this for methylating agent. We could do the N-methylation of amines, and not only that, we could do monomethylation, dimethylation, and trimethylation. And this is the first time we are using methylation. Is a 6 electron reduction. This is 12 electron reduction. This is 18 electron reduction process we could do completely metal-free, that we just reported last year. I'm not taking you through mechanism because I am going short on time. So, and then what we are trying to do now, integrate two very difficult process, completely metal-free. We have been successfully done that. We have integrated hydrogen and carbon dioxide together in the same reaction sequence. One completely metal-free process we developed, but we could do a borinium ion actually. This is something I did not discuss today. So borinium ion is a FLP, prostated Lewis pair, that can activate hydrogen to create NH compound, and then we use our metal-free catalyst to do the N-methylation process, by which we could integrate hydrogen activation and carbon dioxide activation to create a number of drug molecules like anti-tumor activity, anti-malarial drug, or in formulation. So it is a very tough process if you look at it, if you want to do both hydrogen and carbon dioxide activation all metals. So that is what we have recently been successful. This is unpublished result, and we have done it in several reactions. We could use this process to prepare gallipine, which is anti-tumor drug, anti-malarial drug, angustarine. All this we prepared medically by integrating the carbon dioxide and H2 catalytic process. Well, this is something we wrote this concept is as an emerging concept. We wrote a perspective article recently on this topic, how we can do CO2 activation and catalytic reduction all metal-free. So right now we are developing a lot of other new reactions which is not reported. For example, this is a reaction we are right now developing where amide can be coupled through CH2 as this methylene group comes from CO2, and then this reaction is not known. We are developing for the first time this kind of chemistry with our metal-free catalyst. And also, this is also not known with carbon dioxide. We are doing thiol formulation. So we can take thiol and do formulate thiol in CO2 with our metal-free catalyst. So we have been working on this. So with this, I would like to conclude my talk by telling that, so we are working on several concepts, new reactions, and we are exploring several aspects how CO2 can be used as a reagent rather than considering as a greenhouse gas, and all we are trying to do completely measurably. So with this, I would like to thank my co-workers, Shamaresh, Pradeep. Shamaresh started this work. He's right now at TU Bharali. Pradeep is at Hopkins University. At USA, Shubi, Sridhar, Shomi, and Utpal right now in my lab is the students. I thank ISA Kolkata and staff for supporting us, and also Shopnpati and Ayandatno for their contribution in theoretical calculation. With this, I thank you very much for your kind attention.
Thank you, sir.
Yeah.
Is there scope for any question session?
Yes, Professor Utpal, you can go ahead.
Professor Mundal, congratulations, excellent talk. I have a couple of quick questions. You talk towards the end. You talk about using borylene cation. What's your take? What is your thought on using base stabilized borylenes?
Base stabilized borylene?
No, base stabilized borylenes, neutral borylene, base stabilized.
I'm sorry, I'm not getting you actually. So you.
I repeat, neutral base stabilized borylenes, the one made by Guy Bertrand long back. So you have.
So if you look at some studies by especially Douglas Stephen, and later on by the work of the lady who is now the chief of SCS country. I'm just missing the name actually. So they have done certain work actually on this topic. You can go and look at that. I'm just missing the name. I'm sorry. So if you look at the editor-in-chief right now.
No, that's okay. But my question is that
We have. I'm sorry.
Can you hear me?
Yeah. Yes.
So you have taken that boron cation. So is there any specific reason for taking that cationic stuff? Why not do it some neutral one, like as I said, neutral borylene?
Neutral borylene. I think it has been used for CO2 acquisition, but I'm not sure that has been used catalytically. It can capture CO2. Okay. But in borylene preparation, if you look at the borylene preparation is not going to be so easy, right? Yeah. So you have to use potassium, graphite, and all these things as a reducing agent. So it's not easy to study as a catalyst. So that part is a practical, realistic part actually. But in principle, borylene of course can capture. I think there are some reports of borylene and carbon dioxide capture.
Okay. Thanks a lot. Yeah. Thank you.
If anyone has further more questions, they can ask.
Sir,
hello. Yeah.
I would like to know what is the present status of India towards carbon dioxide contribution.
What mean by that present status means you need to say the industry or?
Yeah, industrial or do the Indians, the scientists really wants to concentrate on the carbon dioxide conversion, or they need to focus on some other research area that can help the Indian economy?
Look, it's a big question actually. I don't know how far I have time to answer actually. Definitely this is a problem we have to work on that. And this is one problem. The other problem is that how to split water. Ideally, so if we can create green hydrogen from water splitting and then use carbon dioxide for induction, that will be great way to deal with it. Right now, whole energy sector is trying to move from so that carbon-free society. 2050 is a target here that way we can try to achieve carbon-free society. But right now we are not nowhere close actually. I think it's a cheap, so any energy we create today, it will emit carbon dioxide. So I think the best way is how do you really take care of the carbon dioxide to value product. And for that, ideally, you can use the hydrogen for the reduction of carbon dioxide. That will be really great. But at this moment, I don't know much in India, this green hydrogen and carbon dioxide together for a realistic process, anybody is working on it. At least I don't know. But that's a very tough problem.
Yeah. Thank you, sir.
Sure.
Thank you, sir. Our next speaker is Professor Partha Sarathi Das. He pursued his PhD degree from CSIR National Chemical Laboratory, University of Pune, and has acquired postdoctoral experiences from across the world. That is from Howard University, USA, Tohoku University, Japan, and RWTH Aachen, Germany. He has been awarded with Bronze Medal of Chemical Research Society of India and also been honored with various dignified positions in many research societies like Council Member of CRSR, PEC Member of Technology Development Board, DST Government of India. He is presently working as a professor in Department of Chemistry, IIT ISM Dhanbad. Sir, you may now begin your talk.
Good morning to all of you. I hope I am audible. Yes, I am audible to all of you. Yes, sir. Good morning, you are audible. Yeah, good morning, very good morning. It's a pleasure to be with you today morning. And sharing the chemistry with you, and particularly I am grateful to my good friend Pankaj and Utpal for the kind invitations. Okay, so and of course this is very exciting to be with you in the interactions today morning. Okay, let me begin with the presentations. So what I am doing, I'm just off my camera, so I will be on into the presentation mode, so that will give a clear picture on my presentations. Okay. I hope it is visible. Yes, it's visible. Okay, great. Yes. So I think the national conference which proposed by Chemical Sciences, Tezpur University on sustainability, medicine and clean energy. So today I am going to share with you our thoughts, our chemistry in the sustainability, and which is very much related to the medicinal chemistry. Eventually it takes the healthcare sector, medicines and molecules. Okay, so when you talk about the drugs, when you talk about the healthcare system, when you come with the drug discovery process, you have to take care of the two chemistry which is very close to our heart. Okay, so one is the organic chemistry and another is the medicinal chemistry. So as I started my journey with the industrial research, so when I start to looking into this kind of things, how to make the bridge between the organic chemistry and medicinal chemistry and solve the problem of the industry and staying in the academic circles. So to start with the discovery chemistry, so when we think about the molecules, when you think about the new drug compounds or new drug chemotypes, so you have to come to a organic chemistry, make the molecule, test the molecules in a biological systems, and eventually you come up with a candidates which is called the developmental candidates, the drug compounds. So this is, I say, this is a make and test kind of phenomena. So to make the meaningful progress of a quick entry of the molecules into a biological system, then come out as a lead compounds, and which can potentially be a drug compounds in a future, you know. So that's the overall gain for the chemist. So when you exercising the organic chemistry, and particularly when you are looking the medicinal chemistry, you have to develop a lot of tools, synthetic tools to make the meaningful compounds. Of course, this process is a very iterative process when you need a lot of molecules to a lot of compounds, and a lot of chemistry has to be developed to overcome the in vitro, in vivo, whether it is a pharmacokinetics or pharmacodynamics techniques to come up to a lead compounds and then make to a drug-like compounds to have the various therapeutic areas, okay? So in this form, so what we do, the organic chemist particularly when we do these things, so we talk about the sustainable chemistry. So when it comes to the gram level, to the kilogram level of synthesis, whether in the medicinal chemistry lab or you are in the process chemistry labs, so sustainability is extremely important, because the sustainable give the affordability, the affordable synthesis. And to make the sustainable and affordability, you need a tools. You need a good tools, whether it is a mechanical engineer or a chemical engineers or a chemistry guys. Today tools are extremely important. And all the reactions, whatever we developed and whatever we make it to make a meaningful compounds, these are all sustainable tools. Unless these are not sustainable, they are not delivering the compounds in a meaningful way, your chemistry is half done. So that's the focus of my lab. So what we do, basically, we enterprise of heterocyclic synthesis from concept to practice. That's what we do. And then chemistry of sustainability from laboratory to affordable synthesis. So that's the bridge between the academia and industry. So when you will work for the academia, or you can take the challenges from the industry and solve the academia, it can be vice versa. So you solve the problem in academia, then eventually you can partner with the industry and do a meaningful collaborations in a holistic manner. So that's the whole country is looking for. So where we the chemist has to contribute in a much more meaningful way. Of course, we work on mostly on the heterocyclic chemistry, what I'm going to show you today. So this is the landscape of heterocyclic chemistry. It's changing. It is the chemotype, it's changing. In the discovery process, when you come up with the medicinal chemistry, the scope of intellectual property, when we look at, obviously when you are making a compounds, you have to always think whether your compounds has a value or no into the market area. Improve the physiochemical properties, that's obviously we look when we do the structure activity relationship study, particularly when we look for the medicinal chemistry. And obviously when you come up with the new compounds, you come to a resistance, and particularly in the sector, in the therapeutic sector of bacteria and cancer. And this is obviously true. I will come up with the three very fantastic structures for you. This is the inorganic, the feedback, the start compounds. You can see the structures. It's a pyrimidine-based compound approved. This is a kinase inhibitors and treatment for the myeloid leukemia. And then in 2011, you can see the pan of the time scale where it's hemorrhagic, azindole systems, or the new compounds is approved is labutinib, so which is as a fused system. So the system is changing, the chemistry is changing, the chemotype is changing, so you have to need a synthetic tools to develop. Okay, so that's when I jump from industry to academia. So we start the thinking in this process, and these are the expansion of the tools, and these are the areas we presently focus. And this is an N-annihilation techniques we have developed extensively, and I will tell you what are the advantages of this N-annihilation techniques. I will take a couple of examples. And this is a selective N-annihilation techniques with the help of coronets donors. This is famously known as Chamberlain coupling, and my good friend Utpal has a good contribution in this area too from Tezpur. This is recently we have wrote a review on synthesis with Professor Lam, who is the co-inventor of this then we work several heterocyclic systems. Particularly, I will discuss with you today azimuth systems, which is a very, very important. You can look our feature article very recently came in CAPCOM to have a valuable findings how these agile systems in a biological phenomena. So these are the drug molecules which is very, very close to this kind of techniques or this kind of synthetic tools can be utilized. We work another area where this just before I listened to the carbon dioxide techniques, how it had been utilized in the synthetic purpose, but we use the carbon monoxide techniques for the carbonylations, and we use basically the surrogates, not the gaseous phase reactions. So use the particularly solvent. I will couple of examples I will brought for you where the chloroform has been used, and very, very old reactions, these reactions, how it has been utilized to give the chloroform convert into a carbon monoxide. Okay, and of course we work on the sequential arylation techniques, so where we have these things. So you can find the chloroform as your surrogates. Recent developments in organic biomoleculars is a very invited feature articles. And then the strategy of sequential arylations in the perspectives in last year in Journal of Organic Chemistry. Well, so why we are so interested in this kind of techniques and these things, whether you take the N arylation, C arylation, particularly I am going to look at the whole phenomena is going to be happens. So this is, if you think that kinase inhibitors, which is one of the area where we focused most of our research when we are designing the chemotypes. This is the particularly the how it's really work into the biological systems when you design the kinase inhibitors. So basically we do the ATP, the adenine part, the mimicking part, and there's we have a donor and acceptor kind of properties. Then we do come up with the selectivity, and particularly two regions where you can hydrophobic pockets 1 and 2 and phosphate pockets. And this arylation techniques actually works very nicely to come up with a new design of the kinase inhibitors, and they are quite stable, particularly aromatics and heteroaromatics, most popular in the hydrophobic substitutions because they are metabolically stable and they can give these various substitution patterns in fine-tuning of the pharmacophysical properties of a drug molecules. And that's the techniques is extremely important when you can come up with a particularly kinase inhibitors today in the designing part. Okay, so keep on this mind. So what we thought is to take some kind of heterocyclic system, so where we have the challenges, so how to overcome these challenges with our new techniques developed, the chemistry developed, and followed by it can be utilized by the medicinal chemist. Okay, so this is a azole system. So azoles are everywhere, today in the drug, whether it is a imidazole, benzimidazole, pyrazoles, this kind of systems. Anywhere you take up today, any medicinal chemistry literatures, you will find plenty of this kind of things. Take one example of benzimidazole systems, which is the third best abundant heterocyclic today has been used in the top 200 drugs, which is a commercially successful drug. I am not talking about the academically exercised. This is a commercially successful. So if you take 2 amino benzimidazole systems, okay, so there are challenges. If you have to then focused, I told that's why selective, sustainable, focused on these things. Okay, so if you have to take this any kind of selective N-arylation techniques, whether you have to go N1 or C2NH2, there is really a challenge for you. Okay, so please look after our invited feature articles in CAPCOM for the selective N-arylation of azoles. You can find a lot of information from there. So this is the couple of drug molecules which are just I would want to draw your attention in these things. Aurora kinase inhibitors, mTOR inhibitors, and that's the compound, the last compound, which really presently we work on the C-Jun N-terminal kinase and solve the issues, how to solve the issues. So before that, what was, so we want to challenge the book world Hatti couplings in this manner. Okay, if you ask anybody, any chemist to do the things, simple N-arylation kind of exercise, he will think the book world is kind of starting point. expensive palladium catalyst, and it will go for kind of phosphine ligands. And the interesting part in the phosphine ligands are quite expensive, and these are patently protected. So if your industrial setup, you can bring it today. So you have to pay very high royalty for the to use for a commercial purpose. So that's why still, in the industry, the copper chemistry is still more popular. It is not the palladium chemistry, though we exercise many in the academic format. But whenever in industry you go in a kilogram level, multi-kilogram level, ton level, I think copper is actually do the purpose. And we solve the issue. So how we solve the issue? So this is a selective N-annihilation techniques. This is a open flux chemistry, coronet as a donor. N-annihilations, we do the CH2 N-annihilations with a 1C2 amino group, and we can do in the C1 annihilations techniques in these things. So these are highly successful in the heterocyclic chemistry, like if you can take bench imidazoles, pyrazoles, indazoles, or piridoimidazoles, or pyrazolopyrimidine class of compounds. These are a couple of results. So you can how sustainable this chemistry are. These are very, very sustainable. This chemistry, it can tolerable at least in the others highly sensitive functional group, or do the eventually it can go the further derivatization like bromo, chloro, or other groups are sustainable. Even in this phenomenon, you can introduce the heterocyclic like pyridine, like thiopene, or other heterocyclic chemical class of compounds, and yields are very, very good in this phenomena. So you can get selectively only one product, okay, only N2. So it is not going to be touched in these things. Only this portion is going to be touched. So you can do the purpose. So palladium has been replaced by copper. It's almost 10,000 times cheaper than palladium chemistry. Okay. So this also be successful with other heterocyclic class of compounds like pyrazoles. This is a pyrazole system, indazole systems, or it is some kind of purine kind of substance. It has successfully been developed. Copper, I have to say, it has been 20 mole % due to by pyridine as a ligand, cesium carbonate, DMF as a very mild temperatures. Just you can warm it the reactions, and this is an open flux chemistry. So you can put the reactions. You can go home in the evenings. You can come back in the tomorrow morning. The reactions is ready for you. So that's the way the medicinal chemistry works. So once your system is sustainable, you can put a series of reactions. Just come back to the lab in the morning. You purify the materials. You keep for the biological testing. So that way your chemistry is sustainable and it is deliverable. So that's the industry phenomena. You have to deliver how quickly you can deliver, and this chemistry actually helps to deliver in a timely manners. Well, as I told that all our chemistry is actually directed for this kind of medicinal chemistry exercise, and we applied this chemistry in designing and developed the C2 and terminal kinase inhibitors. And this is a pyrazole of indazole class of compounds where selectively this NH2 has been derivatized with N-annihilations, and even the NH compounds is not been touched. So this is a copper catalyst, open flux chemistry, highly sustainable. And this is the lead molecules has been designed, has been developed, and it has been successful with these applications of tools. Okay. Well, so this kind of chemistry we have explored. Some others, so when you have multiple sector, as I told you, this chemistry has been completely designed for the selective N-annihilations. You can find it. There is a OH group and NH group. I'm not going back to the chemistry work developed by Utpal chemistry. So if you can, there is a Jack's paper before us. So it was in the N-annihilations use expensive ligand like all phosphine ligands. So, and palladium as a catalyst, sometimes they use pre-catalyst. So our system is very, very robust system. So you take copper acetate in this thing, silver acetate as a oxidant we have used instead of basically the air. And methanol is a solvent, much cheaper, and almost a green solvent in this thing. So you take these aminophenols, you have successfully done. So these are the chemotypes, or these are the new design where you can free the OH group free and you can only selectively protect the NH group. And this has highlighted its impact, so we published these results. Okay, so this is the N-relations techniques we have developed, and now we are working on these areas to come up with a more complicated systems where 2, 3, 4 system, and then trying to apply this amide kind of system where really the book-wall chemistry doesn't work, or even this Ullmann chemistry, which go in a higher temperature, it doesn't come back. So that's the chemistry presently we are developing, and hopefully it will really help the medicinal chemistry to design the compounds with the new chemotypes. Let's come to the azide systems. So we work many heterocyclic, but these are the system we have contributed more. So azide is a very interesting characters. Indole is a king of heterocyclic. You will find a lot of natural products. You will find a lot of drug molecules. This is the isosteres of purine systems, adenine systems. Azide is fantastically work, and particularly if you see, there are 4 type of azide systems. 4, 5, 6, and 7. 7 is very interesting. These things. Why it is interesting? Because it's a 1-3 positions. They have a donor and acceptor properties. So one NH can donate and one N can. So one is pyrrole and another is pyridine. So one is electronically rich system and another is electron deficient system. So that way, for an organic chemist to work in this kind of systems, it is very one way it is challenging, another way it is very interesting. There are a lot of molecules are into the market, commercially successful, starting from temurafenib to pexidartinib, the new compounds, and many are coming. You can see today, you can search the Journal of Medicinal Chemistry or BMCL, you will find plenty of examples on azide-based systems, starting from anti-tumor activities to rheumatoid arthritis activities or malaria or tuberculosis activity. A lot of compounds are today potential, and these are the compounds I have taken which really work for this kind of COVID-19 treatment. They have been repurposed and reused based on the same azide systems. So when we started working these things, we thought this kind of chemotypes we can develop. So these are our contributions on azide systems. So we started with the selective C arylation techniques, and then we come with the carbonylation techniques, then we come with the global arylation techniques, then we put into this SO2 group into these things, and we do the oxidative het additions to keep up alpha beta unsaturated things. I will share with you. So why these are important, So when you work for the design of the new chemotypes and then go eventually into the drug molecules to balance between the pharmacokinetics and pharmacodynamics. So what the industry basically needed in these things. So you come up with a new designing part, the fragments-based design. So if you can see the global phenomena, this fragment-based design actually work fantastic today. And today with these things, in later part, I will show you how in an IIT setup we are working, particularly to the artificial intelligence, MI-based, all these techniques are giving some kind of data sets, which the data sets you can find it, and from data set you can eventually come up with the new compounds, or you can know, okay, this is the molecules you have to hit it, and then you do the structure activity relationship study, and your time scales will be much lower, much lesser in these things to reach to the target molecules. So these are the areas we work for. When we have a new chemotype, like and particularly if you see the fragment-based design, oncology sectors, kinase inhibitors, they part of the most of the cases, and these are some new data about the HIV infections. We have first put this kind of molecules for a basic screening test, and these are the good starting point to look for into this kind of things. This is the first chemistry way back we have started. So this is a selective C2 arylations. We have successfully done it, and then chemoselective C arylations techniques we have done. First C2 palladium acetate, triphenyl phosphates, and so and then we use the oxidant in presence of acetic acid as a medium C2 is successfully done, and then in presence of iodo and bromo it had touched, like it's not going into the like a routine Suzuki type of coupling. Is oxidative couplings happens, and then we come up with a tri-arylated compounds which is very successfully done with a good yield. And eventually what we did, we have come up with a new compounds that which is tri-arylated compound. That is very recent data. This can be done with a palladium. So one after one, you go sequential manner and do it. So this, if anybody wants to read our sequential chemistry, very recently in JOC as a prospect, it has come. We have covered almost all heterocyclic chemical class in a sequential manner. So agile system is one of them. Well, this is a oxidative head kind of thing. So what interesting part, our design completely unique. So what we do in a commercial kind of where you can have a drug kind of molecules. You can see the advanced intermediate like of things. So with a one go, we can make this kind of molecule. This is a room temperature chemistry. In palladium, copper has been utilized as an oxidant, and terminal oxidant is the air. So fantastic examples of a green phenomenon. Lot of functionality has been tolerable in these things, very good yield, and typical mechanisms, I don't want to go the mechanism. It's the CH activation, migrations, beta hydride elimination, and then catalyst regeneration with copper and oxidants. And these are the chemotypes has been developed, and looks like drug-like molecules. And from there you can go into you can turn your thought process into the various therapeutic area if you are interested on agile system. And paramenzyl group, DMP group can be removed, chopped off, and it can be give you exactly the system what you want. That's one donor and one acceptor properties. Okay. This is very interesting in agile system when we try to develop this chemistry. Now we are developing actually this chloroform as a CO source, and if you remember, there is a chemistry, I think, very old, when dichlorocarbon has been utilized is salicylic preparations. But this you can generate this kind of CO, and then CO group can be trapped, and it can be utilized as a source for carbonylations. If you think the carbonylation techniques, okay, the old things, you bring the carbon monoxide gas, put a balloon in a normal laboratory condition. But have you ever thought of that, how it can be industrially successful? So when you have to make the material in the ton levels or kilogram level, that's what I told. It's a learning from the industry problem, solving in the academia. That could be one of the goal of our laboratory. These are very successful chemistry, and we have developed recently published in ChemCom. So when if you can see this kind of amine group which has been incorporated, like this morpholine chain, which is very, very desirable for a medicinal chemist, or this kind of trimethoxy compounds has been also, or this kind of fused amine systems, very successful story with a good yield. So not only these things, not only azindole varies, we have a pyrazolopyridine class or indazole class compounds also we have done successfully. So how the mechanism basically works, first the oxidative additions with and then in situ it has been generated this carbon monoxide, and then come this amines, incorporations, terms, reductive elimination, you get the carbonylated product. And these compounds can be also successfully done in one form. So one Suzuki, one carbonylation technique, but there is a hitch into these systems. Okay, so this is a commercial, this is a successful story with making lot of developing lot of chemotypes for the cell line data for anti-cancer study. We have done successfully with the other imidazopyridine class of compounds. Okay, but there is a hitches with these compounds when you do this kind of things, because you need the KOH into the system. Okay, and functional tolerability is a huge problem, and also we observe there is a problem when you go for this kind of scale-up kind of techniques, So that's the problem. So how to solve the problem? So we come up with a very new techniques. techniques. Okay, this is a completely techniques we are developing with the help of mechanical and chemical engineering peoples. So how it's go? This is a chloroforms you can use. So this is the basic fundamental reactions. We have a, suppose you do the Suzuki type of coupling where you can have a carbon monoxide and fix, and you are to make the ketone kind of compounds. So this is a CO wear techniques, and now it has very popular. So this is a ex situ generation. This is not in situ. This is a ex situ generations of this thing. So how really it works? Okay, so it is a fantastic chemistry can combine with the engineering in these things. So you take the chamber 1, you take the chamber 2, so you put in the chamber 1 chloroform and KOH and the solvent and go to the chamber 2, so it can air and boronic acids and everything is present there. So once you have a carbon monoxide can pass through these things, it's generated, it can transfer, it can go to the second chamber and it can use as a reactions. Okay, fantastic. Ex situ generations, you are detached from KOH from your system. You can minimize the chloroform as a solvent, chloroform as a reactant. So it's highly economical in these things. It is available and cheap, and you can do it to the transfer. But this has a lot of tricks, a lot of optimization techniques. You have to do it. So now presently we are going to do this kind of commercial setup. So where we can use the next step, the laboratory scale up in a lab scale reactor. So that is our next aim, to popularize this kind of chemistry. Well, this chemistry is very useful, in particularly when you want to incorporate carbon-13, So this is the drug molecules level which really we need in a drug discovery process, when you need the carbon-13 level compound to understand the metabolite study. Okay, so drug molecules with the 13 level, and this is a metabolite identification with the stable isotopes. So we are having some successful story in this manner when chloroform has been used as a CO source. This we got a very recent project from BRNS, so it has been we are working on these directions to come up with new techniques for the commercial successful, for the commercializations of these products. Okay. Of course, we also work on the DAP soap, which is now successful story for many chemists to use as a SO2 surrogates, and with the presence of copper, we applied this chemistry in the annual system, and there is also there are some success into this manner. Okay. Well, this is when you today you work in a setup where you have to work in an idea, so your idea can be generated some revenue and it can be generated some kind of collaborations. So this is a story. Actually, what we have done it. So we are working on the selective annihilations of the nitroimidazole system. If you can see, this is the two drug molecules. After a long time, tuberculosis has a two new molecules, delaminate and predominates. Okay, so we have a tie-off now with Arogo AI. This is the as I was telling that you have to work on an IIT setup. You have to work on the techniques and technology best. So when Arogo AI aims to diagnose the drug-resistant tuberculosis through artificial intelligence and machine learning process, so what they will collect the data, and this data can be converted into the in a biological phenomena. So where you can understand where the resistant is working, and where the resistant once you identify the amino acids from amino acid binding, so you can understand the new chemotype, so what you can generate. And this new chemotype, once you generate from new chemotypes, you can come back to your lab, wet lab, and from wet lab. Okay, I'll just take 2 minutes. I will wrap up this thing. So we have tied up the MOU with Arogo AI, and we are working on this direction. This is the last slide of my talk. So as all of are working in the COVID time for the new molecules development, drug molecules development, I think whole country was behind these things. We'll have also a success story on molnupiravir, so EIDD, and this is starting from Unidine. So we have successfully done novel route. This has been patented. Now we have an industrial partner in Bombay, which commercially going to be commercial. If we can get the opportunity, this will be come in a commercial from laboratory scale, we can bring it to the plant scales. Okay, so the whole chemistry and whatever I told, this is about all the synthetic tools and manual being. Okay, so learning the problems of industry, solving into the academia, and that's why it is going to be good phenomenon. It's give a very good training, particularly to the students, to make themselves ready for the. Always I tell to the student, don't be a degree ready, be a industry ready. Okay, the challenges, the problems which are you going to solve in your future, in your career. So that looks everything here, whether you make the synthetic analogs, overall goals in the human well-beings. So before I conclude my talk, I want to share with you the one slides which inspire the students, young faculties, all these things. Okay, these are the acknowledgement. I have a lot of started from Reddy, CSIR, Jammu, then IIT Dhanbad, and then we have good collaboration, financial support from all these people. So before I end, I would like to share with you one beautiful slide, so it will inspire you, many of you. So particularly PC story, why I brought it to a notice, of course, the great chemist. So, but today he's a great entrepreneurship. Today all students, at least in IIT setup, we thought the students will give the opportunity to the entrepreneurship, skill development. So this is a big examples of Atmanirbhar Bharat. Okay, so it's a big examples. So another story of first indigenous drug molecules from India, and though you people are sitting in Tezpur, it will be very amazing story of India's stibamine, Sari, and Brahmachari, the Kalajar, and then when this is a havoc damaging Assam particularly, and this is the drug molecule saves the millions of lives. Okay, and then when you have a cholera and this kind of phenomena, nobody knows this story. I think this is a Calcutta University professor, Anandranath Chatterjee. Today, whatever the WHO formula you take as a what is the water, this is basically developed by him. And just I brought these things from Lancet, which is published in 1953. So I brought these stories with my findings on all these things. This will inspire and again to you to think in a different way, to serve for the society, to serve for the nations. Maybe these are the good examples for you to be inspired. Okay, thank you very much for this opportunity, my friend Pankaj and Utpal, and thank you very much for listening to me and for your kind questions. I will be happy to answer any questions. Thank you all.
If anyone had any questions, they could ask them.
Sir, can you please explain the formation of carbon monoxide from this chloroform, or what the methyl chloride?
No, it's a chloroform. Yeah, it's a chloroform.
Yeah.
Yeah, so this is what exactly happened. So when you put this, this is a known phenomenon. Way back 1983 when first developed, this is a KOH and chloroform we take. It's a formed dichlorocarbon, and eventually take the OH, basically the oxygen is taken from the KOH. Okay, so that is the donor here. So we get from dichlorocarbon to carbon monoxide. Okay, it's in situ generated. Okay, and that's what.
Do you need to heat the solution, or it happens readily?
No, you need a mild heat. Okay, you may not get in the room temperatures.
So, in your experiment, have you measured how much volume of carbon monoxide is released?
No, we don't measure. So far, we don't measure because we are going in a very lower scales. But when we'll go for the reactor scale, we have to measure it because the pressure is necessary at certain point. That time we have to measure. When the engineering things is going to be come out, we have to measure it. Yeah.
Yeah, thank you.
Thank you, sir. We'll have a short tea break. I request everyone to be back in the seminar hall after 10 minutes.
Okay, thank you.
Thank you, Parthada, for your nice talk.
Okay, thank you. Thank you. Bye-bye.
Speaker who will now present before us is Dr. Anupam Sabhapandit. He is currently working as a Senior Materials and Corrosion Engineer in Shell Technology Center, Bangalore. He has contributed to a total number of 10 patents, that is 1 Indian and 9 to US. Sir, you may now begin.
Thank you all, and I unfortunately do not know your name, but am I audible?
Yes, sir.
Yeah, thank you. Just for the introduction, I would like to use the video and then I will go to the presentation mode only. Is that fine?
Yes, sir.
Okay.
Okay, you can go. Okay, now you are visible, and you can now go to the slide share mode and you can proceed.
Yeah, sure. So, can you see my slides?
No.
Not yet?
Slide share mode, you go.
Yes. Yeah, you should see now. Is it not yet visible? Let me start this video. I'm not sure why I'm not able to see.
I think one option there present now.
Yeah.
Okay.
No, it's still showing your entire screen. But I can show that, right? Is it visible now? Not yet?
No.
Not sure why it is not. Now it will be able to see. Yeah, it was a bit slow.
Okay, now it is coming.
Yeah. Okay, you can see my presentation, right?
Yes. Now it is visible.
Okay, good. Good morning all, and thanks Utpal, Pankaj, and all organizers for giving me the opportunity to tell a very young and enthusiast audience what I learned so far in the industry. So I understand that the presentation should be around 25 minutes and then 5 minutes for questions and answers. So accordingly, I will try to cover my topic. It's going a bit slow somehow. So briefly about myself, so that you will know what I learned and where, to correlate with what I'm going to talk. So I did a PhD and then I joined in a chemical company in Pune and worked 3 years with polyacrylamide synthesis and applications. So basically for water treatment. And then I moved to the oil and gas industry. So for last 20 years, I have been involved mostly in chemistry applications in oil and gas industry. And only in the first part of my industrial career, I was involved with simple synthesis and applications. So after that, it is mostly only application type of chemistry. So please expect that what I'm going to tell you is related to that. So my objective today is not to tell about what the chemical molecules that we have been handling, but to tell you about few chemical challenges in the industry that I have been seeing myself and can be addressed by chemists. So whoever is interested in the industry jobs, you can think of such issues, those are coming in your life in future. And with this, you should get some hints of what are the things that those will be, what they are like. So basically, I would tell you about specialty chemicals. What are the specialty chemicals? Few of them I'm going to explain to some extent, and then I will focus more on the challenges of two specialty chemicals that we are facing every day, and the chemist can work on those. So basically, if you see this chart here, do I have a pointer? Yeah, okay. Let me use the pointer. Okay, if you see this chart, the amount of consumption of specialty chemical is almost directly proportional to the industrialization of a nation. So you see China and US are the largest users, biggest users of specialty chemicals, and China is also the largest manufacturer of specialty chemicals along with North America. And so the consumption of specialty chemicals actually directly indicates how industrialized one country or one nation is. Now, what is specialty chemicals? You cannot get a very well-defined definition of it, but what I would say is when you have one molecule which will address an issue very precisely at a very low doses because of its chemical functions designed particularly for that to address that issue, is specialty chemicals. So one example can explain it. For example, there are some issues of formation of ice along the oil and gas lines which are laid in the seabed. So to stop that, people used to use monoethylene glycol or methanol, say 40 to 50% of the total aqueous volume in the earlier days. So you are occupying half of the line's volume with that chemical, monoethylene glycol or methanol or similar things, which are bulk chemicals. So now, after say 70s or 80s, the chemists came up with things like kinetic hydrate inhibitor, which is a specialty chemicals. And then instead of 50%, you just need to use 0.1% or 0.5% of the chemical in the line. So that is how you can really create a picture of specialty chemicals in your mind. So you know about catalyst. You don't have to use hundreds of kgs. You have to use in grams. Similarly, corrosion inhibitors and generally polymeric initiators, polymer reaction initiators, those are specialty chemicals. So there are some kind of other specialty chemicals, they also call them specialty chemicals, like some specialty paints, etc., which are used in bulk quantities, but I would not go to those in today's discussion. I would focus mostly on the specialty chemicals which are used in very small quantities, even in ppm level. For example, I worked with the chemicals called flocculants, where you use sometimes 0.5 ppm of the specialty chemicals. So that clearly tells you that even if you increase the cost to sell those chemicals by say 10 or 15 times or 20 times of a bulk chemical, still people will buy it and both parties will be benefited, the buyer and the seller, and still they will get better benefit. So many times specialty chemicals may be one single molecule in the formulation, but in several cases, those may be a mixture of multiple molecules and one or two solvents. For example, the corrosion inhibitors, in many cases, are a mixture, a non-interacting, non-chemically interacting mixtures of 3 or 4 organic molecules with 1 or 2 surfactants and 1 or 2 solvents. So today I would like to tell you about 2 specialty chemicals. Those are very widely used all over the world across industry lines, and those are corrosion inhibitors and scale inhibitors. So let me tell you briefly about the process in a few minutes, why we need corrosion and scale inhibitors. So I put this picture here intentionally. So if you see the lines here, the pipes, outside you can see a coating. So even if rainwater and other environmental conditions create a corrosive environment here, you can protect it outside by using paints. But what about the inside? If you are flowing some, say, acidic fluid here or acidic gas with some water vapor here, how you are supposed to prevent the corrosion inside in case you have corrosive metals there? In many cases, these kind of pipelines are metallic. In most cases, it's called carbon steel alloy, which is industrially viable in most cases. So there you need something to be injected in the fluid itself. So that is where the corrosion inhibitor comes, and that is where the scale inhibitors also comes. Because if you have something which has a scaling tendency inside such pipes or equipment, and then form scales there, it will definitely degrading your productivity. So being chemistry students, all of you are very well aware that when you have metal, water, and oxygen together, you will have corrosion. To whatever extent, you will have corrosion. Now, you will have to mitigate that in a feasible way. Now, thermodynamically, if this condition is there, you cannot really stop corrosion. What corrosion inhibitors do is minimize the corrosion rate. So different industries has different limits of corrosion allowance. So they calculate how thick their equipment or pipe or the machine's wall is, and they can allow a certain amount of corrosion considering the total life of the equipment. For example, if you have a 10 centimeter thick carbon steel wall, and if you have a corrosion rate of say 0.001 millimeter per year, that is the penetration rate of corrosion, then possibly you can sustain with that 10 centimeter wall with that corrosion rate for 20 years or 25 years. So if a corrosion inhibitor can reduce the corrosion rate to that extent, then it is called a successful corrosion inhibitor. And same is the understanding with scale inhibitors. So you probably cannot really stop scaling entirely. But what people try to achieve is to reduce the scaling tendency to a certain extent so that it always keeps the lines or the tanks in a workable condition, safe condition. So the major applications of corrosion and scale inhibitors, I would say there are many, but what my experience is concerned more about oil and gas industry, because I have been working in that industry for last many years, and then mineral processing. For example, you have alumina refineries, you have zinc and iron ore refineries where you use a lot of water in the process. So actually, wherever you have water, including municipality water treatment plant, water lines, cross-country water lines, cross-state water lines, everywhere, you may have these two issues, corrosion and scaling. And then you have to use corrosion and scale inhibitor there. So practically, most industrial applications and industries, most of the time, need scale and corrosion inhibitors. However, there are hundreds of different mechanisms of corrosion as well as scaling, and then whoever is interested, you can really get into it. You can do a good research and you can find things there. This is not, today I'm not going to cover those. So let me go to corrosion inhibitor and scale inhibitor one by one and tell some challenges in the industry. So in the very early times of industrial oil and gas production, for example, people use just crude oil as a corrosion inhibitor. For example, if they have to pump some acid through a production line, say 1 kilometer down the surface, they would first make sure that they pump some crude oil there and form a layer, and then they will pump the acid. So for different purposes, particularly for cleaning up some production ways down the production line, they need to pump hydrochloric acid up to a concentration of say 28%. So now consider a situation where you have a temperature of say 105 degrees centigrade and you have 28% hydrochloric acid, and you will keep it there for say 3 to 4 hours, and still without corroding your alloy. It may be different kinds of steels, but it will still corrode very fast when you have that situation of acid and heat temperature. Now, initially they used only oil or any kind of temporary coating to prevent those things, but which time, say in 1970s or 80s, the oil production went into hotter regions because you had to go to deeper reservoirs. So these techniques could not work further for those. And then people came up with different molecules. So one interesting thing is that some arsenic and sometimes some antimony salts and compounds were very good corrosion inhibitors, which can protect your alloys at a very high temperature in very highly acidic situation as well, because they do not allow the hydrogen to form. So it's kind of cathodic protection for the metal. But those were very toxic chemicals. I mean, nobody will today allow arsenic to be available anywhere in the environment. So those are not popular. Those are not practically used in today's industry. So now, in the latest version of corrosion inhibitors are actually organic molecules, which are mixed formulations, basically. As I told at the beginning, those are like mixtures of quaternary ammonium imides and imidazolines sometimes, and some surfactants to dissolve them in the medium. For example, if you are using methanol or ethanol as a solvent, you have to use sometimes some kind of surfactants to dissolve all these components together. So basically, the modern industrial corrosion inhibitors are, say, 5 to 10 molecules, different types of molecules in one formulation, kept together using the power of solvent and surfactants. And the corrosion inhibitors, I will show in the next slide, is like a kind of surfactant, you can say. So how they work is, if you consider, let me show you a few molecules before this. So if you consider these molecules, these are kind of corrosion inhibitors, very well known, very capable to perform at different harsh conditions. So one is cinnamaldehyde. So it's coming from the cinnamon oil. Another is propergyl alcohol. A very common type is quaternary amines. So you see this molecule, it's a quaternary molecule. And then even inulin, which is a kind of diluent for chicory, for coffee, in fact. That is also a corrosion inhibitor. Now, you see that these are different types of molecules. Not all of them are similar in type. Here, you have this end which will help the molecule to get attached or to get dissolved in the aqueous fluid, and then it has this hydrophobic end here, which may form a layer like this. So you can note that there is no very well defined or very well understood mechanism for any inhibition performance in the industry. It's a kind of understanding. So maybe some people may find out up to 100%, 80% or 70% confirmation that this is the mechanism, but nobody can guarantee that this is the confirmed and guaranteed mechanism of so and so inhibitor. So the commonly accepted inhibitor performance is like this. So you have these hydrophobic ends here, and you have the other end attached to the metal surface like this, and it forms a hydrophobic layer which will stop the water to approach the surface of the metal. So if you increase the doses, they generally form a more protective layer, and if you increase it further to a very high doses, most of the times it will fail. So you have an optimum doses here in the middle picture where it perfectly protects your metal surface, and you have to find out that doses by experiment. So now if you think about a situation like this, if you increase more doses, more and more here, first thing is thermodynamically it will suddenly form the layer which will not be very uniform. It will be non-uniform. So you have differences in terms of electrochemical resistance along the surfaces, and then you will start having something called localized corrosion, which is called a pitting. For example, in this position, possibly you will have a thicker layer. In this position, you will have a thinner layer. You will have a electrochemical differences. It will get opportunity to form anodes and cathodes, and it will start pitting like this. It will form a small pit here, and that is also equally dangerous for the pipeline and other vessels. Imagine you have a leakage here, hundreds of such leakages there, and you cannot use those pipelines there. So I will come to that next. So if you see here, so mechanism of this may be different compared to this one, and the mechanism of working of this will be different than this one. So inulin may be forming a simple layer rather than hydrophobic or hydrophilic. It will form a simple layer as a polymer on the metal surface, and this may actually form initially some oligomers, because this electron density here very high. It may form a couple of 3-4 molecule oligomers when it will come in contact with acid, and it form a layer on the metal surface. It is actually a very strong corrosion inhibitor, but again, because of environmental difficulties, you see the triple bond, which is not welcome in the environment anyway. So these are not used that frequently nowadays. So let me come to the challenges now. So I believe you have a kind of idea about what kind of molecules and how they work. Now think about these challenges, and my objective is to tell you about these challenges, which possibly may not be available to the academics easily unless you really come and work in some joint projects. And I saw that the universities in the kind of oil and gas heartland of Houston, they actually address this kind of issues very focused. I mean, they do PhDs and PDF, and even in masters they do address this kind of chemistry research. So let us see the first one, prediction of performance. Now, if you are designing a corrosion inhibitor, you should have in your mind that what molecule possibly you should look into. How do you know that? So consider the situation that you have, for example, oil and gas production. You have some brine coming from the reservoir along with some mix of hydrocarbon with some hydrogen sulfide gas and carbon dioxide gas dissolved in it partially, and you have 2 or 3 phases flowing. So you have a complicated mixer, you have high shear, and you have change in flow rate, temperature, and pressure together. So how do you design a molecule which will perform in that situation? Now, so far, even the most advanced corrosion inhibitor manufacturers all around the world actually rely on the conventional knowledge and understanding rather than the latest computational chemistry and other tools because of the complexity. So I had to work with a group, computational group, to design corrosion inhibitors. Then we realized that as of now, you can see the references. I will share this presentation. As of now, the latest or the most advanced computational design actually can address a situation where you have a iron surface which is having water in it and the corrosion inhibitor molecule. So now, if you add to it oxygen, crude oil, carbon dioxide, and few other things, the computational tools are not capable of handling that situation. So you cannot really, as of now, use the computational modeling to design a successful inhibitor molecule. But what I am telling you is, why don't you try? I mean, if someone is really interested in really addressing this computationally, it should be possible. It needs some innovation. Possibly industry is not focusing on that to that extent. It's a good scope for the computational chemists to address that. And then there is a more basic chemical challenge here in the second point. So you know about the partition coefficient. So if I add the corrosion inhibitor to a oil and water mixer, I would expect that, okay, it will partition to this extent or that extent. So I should be able to calculate the doses of how much corrosion inhibitor I should add at different water levels. So what happens is, when oil and gas is produced, you produce all the time some water and some oil. So the oil percentage may vary from, say, 1 or 2% to 80 to 90%. Now, keep doing lab experiment for each and every water cut, that is called water cut, is not really practical or possible. Now, if you do lab experiment and fix the doses of corrosion inhibitor for, say, 50% water, 50% oil, then what would be the doses of corrosion inhibitor when you have a different production rate of, say, 60% water or 70% water and 30% oil? So if you consider the partition coefficient test in the lab in a simple way, that's a simple answer. Okay, use partition coefficient and calculate the doses. But that is not the real case, because you have such a complicated mixture of water and crude oil and gases, and you have such a complicated mixture of corrosion inhibitor itself. So how you will calculate the dose? So that actually pushes us to a very rigorous and time-consuming and extremely costly corrosion inhibitor testing in the lab. So if anyone can find out a way to calculate the doses based on only few lab tests, that will be a kind of breakthrough. It's non-existing right now in the industry, at least oil and gas industry, where you have mix of oil and water all the time. And the next challenge is, like any other chemicals, environmental friendly corrosion inhibitors. In most of the cases, for high temperature, you always have some kind of ecotoxic chemicals performing very well. When you go to the greener side of the chemistry, they are not sustainable in most of the cases in the high temperature region, high temperature zone. So that is the challenge. And then the last thing is how to minimize the interaction between different chemical additives, because you do not add only corrosion inhibitor in your fluid. You add many different things: scale inhibitor, corrosion inhibitor, different surfactants. How do you minimize? Because it is impossible to completely eliminate the interaction, but you have to minimize it to get your performance, expected performance. Otherwise, you cannot really use them. So there are a lot of scopes to address them and design molecules accordingly. So the next thing is scale inhibitors, which are much more well-defined and understood better than corrosion inhibitors. So a very simple thing, suppose I am pumping seawater to a oil reserve where you have barium from the reservoir water, it will form a lot of barium sulfate. Now, it is insoluble in water, but that is not a problem. That is really not the problem of scaling. So as far as barium sulfate or any scale is suspended in the flow and coming out of the oil and gas pipeline, it will not really create a big problem there. So the problem is this, where you have this barium sulfate and other scales actually forming the scale, the accumulation here. So if you see this, the diameter of the pipe is reduced to half. So instead of say 2000 liters, you are producing 1000 liters per hour here. So it's a huge economical loss, unmanageable. That is why scale inhibitors are introduced to stop this phenomenon. So scale inhibitors are not really intended to stop this. So they are mostly intended to stop this one. So there are two different types, thermodynamic and kinetic scale inhibitors. So thermodynamic scale inhibitor is basically, you know about EDTA, which will capture all iron and similar ions, and it will keep it soluble in water medium. However, imagine if you have to catch all the ions in a huge amount of fluid, how much money you have to spend. So this is not a feasible option for things, huge amount of fluids like oil and gas production. There you use kinetic scale inhibitors, where the intention is to stop the solid deposition on the metal surface. So here they use a different type of molecules like polyacrylates and polysulfonates, etc. Mostly polymers up to a molecular weight of 100,000 Dalton. These are some examples of popular scale inhibitors. Although as I said, the EDTA is not the one that people will prefer. And then these are the kind of typical scale inhibitors. They are used in in the salt formation, sodium salt of say polyacrylic acid or vinyl sulfonate, polyvinyl sulfonate copolymerized with other monomers. So they work as the best industrial scale inhibitors nowadays. So most of them are basically anionic in nature. If you see this is anionic. So if you form sodium ions here, this will be anionic in the solution. This will be anionic. So most of them are anionics. There are examples of non-ionic and cationic inhibitors as well. So again, like corrosion inhibitor, you still have challenges in scale inhibitor as well. So scale inhibitors are very highly sensitive. If you change the pH a little bit, it will fail or it will not give you the performance based on that condition. So as temperature and presence of other chemicals. And then interaction of other chemicals play a very significant role in performance of scale inhibitors, especially with corrosion inhibitors. If you see these, for example, EDTA, and if you mix EDTA with, say, this molecule, both will consume each other. It will not work. So you have to be very careful in selecting inhibitor and inhibitors, considering the presence of other molecules there. And finally, if you really cannot depend on the design itself, and you have to do hundreds of lab testing, that is not feasible, because lab testing of inhibitors are extremely costly and time consuming, and not that each and every lab can do it. So that is all from my side. I think, yeah, I crossed 1 or 2 minutes, but that is all from my side. So if you are interested, I will share this presentation. You can see these references and see what the industrial works and interests are there in corrosion and scale inhibitors. It's a very wide field. You may find it interesting. And then there are some complexities in doing modeling, etc. So I added those. And this is one equipment that we use for corrosion inhibitor testing. You can see you can use very high pressure, temperature, etc. And this is used for scale inhibitor testing, etc. So that shows clearly that it is not easy, not feasible economically and practically to test everything there. That is why we need more theoretical understanding. So that is what I wanted to tell today. Now, maybe some questions if you have any.
Thank you, Dr. Sabha for your nice nice lecture. And we have the different flavor from your talk that how these chemicals can be applied into the industry. Basically, in the academics, we do not have that type of understanding. I have just a small query. So for corrosion inhibition, you use some chemicals. So is that chemicals effect on the quality of the fuel or maybe crude oil which is flowed through the pipeline?
Yes. What we have to see is that is another thing that we need to always take care, because what is called the downstream or the refining part, there the additives may impact. That is why you have to limit the doses. You have to know what kind of refining will be applied to this inhibitor. So these kind of things are always considered. Yes, but corrosion inhibitors are used in such a small doses like 10 ppm to 100 ppm to 150 ppm that it is hardly impacting down the line, and most of the part is getting absorbed in the metallic line itself, so it may not reach the refinery at the end.
Okay, thank you.
Yeah. Okay, thanks. Thanks for giving the opportunity. If there is no questions, possibly you can go to the next presentation.
Thank you, sir. Our next guest speaker is Mr. Aravinda Agarwala. He is a patent analyst and senior scientist in Intellectual Property Analysis team in SABIC, which is a Saudi Arabian multinational chemical manufacturing company. He is bona fide with novelty, FTO, and various R&D experiences in field of polymer science and analytical chemistry. Sir, you may now proceed with the talk.
Hello, am I audible, Utpal?
Yes, so before starting, I would like to inform our students that Aravindo is the first best student of our department, and during his as a student in this university, was a brilliant student. So you will be happy to have your brother giving a lecture in front of you. Okay, Aravindo, go ahead.
Thank you so much, Utpal. It's a moment of pride that I am here today to share a little bit what I basically have learned over the year in the industry. Can you see my screen?
Yes, yes.
Okay, great. It's a moment of pride and happiness for all of us that the department where I took admission in 1997 as a first batch student of MSc Polymer Science has completed 25 years, and it's a vibrant department now. So good morning to all my fellow speakers, my respected teachers, my faculty friends and student friends. So the topic today of my talk is invention, innovation and patents. So you have heard mostly on technology development and how chemistry is playing an important role in improving the quality of our life by having a positive impact on sustainability till now. I will give a little bit of different flavor, how intellectual property rights can enrich the technology development, how it can basically transform inventions into innovations that impact life across the globe. So if you see the agenda of my talk, I'll be talking about invention, innovation, intellectual property rights, patents as a bridge for transforming invention to innovation. And lastly, for the benefit of our student friends, I'll touch upon how patent can be taken as a career prospect for science and technology professionals. So in this slide, you can see inventions many people try to define as a new solution to a technical problem. And here I would like to highlight that invention is different than discovery. Discovery is highlighting or finding a existing thing which was not known. But invention is coming up with a new solution which was not existing for a problem. Also, invention is, people define invention as basically the process or the method where you use your cognitive skills, you do experimentation, you do a lot of theoretical research, and then with these efforts you come up with something new which was not known. Now, what can be an invention in terms of science and technology? Invention can be with respect to a molecule. For example, you come up with a new pharmaceutical drug molecule. That can be or the previous speaker, Napaam, was telling corrosion inhibitor. So if you come up with a molecule which was not known before, and it is a very effective corrosion inhibitor, that can be an invention. A formulation. And you use the same corrosion inhibitor molecule and you make a formulation with some other additives in it, and that gives you the desirable property which Anupam was mentioning, that it should not interact with some other components in the system. At the same time, it should achieve its own desired performance. So that formulation can be termed as a new solution to the technical problem, and it can be regarded as a new invention. It can be a process. So a process of basically making some chemical. Now here, let's say you came up with a catalyst as a new catalyst as an invention. So there can be multiple inventions with respect to that catalyst. The catalyst composition itself can be an invention. And let's assume that catalyst can be used in more than one reactions to produce more than one products. Those reactions also we can claim as new inventions, because the use of this new catalyst for those reactions are not known yet. You have used a new catalyst for making existing molecule, but this particular process of making this molecule was not known, so that can be an invention. Invention can be with regard to an apparatus. So the fountain pen or the pencil which we use, which all of us use, that can be, we can say that is an apparatus for writing. So that can be an invention. Invention can be an article. So let's say a laminate, multi-layer laminate film, or a polymeric film. So basically, these things can be regarded as invention. Moving to next slide. Okay, so innovation. Now, innovation is, many people say, when you derive economic benefit out of an invention, basically we come up with an innovation. Innovation may or may not always include invention, because see, innovation can be not necessarily always technological innovation. It can be a social innovation. It can be any other different healthcare innovation, where you have improved some aspect of the system to touch a wider audience, to improve the life of wider audience. But I will restrict the scope today with respect to technological innovation. Now, innovation is basically always the best definition. What I like is, when you derive some economic benefit out of your invention and you improve the quality of life in the society, that is to provide the society with better means of life, that can be termed as innovation. So there is a very subtle difference between invention and innovation. although you will observe while studying or the internet, many people use interchangeably the words invention and innovation. But for me, that's not the best choice because there is a subtle difference. Now, the couple of examples which you see at the bottom, all of us are familiar with these products and all of us use these products day in, day out. First is 3M Innovation Company's Post-it. Sorry for the typo there. Post-it. So, Post-it, when originally developed, the mandate was to develop an adhesive formulation. But the adhesive formulation did not show the desired strength, adhesive strength. But a use of a weak adhesive in terms of Post-it have done wonders for the mankind as well as the company. So this is one example of a brilliant innovation. Second is Edison's bulb. So you will be interested, you will be basically amazed to know that before Thomas Alva Edison, there was already a patent on the bulb. Basically, in the bulb, the critical component is the filament with a high resistance. When we pass the current through the filament, it glows and we get the light. And the filament is basically encased in a glass chamber. But the previous system did not work practically to give us longer hours of the illumination of the longer hours of life for the filament. So Edison, after thousands of experiments, in fact I have read thousands of experiments, he came up with the filament which will glow and which had a very long shelf life. So this is a fantastic example of invention transforming into innovation, touching upon the lives of millions or billions of lives. Okay, so I'll go to next. So there is a very good quote from one of the serial entrepreneur and many companies he established and he did many inventions. Philippe Cahn from France. Invention is the root of innovation. Innovation is the major force for change in the future. So if we do only invention, it may lie with us or it may lie with our organization, unless we implement it for the benefit of the greater. Okay. Now, this is a slide, a refresher slide. Most of us know about intellectual property rights today. So they are the intangible rights which you cannot touch basically, and they are provided to you because of your cognitive developments. Now, the most important examples of IPR, some examples I have put: patents, trademarks, trade secret. The famous example is the Coca-Cola formulation. Geographical indication, for example, Assam tea or Darjeeling tea. For geographical indication, the product has to do something with the climate, or it should have some attribute of the place of origin, like Scotch, or for example, Mathura Peda maybe, or some silk, Kanjivaram silk maybe. So it has to do some speciality or with respect to place of origin. And then copyright, where you express your basically thought or into a tangible medium. For example, a portrait, painting portrait, or a book, or a CD of your song. So now, what can we do once we achieve this intellectual property rights? They can be sold like any tangible property. Now, before getting into this, we can give an example or analogy in terms of whenever we own a house, what do we have? We have a boundary to our house and we have a deed, sell deed. So that establishes the ownership of the house in our name. Similarly, when we apply for some intellectual property right, we have a boundary that what we are claiming, what is belongs to us. Similarly, okay, so now what can we do with the limited rights provided to us? We can sell it to some third party, or on the reverse, vice versa, we can buy a IPR from someone else. We can license it out. So that can be synonymous to lease or rent, or it can be passed on via will to our legal heir, or we can assign it to some other institute or company. Yeah. Now, how does IP help the creators? It protects the economic rights of the creators. Otherwise, if there is no protection, everyone will copy our intellectual creation and have a free ride. And it will also prevent the commercial exploitation of owner of IP. Because tomorrow you may come up with a corrosion inhibitor, which is very vital for oil and gas industry. So if you have a patent on it, you can always license it out to industry and earn royalty on it. Because while developing it, you have invested a lot of human capital, lot of man hours, lot of money, lot of experimentation. So you have every right to enjoy the fruit of your intellectual creation, at the same time benefiting the bigger society. So it also, basically the last point is, it also creates or develops a culture of improving the society by having new inventions. Because it encourages you, once you get the recognition in terms of your name, or let it be monetary recognition, but mostly it is about your name, and it is your contribution to the society. Yeah. So now I will focus out of the IPR mostly on the patents. Patent is a limited monopoly. Remember that, the word limited monopoly. So when you come up with an invention and apply for patent to a patent office of your country, they will provide you the patent for 20 years when they grant it. The life is of the patent is for 20 years from the date of filing. So that's a limited monopoly, provided for public disclosure of your invention. So you need to disclose your invention to the society. So initial 20 years, you will have limited monopoly. After 20 years, the invention will be free for public use. So public will be able to use it freely for the benefit of the society. And one other important thing, always remember, if you have a patent, it doesn't mean that you are free to practice your invention. It's a negative right. It's a right to exclude others from making or using, selling, or offering for sale, or importing your claimed invention. Now I will give you an example. So I go back to the example of pencil. So let's say person A invented a pencil. So where there is a graphitic rod for writing, and the graphitic rod is encapsulated by a wooden housing. Okay. So now person A has got a patent on the pencil. Now person B came up with an improvement on the pencil. What he did, he put a eraser tip on the pencil, and he also filed for a patent in the patent office. And he argued in the patent office that this is an improved product, and patent office granted him a patent on the pencil with the eraser tip. Now two persons are having patent on pencil. And person A is having the patent on the original pencil. Person B is having a patent on the pencil with a eraser tip. Now when it comes about selling the invention, okay, person A can sell his pencil in the market, provided if no third party, no third person has another granted patent on the pencil. Okay, if a third person has a patent related to pencil, which is related to his invention, type of pencil, then he will not be able to sell it into the market. Okay, now person B, you may argue his invention is new. No, his invention is narrower. The broad invention patent is with person A. Person B is having a narrow patent with a pencil with a eraser tip. So person B also will not be able to sell it into the market unless he takes a license from the person A, because person A is having broad legal coverage in terms of the invention. So it's a very complicated, basically these scenarios are often in reality. So you have to do a thorough due diligence when you want to launch your invention into market in terms of products. And the patent rights are always territorial. So if you have a US patent, basically you can enforce your patent right only in US, not in any other country in the world. Okay. So quick basically snapshot on the patenting process. So whenever you have an invention, we should always write an invention disclosure. Okay. So mentioning what are the problem in the art, and then what you did, technical solution you did to arrive at the current invention, and what are the technical advantages you have achieved because of your technical solution. So once you are ready with your invention disclosure, normally we do prior art search. That is, what was known or what is known at the day of invention and before, on today's date and before, what is known in the literature, or it can be in a comic book, it can be in a movie, it can be in a research paper, it can be in a previously published patents, previously granted patents. That is known as patentability. Now, what are the criteria for patentability? So in the bottom I have put, your invention should be new, novelty. So your invention should not have exist in the prior art. Okay. So no single reference should disclose all the elements of your invention. If some single document discloses all the elements of your invention, then we will say that document anticipates your invention and your invention lacks novelty, and because it is lacking novelty, it is not patentable. Second point is inventive step, or it is termed as non-obviousness in US. Inventiveness is a more of a European terminology. So if the invention is not obvious to a person skilled in the art, having regard to the state of the art. So I'll give you an example. So you have some formulation, and you have used, in the prior art, people have used methane as a methylene, basically let's say methane as a component of the formulation. Now you made a formulation and you are using butane, and you are getting much better properties compared to, or relatively similar but improved properties compared to the prior art formulation. Then examiner will not allow you a patent. He would say your invention lacks an inventive step, because to a person skilled in the art, so he is an imaginary person who is having degree or knowledge in the same subject in which the invention has been done. So the examiner would say a chemist would have basically thought that if methane works, then its analog or homologue butane would also work. So you need to demonstrate in your invention that this would not have been obvious to a person skilled in the art. It's completely beyond imagination of basically chemists. I have come up with this to show this very high improvement. And the third point, our invention should have an industrial utility. So they should be capable of making in the industry and have a use. Now, once we do the patentability, we define the scope of the invention which is eligible for getting a patent. Then the patent drafting and filing happens, and the examination happens, and then followed by grant. And whenever you have a grant, you need to manage like for our house property, we pay tax to local authorities every year. To maintain our patent also, we need to pay, most of the countries, the annuity fee is annually. So we need to pay a maintenance fee every annum to keep our patent alive. And another thing can be, we might be able to license out our patent to an industry. Now, this is an interesting, I hope you will find it as an interesting case. So there was an invention. So if a ship is basically sunk in the ocean, how would you float it again? So there was an invention filed by Karl Kreuer in Netherlands. So what he said, he will fill the ship's bottom with buoyant bodies, for example, balloons or some balls hollow. And because if you fill with a lot of them, then the ship will float again. Now the examiner said in 1949, the Donald Duck comic has shown similar thing. If you see on the right side picture, the first picture, they are filling one basically funnel kind of thing with a lot of ping pong balls. And as they fill it continuously, the ship is coming up. So examiner did not grant this patent based on this prior art. He said this technical improvement was already disclosed in this particular comic. This is a very interesting thing which you can see. So we need to be very much aware about what exists in the prior art, what is available in the prior art, before carving out the scope of our patent application. Okay, now how invention, patents help basically invention to become innovation. So if you see the left hand side circle, we have, whenever we invent, normally nowadays trend is to get a patent. Once you have a patent, you can always monetize it by licensing out or by launching a product for the companies like us into the market. Once we have the money, it not only covers our R&D expenses, it always contributes to the profit of the organization. That helps you to grow, concentrate on another problem of the society, again invent. So it's a continuous circle where you can continuously keep on inventing, because you are able to convert your invention into innovation, whereby you are providing the world better life, you are providing the world with a technological progression, continuous growth for the inventors, society and your organizations. Now, couple of Indian case study I have taken from WIPO. WIPO, by the way, very good resource for the students to learn about intellectual property. So if you Google WIPO, you'll be able to come up with the website and you will find tons of resources in the WIPO. So Biocon, all of us know, one of India's largest biotech company. Founder Kiran Majumdar saw, she originally intended to be a brewer, but after coming back from Australia, completing her education, the brewing industry, which is to make basically beers and alcohols, did not accept a feminine candidate. So she moved into, in 1978, fermentation science to make enzyme. And to do so, she was able to collaborate with a company from Ireland. And one of their first product was papain, which is extracted from papaya, and it prevents chilled beer from turning hazy. If you see, almost after 20 years of the company beginning, they filed their first patent, which has grown to 900 already by 2010, exponential growth. And as I said, here in this current talk, I have been concentrating mostly on the patents, but trademark is another strong intellectual property right, which can help you to transform your invention to innovation. So InSCIgnis is a world-known trademark from Biocon, very well-known trademark for insulins. And they have collaborated also with a lot of companies like Novex, Optimer Pharmaceuticals. And if you see, their revenue in 2021 is almost $1 billion, which is close to 8,000 crores in terms of Indian money, and 11,000 employees currently almost. So basically what I am trying to drive the point here is how they have utilized IPR to convert their inventions into innovations, to grow their company at the same time benefiting the society, creating a lot of jobs for human capital in the country. So they are able to improve the sustainable quotient in our life by becoming a leading innovation company. Now here one important point, Kiran Majumdar always tells, patenting is an expensive business because you need to involve experts in drafting your patent, you need to pay them, you need to pay for the patent office fee. So you need to choose what you want to file, what you don't want to file, because few things are better not filed. You may want to keep them as trade secret. And then when you choose what you file, you need to protect, safeguard your invention, convert them into innovation, and then contribute. So that's the bottom line of this Biocon. Second one is an interesting study from Indian Railway. So there was a engineer named as Boji Rajaram in Konkan Railway, managing director he was. So Konkan Railway, the path is very difficult. It goes via a lot of ghat sections, hilly areas. So there are frequent accidents were reported in the past, causing human life loss and property damage. So there was an accident in 1999 that triggered Rajaram into thought, how can I prevent these accidents? So he came up with an invention, Raksha Kavach anti-collision device using GPS system and microelectronical basically devices and processes. So he filed a patent in 2001 in India, and 2003 he filed several other patent applications. And experts have assessed that potential royalty of his patents could have been $1 billion, huge money, right? But he chose to assign his patents to Konkan for greater public good. And the Konkan Railway provided it to a license to a company called Kernex Microsystem for making the device. And the device have been successfully implemented in the railway with 99.9% accuracy rate. What an inspiring story by an Indian inventor transforming his invention into innovation. So I have a couple of more slides. So before I sum up, it will be apt to talk about academic institutes and IPR ecosystems. So in the Western world, the IP ecosystem in the academic institutes are very well developed. Forget about Western world. If we look at our neighbor China, last 10 years, it has been a terrific improvement or development in their academic institutes, and a lot of their technologies they have been able to translate into industrial products. The technologies which are developed by the students, faculties. So the point I am trying to make here is we need to have a very strong IPR ecosystem, because we are no less cognitively than any other part of the world. We are equally competent. We also develop a lot of inventions, but many a times we do not realize the value of our invention. But we have few success stories as well. One glaring success story from our department, our Robin Datta sir's arsenic removal system, which have been positively impacting lives throughout the world, and we are quite proud of it. But we need thousands of more such success stories, because each of you are capable and each of you have been inventing. So what we need in an university? We need advanced facilities, we need human capital, we need a very strong IPR cell in an university to capture the invention properly, to help the faculties or inventors with the patenting formalities. We need a IPR policy of the university, that how much, if the invention gets translated into a product, or if you give a license to the industry, how the inventors would get benefited out of that. Invention ownership. Let's say one of the student or faculty member invented at his personal time without using the university resources, then the ownership of the patent might lie with the inventor himself or herself, not with the university. So we need to have a clear demarcation in the policies, what is what. Then we should have some incubation centers to grow the technology, where we get some funds from the governments or some other funding agencies to develop some smaller spin-off companies that can basically be acquired by big companies, or that can grow themselves into big companies. And there should be some efforts on the licensing, how to collaborate with the industry, to know how my previous speaker, Dr. Anupam, he highlighted the problem of the industry. So if we have collaboration across the industry, we'll be able to know the problems in the industry, and we might come up with a solution for them. And then the last point is by licensing, when we monetize our inventions, benefiting the public at the same time, we will be able to grow the facilities of our research centers, will be able to involve more human capital, will be able to develop more jobs for our scientific professionals. So it's a circular process, and I have just touched the very high level point. It itself is a topic of a talk. So to conclude, for student friends, for becoming a patent professional, most important thing that you need to have a solid foundation of science and technology, because patent is a mixture of mainly legal and technology. But before acquiring the legal acumen, you need to know your subject in depth. Apart from your subject, if you look at the pillars which I have put, you need to have legal acumen, because it's different from writing a research paper. In patents, what matters is the claims of the patent. So that defines the boundary of your invention. So apart from legal acumen, you need to have IT skills, you need to have data analytical skills, because there are millions of patents out there. So you need to be able to search out, or you need to be able to project some trend based on the prior art. You need to have very good communication skills, because you need to know what to communicate, what not to communicate. Because in legal, every communication matters, and that might be taken up against you later in the court also in some cases, your emails. So, and there could be other pillars in this, for example, economic knowledge for valuation of patent. So what are the options available? You can become a patent analyst, patent paralegal, patent drafting, patent attorney, patent examiner, and so forth. So this itself is again a topic for a elaborative talk. So I would stop here. Thanks Utpal and Pankaj for giving this opportunity to talk today, and I would be glad to take any questions.
Thank you, Aravinda, for a very nice talk. This is a very new flavor for our students. So I have a little bit curiosity about so what is the role of actually patent analyst as a career? So what he has to do in his job?
All right. So to become patent analyst, as I said, Utpal, currently I work for high performance polyimides, and I also support for material development for mega trends. Mega trend means 5G or healthcare trends recent. So I support our technologies in our company for these roles. Now, what skills I need to have? So one of the skills that I should have full knowledge on the materials as a subject. For example, structure property relation in the polymers, or polymer synthesis, or polymer properties, how they can be. We can choose a polymer for a particular application. Now, apart from that, I should be able to have some legal knowledge, basically the legal awareness, what a patent claim means. Okay. So when a technologist wants to develop a product, for example, the previous example, if Anupam wants to develop a corrosion inhibitor, he might write an email to me, Arvinda, can you give a patent landscape on corrosion inhibitors for oil and gas industry? Now, I have the right searching skills, Utpal, because there are several commercial databases which collects the patent documents from across the world in one place, and any common person will not be able to effectively search. There are some searching know-hows which we have been trained on. So we are the right person to search. For example, I come up with 1,000 patents on the corrosion inhibitors. Now, out of 1,000, not all will be relevant. Only 200 or 400 could be relevant, 2 to 400. Now I need to basically knock off the 600 by my cognitive skill, and I need to further deep dive into 200 to 400 to bucketize them into some class of technology, to report back to Anupam, to saying that, Anupam, this has been the trend in the industry or academia, and these are the key companies which are active in this space. There are, hey, look out, there are some small companies who have developed some nascent technologies in this space, and we might want to check out their technology and see if there is a possibility of collaboration. So we give a lot of recommendation. That is one part, Utpal. On the legal part, if my company has an invention, and let's say I have developed a high hit polyimide film, dielectric film, and our company want to launch in the market. Now, before launching into the market, we need to do a freedom to operate. What does it mean? I need to create a report where I need to check out if any third company, any other company than us, have a patent on a polyimide dielectric film. If any other company is having a patent, our company cannot launch the product into market because we will be infringing their intellectual property. And infringement cases can bring a very bad brand name to your company. Court can order millions of, you might be hearing always about Apple, Samsung fighting on the mobile smartphones, and then courts giving millions of dollars of penalty in different countries. Some countries give penalty on Apple, some country courts give penalty on Samsung. So FTO is one of the critical work. And also we deal with the examiner's response. We help technologists to write back to the examiner saying that your objections are not valid, why you are. Our technology is novel, it has an inventive step. So there are a lot of aspects, Utpal. So few of us, we get it from our formal education in the university, and few things we basically catch up along the job. And students can think of doing a PG diploma in patent law, which are via distance mode from Nalsar University. That might help them. Thank you.
Thank you. So if anybody has some question, they may ask to Aurobindo to have more clear idea about patents.
Utpal, can I ask a question? This is Utpal.
Sure, Utpal. Go ahead, please.
Okay. Thanks, Aurobindo. It was a fantastic talk. I think I just have a simple question. Suppose we have some patents and now we want to go to the next step. We want to find some collaborator or some companies who want to use our patents. What is the best way to go ahead?
So, Ujjal, there are multiple things you can do. One thing is, if you are aware from your domain knowledge that who are the company active in that space, okay?
Okay.
So you can, are your patent granted already?
Yes, some of them are granted.
Okay. So you can reach out to them directly, telling that you have so and so granted patent in this technology. If you would be interested to have a interest in our patent, so we are willing to offer license for you. Now, license can be of two types: exclusive license and non-exclusive license. So for your patented technology, if you give exclusive license to me, then you are exhausting your rights in the grant. Basically, I am the only one who will be able to use your patented. But non-exclusive license, you can parallelly grant it to multiple companies. Okay. Now, second point, what you can do, there are some companies in the market space who helps you to license out your technology nowadays. Kind of tech broker company, technology brokerage company. Maybe if you can email me, I will be able to help you with few names. You can reach out to them that I have these patents and I am willing to provide license to the industry for the use. That can be one option. Third option is that you do a search in the patent field in your area to see who are the active company if you are already not known to you. That way you can identify who can be your potential licensees. Okay. Thank you.
All right. Thank you. Maybe I'll write to you. Thank you.
Yeah. Okay.
Thank you, sir. I would be very pleased to inform all the invitees and participants who have joined us in online mode that poster presentation is also taking place in the department in offline mode. And our fifth invited guest speaker is Professor Rahul Banerjee. After completion of PhD from University of Hyderabad, Professor Rahul Banerjee served University of California, Los Angeles as a research associate from 2006 to 2008. He is presently working as a professor in Department of Chemical Sciences, ISAR, Kolkata. He has been awarded with various distinguished awards and honors, and one of which is Shanti Swarup Bhatnagar Prize in Chemical Sciences for 2018, jointly with Professor Swadhin Kumar Mandal. I would now hand over the screen to Professor Rahul Banerjee, sir.
Thank you very much, madam, for this kind introduction. I am audible, right?
Yes, sir.
Excellent. So thank you so very much. And let me first share the screen. Okay. Okay, thank you very much for this kind introduction and this kind invitation. On the very outset, I'd like to thank all the organizers, my friend Vipul, Dr. Pankaj, and others for their kind invitation. It would have been nice to visit Tezpur University. I have never been to that part of India, so if I get an opportunity, most certainly I'll grab it in both hands. So today let us discuss in about next 20 minutes or so something about the porous materials and what can we do with that. So I will discuss mainly about the covalent organic frameworks. This part perhaps I have to just browse through it. I don't think I will have enough time for that. So let's see how that works out. In order to understand porous material, and if you think about it in detail, a few things you need to keep it in mind. And if you are now, we had a discussion with the industry and patents and so on. Let me tell you one thing. My experience with the industry is that first thing they will ask if you have invented something, whether the patent is there or not there. First thing they will ask is whether it is inexpensive. I mean, whether they can make money out of it. Period. That's the way it is. You like it, you don't like it. That's the way it is. At least that's what my experience says. Second thing, other things are, of course, some of the properties. First of all, you can make it very quickly or not because they have to go to the production at some point. It has to have a lot of different shapes. For example, if you are working in a polymer industry, it has to have a flexibility and stuff like that. And we work in the porous material, so obviously the expectation is that it has to be porous. So these are the objectives that you need to know when you are making or working in the porous material industry. What are the different porous materials that we are surrounded with? One of them is zeolites that we use in our AquaGuard, Kent purifiers, Surf Excel, and stuff like that. The new ones are the metal organic frameworks where you have a hybrid organic and inorganic counterpart. You can synthesize these materials at ease. And today I'm going to discuss something about the completely brand new organic polymeric structure, that is the covalent organic framework, very distinct kind of material. So what are these materials we are talking about? These materials are very simple. If you take C2 symmetric amine and C3 symmetric aldehyde, if you assemble it, just do a drawing in a piece of paper or chem draw, you will see that they take up these hexagonal structures. And if you stack up these hexagonal structures, once again, these are not materials, nothing has been synthesized, just a drawing in a piece of paper. The drawing itself will tell you that, this has to be porous. That's just, and then eventually you can make these compounds into the lab, and you can see in the slides, very simply, you can make these compounds in the lab and you can precipitate them as a powder. So that is very, very simple objective for this material. So these are called covalent organic framework. Why? Because these are covalent bonded compounds, they are organic in nature, and they make a framework. So covalent organic framework. The way you can do it is that you can take up this piece of paper, as I told you, then you can just draw some of these structures and eventually just use the building blocks, organic building blocks, and go to the lab and make this compound. This has become that simple. Believe me, this has become that simple. This will have a very beautiful organization and you will have a very nice structure, and and you can precipitate them as a crystalline or polycrystalline powder. So many different ways you can make it. I'm going to discuss it in detail in a minute. What are the ways? We are going to stick to the ship-based condensation part today. What are the uses of this covalent organic framework? I'm sure you are already thinking that what would be the use of these materials. Maybe they are good for nothing. But since you are sitting in front of the internet, just type covalent organic framework in Google and you will, I don't have to advertise. You will see hundreds and thousands of hits, literally hundreds and thousands of hits. And different, like drug delivery, membrane separation, energy storage, photoconduction, so on and so forth. But these are all beautiful things, these are all sort of publicity kind of stuff. But in reality, what happens? You want to make a material like that. Of course you do, but please note that they are not school children. You say that you align exactly in this way and so on. They won't. They are organic molecules, or they are just molecules. As soon as you mix them, they will do a very random reaction, and this random reaction will eventually lead to a completely amorphous and non-porous polymer, which is basically good for nothing. So how do we take care of it? How do we counter, and how do we make, avoid this and make that? So how do we do that? So what we do is we use something called a freeze pump thaw, very brutal technique, not at all prescribing to anybody. Don't even try, waste of time. But we used to do it because we had no other way. So where you take a tube, glass tube, where you add a high boiling solvent, and then you add all the ingredients, then you freeze the solution, and then do a freeze pump. And after doing the freeze pump, then you flame seal it, and after doing the flame seal, you heat it, and at 120 degrees centigrade temperature for 7-8 days. Sometimes it will explode because you can see this is completely sealed. So this is a total mess, and even then, if you get some product, so this will be just a few milligram scale after doing these kind of things. Literally putting your life in front of the line. But as a result, this is, even it looks nice. The reason we do it, because we need to counter the amorphous polymeric compound. We need to, give the activation energy so that this crystalline structure pops up and this amorphous compound, goes down. So that was the target. But nobody is going to really like it. Whenever I spoke to industry, no one liked it at all. So that time I visited Tata Steel, and then they said that, they are using these porous materials that they are using, like mesoporous silica and some zeolite materials to filter the water, not the CO2 capture. I'm not going to talk about CO2 capture right now. So filter the water passing through these pipes. If you are thinking what is the dimension of this pipe, please see this truck and you will get an idea. Whenever I see some papers, I see people, in order to prove what is the size of the material, people put a coin or some 1 rupee coin or 2 taka coin, something like that, and show that. So I'm putting a truck next to the pipe, so you can get a size understanding. These goes into these tanks, and then they remove all the junk, especially the chloride and cyanide anion, and pump it back to the blast furnace again. So they said that, can we really use your material? And I'm thinking, if I have to use that milligram scale freeze pump thaw and I have to fill up this tank, our children and our students' children and their children will keep on making coughs, and this pipe will never fill. So what to do? This is not going to be a steady technique for us. But imagine we could have solved this problem. Imagine we could have bypassed this technique. Imagine we could have made it in gram scale. Look at how many different ways you can make covalent organic frameworks, how many different types of synthetic, variability you have. Along with that, I'm sure you guys are synthetic chemists, and many of you are much more expert than what I am, or my group is. So you can choose many ligands, organic ligands, and with these, hundreds of synthesis techniques and hundreds of ligands, literally you can make materials you can think about it. It will be literally, sky will be the limit. So all these beautiful things. So how do we get into this, and how do we make it easily and then bypass this garbage? How do we do that? So that time we thought that, our reaction is become very fast. We are reacting it much faster than we should. As a result, it is going in this pathway. So what exactly is the problem? So if the reaction is going in this pathway, it is not going to help us. We need it to go through this pathway. But because of the speed of the reaction, because as soon as you are mixing the amine and the aldehyde, you are immediately forming these bonds, chip base, and then immediately haphazard structure. So how do we counter it? How do we counter that problem? And we make these with ease. Okay. So what we thought that if in order to stop or at least slow down the reaction between the amine and the aldehyde synthesis, why don't we mix the amine with organic acid first? Why? So acid will protonate the amine. So now the NH2 bond will become NH3 plus. So now when the aldehyde will come into the picture, it first needs to break that NH3 plus, right? It has to have free amine, otherwise how it will form the ship base compound. Okay. So we thought that will probably give us some delay, and eventually that will probably help us to make these crystalline products in bulk scale. So we did that, and this is of course some cartoon, and what we did is that we picked up an organic acid, which is paratoluene sulfonic acid. We react with the amine, then we made a paste, which is basically the salt, and this particular salt just doing the reaction, it starts doing the reaction and eventually starts forming a precipitate. So what we have done here is that we took paratoluene sulfonic acid, paraphenylene diamine, made a salt, added a little bit of the aldehyde. Now the aldehyde cannot react at instance, and the reaction becomes very slow. In order to speed up, we added few drops of water, and then which made a nice flaky pasty kind of material, which we put it into a preheated oven and make this covalent organic frameworks. Done. Absolutely done. No fist pump or nothing. And when we checked the surface area, and I was really surprised. Look at the surface areas, look at the porosity surface areas, 3000 meters square per gram. And when you are using the traditional process, it is about, we could go up to around 2000, maximum. So this has given us an enormous help. You may counter argue that, how did you pick up this paratoluene sulfonic acid? No, it is not. We did trial and error. Of course, we used nitric acid, sulfuric acid. Nothing worked. Everything became charred or something like that. We also use acetic acid. No luck whatsoever. Then we, placed their pKa's, and we figured out these are extremely low pK and these are fairly high pK. So we need a moderate pK. So we chose a few of those compounds which have a moderate pK, and one of them, paratoluene sulfonic acid, worked fairly well, but the acid with a moderate pKa. Then we took and then we went ahead and then did some processing. This is a very simple equipment we use in our home to make, let's say I don't know if you are, I'm sure you have something called semi, and then we cut it and put it into, it's just rice pudding. So we put it into milk and we make beautiful dessert out of it. So we use that, and also some other molds, make some covalent organic framework, lamp and whatnot, and out of it. So that was, absolutely a big success, and we are very, very proud of it. And on top of it, on my colleagues at NCL, they are now using this twin screw extruder. It is basically a fancy equipment of our masala making. So where you have one screw going clockwise, another screw going counterclockwise, where you put your ingredients, let the instrument start, and you make the covalent organic framework out of it. Add a little bit of water so that the flow is constant. As you can see, the powder diffraction is not as beautiful as we have expected. There is some periodicity, but not as long range we have expected. But nitrogen adsorption isotherm shows a decent porosity. If you do a crystalline baking that I told just now, that would be absolutely wonderful. But if you want to make it in batch, these are the values we could get, which is also not bad. These are the chemical stability. In case you thought that I'm bluffing, these materials, 9 normal HCl after 1 week, nothing, no change whatsoever after 7 days. And bicarbonate, dichloromethane, tetrahydrofuran, water, these, that, every other solvent we tried and checked the surface area as well. So at that point, so after these success of this synthesis, we thought that how could we take these materials to the next step? What can we do? And that time I found this literature, it is about graphene oxide, nothing to do with covalent organic framework. So where they took this 2D graphene oxide and then they made different kinds of morphologies, macroscopic morphology. This is a 0-dimensional morphology, this is a 1-dimensional morphology, this is a 2-dimensional morphology, and this is a 3-dimensional morphology. So look at this. So they made many different morphologies, macroscopic, using a 2D material, and each one of them are for different purpose. And we thought that we also have a 2D material. Shouldn't we be able to make some kind of morphology as well? And if we can, they should also showcase different properties and different applications. And in our case, compared to graphene oxide, we do have a better material because here we can do functionalization, which you can't do in graphene oxide. So we thought that let's try it out. So that's what I'm going to prove it in next about 10 minutes or so, where we took two systems, two identical systems, where we took exactly the same aldehyde. This is the benzene fluoroglucinol trialdehyde, and this is the diamine. This is the azodiamine, and we call it phenantridine diamine. We call it DPP, and this is we call azo. So this is azodiamine, same aldehyde. So scenario two, two scenarios. First scenario is that we took all the aldehyde into a dichloromethane solution and amine into water. And so 100 ml dichloromethane, 100 ml water, we threw the amine into the water, dichloromethane into aldehyde into dichloromethane. Then what we did is, we just simply layered it. We just do a very simple layering. This layering is very common in the interfacial polymerization, but what we did over here, we took the aldehyde, we took the amine in water, just made it in a layer, because aldehyde being this dichloromethane being the oil, will not mix with water. So, okay, that is wonderful, that is interesting. That is wonderful and interesting. And as a result, what happens is, it started crystallizing at the interface without any heat or anything whatsoever. I mean, that is something really, really interesting piece of stuff that we found out. So we were absolutely stunned. Not only that, what we found out is that these are not only crystalline, these films, we could lift these films, and these are also porous too. That is something very interesting. Then we monitored it with ACM imaging, and we found out these are about 500 to 600 nanometer to 1 micron thicker films. So that is extremely good. And of course, needless to say, you can cut down the thickness if you want to. I mean, provided you want to use it for some purpose, you can cut down the thickness. Our perspective was to make some self-standing films. So we went ahead around 500 nanometers so half a micron to about 1 micron thickness. While looking at the mechanism of the synthesis, we found out that initially when we mix these aldehyde and the amine at the interface, they start forming some fibrillar geometry. And these fibers eventually form the film, which is interesting. We monitored it, and we found out that yes, indeed, you can monitor it with respect to infrared spectroscopy, powder diffraction, and you see that after certain about 24 hours, the long-range periodicity starts picking up. Okay, good. You can see that you can really make thicker membrane should you wish to. We generally went ahead with around 1 micron membrane and not more than that, sometimes half a micron. And we could place these membranes between two filter papers and then did a very nice molecular sieving using that, absolutely excellent molecular sieving with respect to size fractionation. You can ask why it is showing the molecular size fractionation. As simple as that, because the pores are aligned in that particular way. So that is the reason this molecular size fractionation is happening. Of course, if you do it in a long run, this will start absorbing and there will be seepage. Please note that. But in let's say about 50 to 80 runs, it should be fairly okay. Then we separated a bunch of dyes. These are some of the examples that I'm showing you. This is a rose Bengal dye. We are trying to do something with the arsenic now. Let's see how far that goes. Okay, all right. Now scenario 2. Now in the scenario 2, what we did is the following. Instead of having a layering, and having ingredients in different solvents, we just threw everything in dichloromethane, everything, aldehyde, amine, acid, mild acid, everything in dichloromethane, and put some deionized water in the top. Nothing is there in the deionized water. When we checked it, when we checked what is happening at the interface, we found that instead of forming the fibers, now they have started forming nice spheres out of it. Why is that? Because you can see the significant amount of dilution helps them to form the spheres, and these spheres start assembling and eventually form a film. The same film, previously also we made a film with this interfacial crystallization, but this time it is also interfacial crystallization, but all the ingredients are in dichloromethane. Okay, so it is a sphere to film. Previously it was a fiber to film. You can monitor it with respect to XRD and BET surface area. I'm not going into it. So that's in a nutshell. So you can take a sphere and you can convert it into a film. Previously you used to take a fiber and you were converting into a film. So eventually we monitored with respect to DLS and other studies, and also the morphology monitoring, and we found that indeed they form the films. So there are two ways into looking into it. Let us see. In first case, there it was in acetonitrile, in dichloromethane and water. You form the fiber to film. In second case, everything is dichloromethane, only water, deionized water in the top. You made the sphere to film. Now, this is the same ingredient, by the way, same ingredient, final product being the same. Now what happened is the following. Then we checked the powder diffraction and the BET surface area, and we found that though their starting materials are same and the products are same, but their properties are completely different. So you can see how they have changed the properties, because the morphology modulation or I would say the nanosynthesis is different. So then we checked it a little bit carefully, and obviously, as I told you, that these two materials have different kinds of morphology, and their formation is different. So in order to prove that these two materials have a distinct nature, we just went ahead and did some simple nano indentation with my colleague Mallareddy. Simple nano indentation, just to take a tip and prick it into your film. So the fiber-based films, the tip goes very fast inside. It is unable to resist the tip. Whereas in the sphere-based one, the tip is not going further at all, or much lesser when you push the same load. So this is what you can see. This is the depth and this is the load. On the same load, the fiber-based films, they move much ahead. The depth goes into about 100 nanometer. Whereas on the same load, this is only about 10 nanometer when you have the sphere-based film. Why? Because of the simple packing that I wanted to tell you, that the packing density of the spheres are much better compared to the fiber ones, and that is the reason it resists the indenter movement. So you could understand that's a simple methodology of synthesis of the covalent organic frameworks. Now you can not only make these frameworks of your choice, also you can make some nanomorphologies and eventually synthesize some bulk morphologies for your choice. So I will skip this particular topic. Unfortunately, this is a nice catalysis work we did. I will take about 2 or 3 minutes, which actually I have, to show you a recent work that we have been doing. Once again, same related to the different dimensions, but this time we go to the carbon. So in carbon, we have different allotropes. One is fullerene, carbon nanotube, graphite, and diamond. Now let us look into it. Fullerene being zero-dimensional, there is the organic cages available in the literature, which you can sort of give a resemblance with the fullerene. So fullerene and the organic cage, this is also zero-dimensional in nature. There is no bonding in the X and Y direction. Similarly, the covalent organic frameworks that we talked about, these are called 2D materials. As you can see, they resemble very well with graphite or graphene. Okay. Now the another one is the diamond. You can also make 3-dimensional covalent organic frameworks, and you can make similar diamondoid topologies as well as a 3D structure. So you can do that. You can have a synthetic analog of these kind of allotropes. I'm not saying that they are replacements. No, they are absolutely not. but they are synthetic analogs of these carbon topologies. What about the 1D? We couldn't find any. So what we thought that let us take these same chip-based products, but this time let us have a bent system. And this was our design. And we believe that if we use this tryptophan, this diamine or tetraamine compound, and react with the dialdehyde, it will form this exactly tubular structure. This is our prediction, by the way. This is just the drawing. These are all cartoons. Then what we did is we went ahead and did the reaction, and please take a look at it. I mean, it took us almost 2 years to isolate these compounds, and we could do AFM studies. You can see the height profile also matches. It will have a significant, particular height profile, around 4 to 5 nanometer, and that exactly has happened over here, 4 to 5 nanometer height profile for these tubular materials. We did study with IR and NMR. Please see this aldehyde peak if you want to know what these aldehyde peaks are. There aren't supposed to be any aldehydes, but there is a peak here. So if you want to know, please let me know, then we can discuss during the time. They do very nice intertwining. They form this very nice intertwining, but which is obvious because a straight fiber will not remain. They will try to intertwine as much as they can in order to take care of the voids. They are fairly porous as well, around 200 to 300 meter square per gram, not like the covalent organic framework, but fairly porous. And also, not only that, they've also formed this kind of toroid structures. We are yet to find out why they do it, why these toroid structures form, but they do still form this beautiful toroid structure. We are working on it, still not much idea why they form these toroid structures. So basically, that's one I wanted to discuss with you, that the opportunities that we have in these porous materials. And if you are thinking about a new research problem, I will encourage you to look into it. And you may kindly email me. Whatever help I can provide, I will certainly do so. These are my collaborators, extremely helpful collaborators, and I have learned a lot from them. I have learned more from my students. Kaushik has now joined in Berkeley, and Himadri is in Munster now. So they have left. So I have a very small research group at the moment. All the funding agencies are deeply acknowledged. Sorry, I overshooted by a couple of minutes. Apologies for that. And thank you for the invitation. Thank you, Vipul. Thank you, Dr. Pankaj. And if in future we get an opportunity, I get an opportunity, I will come and try to interact with all of you in great depth. Once again, thank you very much. And if you have any questions, I will be more than happy to answer.
Thank you, sir. If anyone had any questions, they could ask.
Hello, Professor Banerjee. I am Pankaj.
Hello. Thank you for invitation.
Yeah, thank you. It was nice listening to you. I was just sitting here, and hopefully you will be here with us sometime in the future physically.
Yeah.
Because we are working with, on electrocatalysis. We do like oxygen reduction reaction, oxygen evolution reaction, and so on. Mostly electrocatalytic studies with metals or alloys or metal oxides. And we have seen many people have been exploring metal organic frameworks, even the covalent organic frameworks for this type of electrocatalytic studies. So for that, the proton conduction is required, conductivity, because we need the conductivity in the electrocatalyst. So how can you tune this in your field? I mean, in covalent organic frameworks or metal organic frameworks?
These are metal organic frameworks are fairly good in electrocatalysis, but they have a problem of their stability.
Yeah.
So during the process, sometimes they start leaching out. So that is one problem. The covalent organic frameworks don't have that stability problem, but if you see, these structures are fairly insulating in nature. So when you are doing the electrocatalysis and then all the electrons are confined into one environment and they're not moving across the electrode, then you are a little bit stuck, and then your efficiency, Faradic efficiency, current density, power density, everything will compromise. So that is a little bit of challenge. You need to have a little bit of conductivity into this material. Unfortunately, they don't have it. But if we could take care, or if we could think about or design a covalent organic framework where the conductivity is not compromised. Now you can think that inside the pores, they can store a lot of electrons. And that can do a very beautiful job for both electrocatalysis and photocatalysis. Photocatalysis, a good number of people are working on covalent organic frameworks, where you can have electron hole pair generated, where you can use this electron for doing some photocatalytic reaction. You can use the hole for some photocatalytic reaction as well. So this has been approached fairly well in terms of photocatalysis. Electrocatalysis still a little bit. I would say it is a little bit situational at the moment.
Okay. Thank you so much. So we'll have a lot of discussion when you visit personally. We'll have time and we can have something more. And people have just told me that he has to move somewhere because he is faculty coordinator of these 5 departments, science departments. So he will talk to you later on.
Sure, absolutely. Yes. I'm so happy that I got an opportunity to interact with all of you. Thank you.
Hello, sir. Good afternoon.
Good afternoon.
Sir, I wanted to ask about that membrane separation. How covalent organic framework is applicable in the membrane separation process?
Okay, so generally covalent organic frameworks do have these ordered channels, so you can use them as a membrane separation. If you want to have a self-standing membrane, then of course you need a thicker one. And since the long-range order or long-range growth is not very good, so you may have a lot of defects. So which may lead to some kind of seepage of the ingredients. So that might not be a correct way. So in order to go for a membrane separation, you need to have what I believe that you need to have a porous scaffold, which is a very large membrane where the apertures are 5 micron, 10 micron or something, which is very big zeolite scaffold or alumina support or something. And on that, if you could coat, let's say 1 layer, 2 layer or 3 layer or 4 layer covalent organic framework, which you can, then you will have a beautiful flux, and also you will have an extremely good separation coefficient as well. So I would recommend that if you are thinking about a covalent organic framework membrane, grow them on top of a support rather than going for self-standing. When we started, we wanted to make the self-standing, but I believe that the growing them on the support would have a better opportunity for you.
Thank you, sir.
Yeah, welcome.
Professor Rahul, thanks for that nice talk. Actually, I'm interested in one thing. I'm Samuel from NIT Silchar.
Yes.
Regarding this activity, like, have you tried this encapsulation of nanomaterials for catalytic purpose? Like in MOF, it is quite common, but I hardly seen any covalent organic framework. Can that be done?
It can be done, but these nanomaterials will not go in the pore. If you look at the pore sizes are in general around 1 nanometer to 2 nanometers. So your nanomaterials must be of size of 1 nanometer or so in order to smoothly go inside the pore. So most of the nanomaterials that you will deposit on covalent organic framework or encapsulate in covalent organic frameworks, they will not go in. They will all remain on the surface. So that is a tactical problem, because then your surface will be blocked and things will not go into the system. MOFs, you can make larger ones, let's say about 5 nanometer pores, so you can push some nanomaterials inside, but in COF it is a bit tight and bit difficult to counter. So that is a difficult challenge, but these days people are trying to make 6 nanometer, 8 nanometer large COF structures, so hopefully sometime soon.
Basically, they're two-dimensional.
Yes, that is also another problem, because if you are blocking the surface, then you are blocking the pores and eventually you are blocking the entire property.
Okay. Any possibilities forming kind of 3-dimensional such that maybe
Yeah, but only the synthesis is a bit challenging.
Okay, okay.
So that's why people are not much interested into it. Yes, of course, three-dimensional coughs are very well reported in the literature.
Oh, okay, okay. Thank you, thank you. Yeah, yeah.
Thank you, sir, for your presence in our Silver Jubilee celebration.
Thank you.
So now we'll have a break till 1:45 for lunch, and then we'll come back to the seminar hall. Everyone is requested to be present in the seminar hall at 1:45 p.m. Thank you so much.
carbon quantum dots, and they're perfectly stable. And if you compare with TiO2 or commercial TiO2, even after 1,000 cycles, 100 cycles, it is still better than TiO2. So they are highly stable. However, if you do this reaction for say up to 10 cycles, and then you do not do any reaction, you keep it for some time just in the sunlight for about 10 hours or 20 hours, and then you do the 11th cycle, you will see the efficiency goes down. It goes down drastically. And simultaneously, you can also see that the color of the carbon dot solution is slowly fading. So this gave, this inspired us to actually see what is happening in the carbon dot solution. So in fact, we figured out that in presence of sunlight, these carbon dots convert to carbon dioxide, because it has a lot of oxygen anyway, and it has carbon, and this oxygen becomes activated in presence of light, so it converts to CO2. But on the other hand, if some reaction is going on, the reaction is much more facile compared to oxygen itself, so the reaction goes on, the carbon dot is stable. But once the reaction is over, it still develops the ROS, and ROS kills itself. And simultaneously, you can see when you expose it to light, you'll see that the amount of oxygen keeps coming down because it is converting to CO2. At the same now, if you do the same experiment in nitrogen saturated atmosphere or in normal air, you'll see that in nitrogen saturated atmosphere there is no CO2 formation. So this confirms that the oxygen that it harvests from air actually kills itself, and that is fantastic because we do not have to remove the carbon dots from the solution. It can degrade the dyes and it will get removed. It takes about 30 to 40 days. So this is the concept I have already explained. When the reactants are there, it reacts with the reactants. When the reactants are not there, it reacts with itself and converts to CO2. And you can see actually here that if you keep this carbon dot solution for about 40 days, all the carbon dots gets lost. On the other hand, if you keep the same solution in dark, nothing happens. It remains there. So the carbon dots, if you really use them to clean dirty water, you do not have to remove them. It will self-eliminate. So, and finally, I'll show the last concept, that is the hypoxia, which hypoxia means low oxygen in the body at the tissue level. So a very fundamental question is that what happens to reactant concentration on an catalyst surface under light? So we know that the reactant concentration decides the rate of the reaction. On the other hand, we know that what concentrations we are taking in a beaker, but we really do not know what is happening to that concentration exactly at the active site. And I think there are some reports, old reports, theoretical reports, which says that the amount of reactants actually changes under light conditions, but there are no experimental proof, and you will not come across such papers very easily unless you dig in very hard. So this is just, I made it with my hand. I had to write to the editor because the editor rejected our paper. I said that, where did you see such an effect before? And then she agreed to review the paper. So what I said is that, top is the CQD solution and bottom is water. So about 650 micromole, 300 micromole. Now if you put light on this, the amount of oxygen changes from 520 to 640 inside the beaker. And if you put sunlight, now if you put laser torches, for example, your laser pointer of different colors, you can create different amounts of oxygen in different places inside the beaker. This doesn't happen in water, but this happens only if you put some carbon dots. So the effect of light on auto-absorption not known for any material so far, but changes are expected. This is important in case of photocatalytic reactions where O2 gets involved during catalysis, as we have explained. And what we have shown here is that I show schematically that in a CQD, this is in dark and this is in light. You see that the amount of oxygen on the carbon dot is less under light, but it is still very high. It is less compared to dark condition, but it is still very, very high. In dark, about 135 per carbon dot. In light, about 95 to 100 oxygen molecules. So here you can see we have removed all the oxygen first, and then I have put the beaker in light. The bottom line is for light, and the top light is in dark. You see the saturation levels are different. Similarly, we have taken an oxygenated saturated solution and we have exposed to light. Then you see that oxygen level slowly comes down. In about 3 hours, it reaches a saturation level. Now, if you stop the light, it will, if you stop the light, it will go back to the original one. So it will go back to exactly the same place if you keep it for sufficiently long, about 1 day. So here you can see, this is the cycles, light and dark cycles. You can see the same effect, okay? Only thing is that it takes about 12 hours to come back to the original position. And the same effect you do not see in water. So this effect is dependent on the wavelength of light. If you use different wavelength, for example, 400 wavelength, the desorption is more than 455 and then 495. So it is closely matches the EVB's absorption spectra of the carbon dot solutions. So the more the light it absorbs, more is the desorption of oxygen. So I'm not going to explain why, but I can tell you very briefly that when you put light, and this carbon dots becomes either positively charged or negatively charged. And when the positively, for example, if it transfer the electron to oxygen, excited electron to the oxygen, then it becomes positively charged entity. Then it's the molecular levels readjusts, and then it starts repelling the oxygen molecules, and that's why the level of oxygen actually comes down. So I think this is the final slide where I can show that if you put a light, a laser light, you can tell that where the laser light is there, the amount of oxygen is less here. On the other places, the amount of oxygen is more. If you create a pattern of lights inside the beaker using many torch lights or laser pointers, you can create a landscape of oxygen levels inside the beaker. Or if you use different light sources of different wavelengths, so you have an additional handle to create just wonderful gradients within the vessel. And another interesting thing comes if you shine light from top or from the bottom, then also you can create different oxygen levels because it is related to the diffusion of oxygen. So in conclusion, a novel CQD properties derived from waste plastic is that what we have shown. They are oxygen harvesting, oxygen enrichment. We have seen improved oxygen diffusion, and then we have shown the possibility of using ambient air as free oxygen, a spontaneous elimination, we call it autophagy, or hypoxia, or O2 gradient, or O2 landscape formation inside a vessel. And I think these are fantastic properties, and these are properties which cannot be benchmarked because none of these properties are known so far. So we're very excited, and let's see what else we can do. And I think I'm done. And if you have any questions, I'll be happy to answer. Am I audible?
Your voice is gargling. No, still you are not audible. Anyway, Utpal, thank you. So if anybody has any question, please go ahead. And thank you for your very nice piece of work.
Thank you. Thank you.
Okay.
Thank you. Thank you, sir. So moving on, we are very honored to have with us Dr. Babita Barwati ma'am. Dr. Babita Barwati ma'am is an Open Innovation Manager, Unilever Industries Private Limited, India. Dr. Barwati ma'am's jobs involves working with academia, SME and partners to win companies to bring in new technology for Unilever application. She earned her PhD in material science and did her postdoctorate in US EPA as an ORIS research fellow in the field of green and sustainable chemistry, concentrating primarily on nanomaterials. She has more than 30 publications in reputed peer-reviewed She has more than 30 publications in reputed peer-reviewed international journals and 5 patents. With this, I request Dr. Babita Barwati ma'am to inspire us with your talk. Please, ma'am.
Thank you, Gargi. Let me put up my presentation. Can you see my screen?
Now, not visible until now.
Okay. Then probably, wait, cancel. Okay, let me put window then. Okay. Share. Can you see my screen?
Yes.
Yes, ma'am.
Okay. Let me go back. Okay. So hello everyone, and hope you guys are all enjoying the talks. I also enjoyed 2 of the talks and very technical and scientific talk. My talk will not be in a very scientific way, technical talk, but it will be more of addressing an issue that is affecting all of us, and that is environmental sustainability. And I will be talking about the perspective from the industry that I work in, that is the FMCG industry. And don't go into the very technical terms currently. I will be explaining all of those as I go along, right? Environmental sustainability is a need of the hour, and everyone has to do their bit, right? And we all are consumers. We consume things every day. We are like 8 billion people across the globe, and it's hundreds of millions of tons of products that everyone uses every day, right? So it's something that is growing as a concern for all of the people, that how we can reduce the impact through our actions, right? So all these FMCG industries can impact through their actions into this, very positively or negatively, like how we take into the actions. And since all of us are consumers, whether me, you, or everybody, with time we are becoming more and more aware of this sustainability clauses, sustainability agendas. So we talk about plastics, we talk about waste, we talk about sustainable sourcing, right? So I am going to take some examples today from the industry and give an idea how we are working to alleviate the problems related to this. Before that, I'm just giving you a very short brief info about me. I work in Unilever R&D Bangalore and as a senior research scientist as well as ecosystems manager. And beyond my work, I am a ultra distance running and very passionate about physical wellness and lead a lot of initiatives inside and outside the organization. And before I go into the whole problem of sustainable sustainability, sustainable solutions, etc., let me give a very brief introduction specifically to the students who might not be aware of the terms FMCG and what they do and how they impact the environment, etc. So if you look into FMCG, it is defined as the industries that related with the packaged foods, beverages, toiletries, candies, whatever, cosmetics, beauty products, over-the-counter drugs, dry goods, etc. And now you can understand that every one of us, irrespective of your social status or where we are, geographical status, every one of us use at least one of those products every day, right? And I'm going to give you some of the big names in that FMCG industry in my next slide. And you may now recognize some of those. Some questions. Do you know who makes your Maggi or the Nescafe? That is Nestle. And Nestle is the largest FMCG company in the world, followed by very closely with PepsiCo, Unilever, P&G. Unilever is the company that I work, and we make most of your products that you use, whether it is Surf Excel or Reed or your Pepsodent or Close Up or your Pond's or your Lakme or your Kisan or your Cornetto. So you think that if each of these companies, these are like really the top 10 companies or top 12 companies in the FMCG world from the FMCG across the globe. But then there are thousands and thousands of small, medium and smaller companies. Near to our home, we have Dabur, Himalaya, Patanjali, ITC. Every one of us, we use the products from these companies, right? Now, think the scale of the products that are used globally from these companies and the smaller companies, and relate it to the environmental impact. So these companies will need raw materials, right? Our companies need raw materials, which could be surfactants, polymers, various additives, and also the food-related products like vegetables, grains, oils, meat, dairy, sugar. And this accounts for almost hundreds of millions of tons of raw materials. Second comes the production stage. And we produce the products that you use for your cleaning your fabric or household or beauty or personal care or foods or beverages. And in the production scale, the utilization of energy, then choice of materials, everything can impact the environment. Third, and one of the biggest problem is the packaging. So we generally use 4 types of packaging: plastic, glass, paper, and metal. But glass, paper, and metal are not a big issue. The issue comes from the plastic packaging. I'll show you in the next slide what is the scale of plastic packaging that are used from this industry and how it could actually affect, right? And all of this together, contributing to all of this is a supply chain. So we have to source the materials from their source. Then we have to get it to the manufacturing units. From manufacturing units, it goes to the distributor. From the distributor, it goes to the retailers. And from retailers, it goes to the shopper. And during this whole age of online shopping, it is till your doorstep. And every step involves vehicular movement. Every step involves people's movement. And this has the huge impact in our carbon footprint. Let us take an example, just one example I am taking. I am not talking about raw materials, formulations, or supply chain. I'm just talking about packaging because all of us know about the packaging problem that is globally is becoming a huge, huge, huge concern. Here I have put only 7 companies, right? Actually 6 companies, and look at the amount of plastic packaging used by them in 2018 and 19. They are no different in 2020 or 2020 and probably a little bit more, okay? And these 6 companies account for approximately 20% of the whole world's total plastic packaging. And it accounts about 7 million metric tons. Now let us think about all other companies, the big companies, the medium companies, the small companies. There's thousands of FMCG companies globally. And we see the problem there, right? It's probably 80% of the whole total plastic packaging is used by this industry, all of this. And as we know, hardly 14% of this gets recycled. Rest, 86%. Out of this, about 25 to 30% goes to incineration. Still remains about approximately 50%, right? And that goes to either landfill or to water bodies. Now see how big an impact the companies like us are making into contributing to this problem, right? And we cannot sit tight. We cannot sit not acting on it. Yes, plastics gives us everything actually. It is very convenient for us. It is convenient. It has transformed our business, how do we work. But now from this plastic problem alone, leave alone our raw material sourcing, about sustainable sourcing, about deforestation, everything. Then our other footprints and energy and plastic. So all the companies are working tirelessly in a very rapid action manner to alleviate these problems. So in the next slides, I'm going to show some of the examples across the world taken by these companies. In this slide, I have 3 companies, Unilever, P&G, and PepsiCo, right? And if you see the examples that I have taken, they comes from committing to be net zero emissions by 2030, to going to reusable, recyclable, and biodegradable packaging 100% by 2025, 2030, and some of the companies like us, Unilever, who is considered to be the leader along with Nestle in the sustainability sector, we have even promised to go completely out of fossil fuels by 2030. All of these companies, if you go to the next slide also, all of these companies are also taking the goal of sustainably sourcing their raw materials. That means sourcing the raw materials that are not related to deforestation, right? All of these are talking about using 100% renewable energy in their manufacturing unit. All of these are talking about completely recycling and reusing their plastic packaging. So there are like 6 different areas that are coming up that actually is contributing towards this sustainability problem. And these are the solutions that we look into, whether it is sustainable sourcing, as I said, that relates to non-deforestation related sourcing. And we are making this whole thing very transparent to our consumers through blockchain technology, which is coming very, very soon. It will be coming where your product has been sourced. We are actually piloting some of those in some of the first. Consumers are more aware and concerned about the environmental effects. Reuse, reduce, recycle, or biodegradable packaging. Biodegradable packaging is still a challenge because most of us, we sell products that contains water, right? Your liquid detergents or your shampoos or your dishwashers, any of those, or your milks or anything like packaged one. And the packagings are not yet in a scale or in a economically viable state where they are biodegradable and at the same time has the properties of the multi-layered packaging, right? Metal, plastic pad plated with metal that you see in most of our flexible packagings. Then carbon neutrality is another promise and the goal taken up by most of the companies, and I think many of us are at 75% kind of scenario. Then lower dependence on fossil fuel. We are looking into alternate sources of carbon and water stewardship. That means we are also working on innovations that has very, very low impact at the manufacturing level as well as at the consumer level, because most of our products has maximum water impact at the consumer level. Like I sell a shampoo bottle, right? I sell a shampoo bottle and a soap, and which contains hardly 30 to 40% or 50% water in the shampoo or much less in water. Now, when you take bath, you utilize minimum of 20 to 30 liters of water to take bath. And you are using hardly 5 to 10 ml of my product. So the water impact, or take the laundry detergents, right? The powders will have no water in it, but the liquids will still have for 50-60% of water into it. But when you wash that one wash load of water, one wash load of cloth, you are using almost like 50 liters, 40 liters of water. So the water footprint is extremely high at the consumer end. So we are working on innovations which will reduce it. Suppose you needed two rinses to wash your clothes, probably you can end it up with one, saving 10 or 15 liters of water per wash load. So that way we can do a lot into the water segment also to conserve water. I will now go into a very specific examples from my industry that I represent, Unilever. And before going into what we are doing, I'll just give you just a glimpse of what is Unilever and who are we and how we work, right? So Unilever is one of the largest FMCG company in the world, and we have a turnover of more than 50 billion euros with a headquarters in London. And we are across the globe with 190 countries that we have business in. We have more than 400 brands which are prominent. So you know all of those, the Tresemme, your Surf Excel, Reed, Buil, Vim, Domex, all of those, Pond's, Lakme, all of those are brands that we know, Cornetto, Magnum, Kisan. So some of the brands that probably all of you are aware of. We have more than 150,000 employees globally. About 2.5 billion people every day uses our at least one product. And we have more than 5,000 people working in R&D to innovate towards bringing these products. And this innovation for us, since we are in industry, it mostly about patents and publications. So we have more than 20,000 active patents currently that contributes to the creation of these products. Now you see, 2.5 billion people every day uses at least one of our products. So if we can turn around our innovation in such a way that it impacts the people positively and the environment positively, then our contribution towards environment and sustainability will be huge. And we are working into it. We're not speaking about it. We are working on it. So next few slides, I will show you how we are working to attain and reach our goals. So in this slide, I am talking about something called a carbon rainbow. So as I said earlier, Unilever has made a commitment to eliminate fossil fuels from our products by 2030. So in our cleaning products, whether it's a laundry product or whether it's a dishwashing cleaning or a floor cleaning or a toilet cleaning, we use a huge amount of surfactants and polymers. Most of them come from the black carbon source, which is the petroleum-based, right, fossil fuels. And we want to go out of it completely by 2030. And how can we do that? For doing that, we need to tap into other sources of carbon. And we have created a carbon rainbow by defining these different groups of carbon. The first one is the gray carbon, which is from recycling or upcycling of petro-based materials as ingredients. For example, we are trying to create oil from plastics through pyrolysis, then do the purification, and then to convert into surfactants. It will still have some impact in terms of energy, etc. And we are using plastics that has been produced by using the earlier generation produced from fossil fuels, polymers, etc. So we are calling it as a gray carbon. It is not black, but it is gray. The other one is green carbon. So green means bio-based ingredients, whether it's polymer, whether it's surfactant, whether probably some hygiene actives, whether any other, or probably any other actives that comes from either bio or biotech-based routes. Third one is the blue carbon. So we're tapping into the sea-based ingredients. For example, seaweed-based polymers for packaging materials. We are working with many academic as well as industry organizations to build into it. For example, CSM-CRI. They work a lot with seaweed-based polymers, and we are trying to see if we can use some of those technologies in our packaging materials, in our flexibles, etc. Then purple carbon. This is really amazing, right? So what we are trying to do is that capture the carbon from industrial processes and again use it for making some other ingredients. I have given an example here is soda ash that is made in a place called Tuticorin in Tamil Nadu, and we are already using those soda ash in our products. You will see much more examples in my next slides where we are doing those. In my second slide, I am saying, apart from tapping into different carbon sources, we are also looking into other aspects of innovation, like biodegradable or natural ingredients in our formulations. We are compacting, we are actually working on, suppose, concentrated formula, so that you can dilute it at the consumer end, but we have to use really low plastics for packaging, as well as we reduce the supply chain impact into the carbon footprint by transporting a huge amount of material in a lower volume. Similarly, as I said earlier, we are also working to develop formulations in such a way that it reduces both energy and water uses at the consumer scale. We are using a huge amount of recycled plastics into our packaging already, which are called PCR, post-consumer resins. And already a few ingredients which are we got from either green carbon or purple carbon. We are still yet to go into blue carbon and gray carbon because that's little far-fetched research going on in many academic organizations with us. But we have already introduced ingredient based on purple carbon and green carbon in our products. So they are already in the market in different geographies in the world. India also, we have a few coming in a few months, but I cannot tell about it because of some of the confidentiality issues. Next is the plastic initiatives that I said. So I'm taking some of the examples. You can see from foods and refreshment, like from ice creams to mayonnaise to Dove to Persil. Persil is actually Surf Excel in India. And Lifebuoy. All of these brands are taking up into either reducing the amount of plastic we are using or using recycled plastics into the packaging. I think about 25% of our packaging now come from recycled plastics, right? Also, we are talking about refilling. So we are creating some refilling stations. Suppose I sell you a big bottle of 1 liter of Surf Excel. Now, if the refill stations comes to you, you can refill it, or you can go to a nearby store and refill it and keep using it again and again and again till its lifetime. And which is for EZP, LDP kind of thing, it's mostly about 5 to 10 years time. But that way, we are talking about reducing the amount of plastic we use, recycling the plastic, and also working on biodegradable packaging, which will come into market probably in few years' time, because they are yet to meet the standards of the industry for some of the liquid thing. But I think for solid products, it will come in a year or two, very soon. It is the whole industry is pushing this agenda, and it is going to work. My last slide is all about how we work, how we are working to get and reach this these goals. We cannot work alone. I think none of the organizations in the world will have the capability and the expertise to develop these technologies and deliver in such a short time. We are talking about going out of plastics, like reducing, recycling, and biodegradable or compostable packaging by 2025. We're at 2022, another 3 years to go. We are talking about going out of fossil fuel by 2030, 8 years to go. So for this, we need partners who will help us and who will give us the technologies, work with us, understand us, right, and help us deliver. I'm not naming anybody in here because there are some confidentiality issues, as well as there are huge amount of partners, probably thousands of them across the globe, from academia, from small and medium industries, from industry association, etc. In academia, I'll just give you a small examples. In India specifically, I work with a lot of our CSIR labs, IISc, ICT, IITs. We also work with University of Liverpool, University of Sofia, a few universities in South Africa or in Indonesia. So whether they are sponsored research projects or those are through government funding, etc. So we work a lot with academic partners because we need those expertise from academia. We work with some companies we call partners with purpose, which are big companies like BASF, Dow, Firmenich, Givaudan, Galaxy, Surfactants. So all those companies, we call them as partners with purpose because they are also innovating to meet the industry needs and the standards, whether it is from bio-based components or eliminating of fossil fuel. So they are working as per our needs. So we have very active collaborations with those companies either. We are tapping into the SMEs because India is the second largest startup country in the world, right, after USA. Huge number of startups and medium enterprises that has innovative technologies, innovative products. We are tapping into that very closely. Like probably I work with almost more than 100 of those partners. We also work with government and regulatory bodies, right, whether it is BIS or government initiatives like Invest India or Agni, etc. I work very closely with them. Then industry associations like FICCI, etc. We work with them, and a lot of NGOs to create the awareness in our water conservations, in our in educating people about deforestation, etc. A lot more goes into it. And we also work with key opinion formers, which are the industry experts, or probably those people are from organizations like WHO or UNESCO or UNICEF, where they are, or from the NGOs like Oxfam or any of those. Like there are so many we work with. I'm just keeping a few names that is on the top of my head. So those people actually who changes the opinions of the governments or the people, right? And we are working with them to understand better what is the regulations coming up and how we can prepare ourselves into delivering towards those regulations, deliver our products by abiding through those rules and regulations, etc. So that's where the ecosystem comes up, and I work as a very actively to build it in India and UK and some other geographies. And that's where I will stop. I will then open this for questions and answers. Can you go ahead?
So nice talk, Bhavita. We know many new things from you. So just one or two questions. So you are talking about alternative fossil, stopping use of fossil fuel in your in few years. Okay, so what will be the alternative course for that?
Yeah. So what I was talking about, use of fossil fuel based ingredients in our cocktails, whether they are polymers or surfactants, all of those. And that's how I have shown you this whole carbon rainbow, which is the alternative sources of carbon. So we are tapping into biosurfactants or materials that are produced from carbon capture, or materials that are used from the sea-based sources, right? So like blue carbon, we're calling them, green carbon, we're calling the biosurfactants or biotechnology-based materials. Purple carbon, we are talking about this carbon sequestration or carbon capture, and how do you carbon dioxide capture and how do you reutilize them into it. And also the gray carbons, where we are reutilizing plastics to create something more of our used products. So that's where we are doing very fast improvement into this field, because we have only 8 years in our hand to completely eliminate this. And we sell, like you saw, 400 brands and millions of tons of raw materials we require. So we are actively working with academia, small and medium industries, large partners, irrespective of whoever it is.
Okay. So you are talking about also using some S.
Soda ash.
Yes.
We use soda ash in our cleaning products, right? Huge amount of soda ash is used in detergent powders or in our detergent bars. So specifically countries like India, Pakistan, Bangladesh, and South Asia and Southeast Asia, liquid formulations still are not very prominent. It is more of still powder and bars. Huge population, extremely large amount of utilization, and it actually has a very, very big impact.
Okay. Thank you. So the last one, suppose I want to collaborate with your company.
Yes.
Somehow. So how that can be initiated?
Yeah. So I told you, we work very closely with academia, right? So we look into the research groups that has research that is important to us, related to our products, and we see that there is a potential of it. So we have 3-4 models of working with the professors, whether it's a sponsored research project, where we sponsor the project for a PhD student or a postdoc student, whether it is 1 year tenure or 2 year tenure or 3 year tenure. Then we also work in a consultancy-based model, where we utilize the professors in different organizations, or the scientists in different organizations for us. We also have a third model where we co-fund along with government, right? That's because many funds in DST or SCRP, etc., where industry can pitch in 50%, the government gives 50%, and that's called industry academia collaborations. So we also work through that model. So there are 3-4 different models. We are also now working for the PM fellowship, where we are actually sponsoring students for the PM fellowship. We already have one with IISc. We are working one with IIT Madras.
Okay, thank you. Voice is not coming. No, still not. No.
I cannot hear anyone. Yeah.
Can you hear me now?
Yes.
Is it okay?
Yeah.
Okay. First of all, thank you so much, Bobita, for your thought-provoking lecture. And definitely, I think our students, we have a lot of students, you can see, no, in the auditorium. In our seminar hall, you can see the camera. You can zoom.
Yeah, I can see. I can see.
And Sandeep is also sitting. Kusum is sitting. Okay. Anyway, it is very good interaction. And could you please tell us that how our student can join Unilever? What is the way?
Okay. So, hello everyone, the students. So I will talk not only about Unilever, but the whole FMCG. India has R&D of most of the big FMCG industries, right? Whether it is Unilever or Reckitt Benckiser. So Unilever R&D is in Bangalore and Mumbai. For Reckitt Benckiser, it is in Delhi. For Colgate Palmolive, for P&G, etc., they have in Mumbai. Reliance is operating in Bangalore. Shell has a R&D in Bangalore. So all these companies, there are huge number of companies that are there in these cities. For specific to Unilever, I'll tell you how to join. We hire people in a few specific categories: from chemistry, from polymer sciences, from chemical engineering, BTech, MTech. Then we or PhD. Same with MSc polymer chemistry or chemistry in BTech, like MSc or PhDs, or people. Very few positions comes in the physics, but more into packaging people. Then people from foods background, and people from nutrition background, people from digital, right, electronics, digital background, who has their expertise in digital modeling and etc. All of these background people we hire in different work levels, whether it's at the fresher level or experienced level and the managerial level and director level. So different things we hire. And we also have another one where you can work with us during your masters, right? We have 6 months internship program where we pay the students to work for us in our site, where you can work with us in an industry relevant project and get the exposure how industries work, etc. But it does not come with a guarantee for job. But most of the time, we actually hire the students if they are good, and we have openings, so we kind of hire that way. So that is one way. We generally take up trainees during their last semester or the semester before, but it is a 5 to 6 months of training program. But other than that, if you want to join as an employee, there are a lot of scopes. You can look at LinkedIn, we advertise there, or you can connect me or any other. So for R&D, so we have people in Bangalore and Mumbai, and as I said, we hire from various backgrounds, from chemistry, polymer chemistry. Chemistry means we say inorganic chemistry and physical chemistry mostly. Organic chemistry are less, but polymer chemistry is there, more of that. Then we look into chemical engineering, BTech and MTech. We also hire from people foods background, foods and nutrition background. So yes, that's where we mostly hire people, both in the freshers, and we pay really well. Okay, our company pays really well. As the industry standard, if you take, we are at the top 25%. If you take 100% is paid by somebody, we are at the top 20%. So we pay more than 80% as per the industry norms in India. Industry norms means FMCG. I'm not talking about pharmaceuticals and all. It's FMCG industry.
Okay, thank you so much. I hope sometime you will visit us and recruit some of our alumni.
Yeah, I would love to. I actually see very less people coming up. I don't see anybody except me and another girl called Maitri, who actually studied in Bangalore University. There's nobody Assamese in our whole R&D center, and we are about 70 PhDs and 350 other people. And I would love to see some of our people coming in, and also request you guys who are the professors to create a curriculum where the students can come and work in industry as a trainee. Like we take trainees from most of the academic organizations, BITS Pilani, different ISAR, Kolkata University, or from VIT, or from JSS College.
In this regard, Bobita has lost the link, I think.
Yeah, it might be.
Yes. In this regard, Bobita, is there any duration, minimum duration for it should be minimum 6 years, or we can send them for 2 months or 3 months?
We do not take 2 months because it is not useful for the student as well as us, because we give them a very meaty problem to work, which is very closely related to our day-to-day projects, which will go to, it's a scientific part of the work, but it will probably, they will end up having a patent, or they may end up having a publication. We give less publications, but more patents. So very active working, 2 months. By the time they understand our safety protocols, they understand the project, it is time to go back.
So that means minimum 6 months.
5 to 6 months. We'll be preferring 5 to 6 months. And we take students from, as I said, BITS, Palani, all the campuses, either Pune, either Kolkata. Either Kolkata comes from 9 months. Then we take students from VIT, we take from SSG College, Mumbai, UD City, a lot more leading organizations. Yep. We also nowadays, sorry?
No, please go ahead.
Yeah, we also nowadays are working, as I said, sponsored research projects. We work a lot with all of these industries, organizations, academic organizations, where we are started to sponsor postdocs. Yesterday, I put in Assam Northeast thing that there is a postdoc position at ICT with a Professor Prakash Mahanwar, which is sponsored by us. We are sponsoring the students as a postdoc with him, and he's advertising for it in the polymer chemistry. And the payment is around 70,000 per month, which is the standard as per the norms. So yeah.
Okay, thank you, Bobita, for this information. So with this, we will proceed for the next session, but we hope that Bobita will visit us when she comes to her home.
I'm definitely.
I can talk with our students directly so that they can motivate them to join you.
Yeah, definitely. I'll be happy to see more and more faces coming, because very less representation from Northeast India in industry. Very, very low representation. So I think we need more people in this.
Okay.
Thank you so much, Bobita. And Dr. Bora, are you please go ahead with oral presentation?
Sure.
Bye-bye.
Bye.
So we'll resume the online presentation now. I think Partho is ready. So Partho Jyoti Das, please go ahead with your presentation.
Yes, sir. Can you see my screen?
Yes. So you will have 10 minutes, 7 minutes for presentation, and around 2-3 minutes for discussion.
Okay. Good evening, everyone, from cold and freezing Chicago, 7,000 miles away from you guys. Thank you, Utpal sir, for giving me this chance to talk something about my research in my home state. So my name is Partha. I am now a postdoc right now in a Northwestern University and working on supramolecular chemistry with Professor Stoddard. Today I'm going to discuss, or probably I would say that I would like to touch the bio part of this conference theme. So I'll talk about the application of fluorescence that you get from small and supramolecular structure. So in my PhD, when I started in 2015 in Israel, I started exploring a small fluorescent molecule called SynBiomen, which is an Israeli invention from 1979. But there was not much application was done in that period. We tried to explore the biological aspect of that molecule because of its very high quantum yield. If I remember well, the quantum yield is 1, it's 100%. So the molecule that you see was actually where the SynBiomen molecule was linked with an AIB transport unit with the cysteine, and that was injected in the tail of a mouse. And when it was looked under the microscope, it was found that in his brain, the molecule actually can penetrate through its blood-brain barrier. So you need a dye to identify the fluorescence to identify the molecule inside the body. So during that process, we started looking very carefully about the molecule. So we were the first group where we studied the molecule in order to find it as a ligand for metal abstraction. So the first complex that we got with the synbiome and fluorescent ligand was with palladium. And during the course, we also got other complexes with sodium, where we found that the fluorescence is quenched with this heavy metal atom effect. It was not very easy for us to proceed with this chemistry back then, because the synthesis was, even though it looks very simple, it was not like that, because of a very involvement of a toxic step, because it involved a chlorination step, which is very toxic for human bodies. So back then in 2018, together with my colleagues from IIT Kanpur, and we developed the alternate synthesis for chlorination in this pyrazolone ring. So the chlorination was done by this molecule with by mechanochemistry, and as well as in solution also you were able to get in the same yield and as a precursor to make our synbiome molecule. Once we established a new procedure, we thought of exploring the metal abstraction chemistry with this ligand. So we changed the oxygens by sulfurs by using Lawson's reagent, and also by P4 estanes, another thionation reagent we have. So currently this work has been almost submitted to a journal, where we actually used these thionated ligands to make metal complexes with coinage metals, in order to show that it can be useful for the abstraction of this copper, silver, and gold. So in my PhD, it was mostly focused on fluorescent molecules, which are small fluorescent molecules. Back in 2019, I moved to Professor Fraser Stoddard group. Probably most of you know him because he got a Nobel Prize in 2016, and his early invention of, in 1983, the blue box. Now, the blue box, the name itself doesn't come because it is fluorescent. The molecule is not fluorescent. However, Fraser termed the box in a sense that the electron deficient sites, he termed it as a blue site. So that's why it was termed as blue box. However, that was just the beginning of a new era of chemistry, what he called as a mechanical bond. So today, the synthesis papers that you see on rotaxanes and catenanes, where you see the interlock molecules, it was all started in 1983, and together with a process of nano car, mechanical motors, mechanical pumps, and all these inventions led them to a Nobel Prize in 2016, together with Ben Feringa and Jean-Pierre Sauvage from France. In Fraser's group, we were very limited to do biology because of our main focus on material chemistry as well as mechanical bond. In 2018, however, the blue box, or you can say the extended blue box, were further modified by introducing a fluorescent molecule called thiazolothiazole, which yield a 100% quantum yield. So that was used for bioimaging purpose, for cell imaging purpose. If you want to study more about Fraser's work as a history in his and his contribution in mechanical bond, you should definitely go for our recent review that is published in CCS Chemistry. So I'm not going to talk about today about his research on mechanical bond or pumps. So I'll touch on some of the cages or molecular boxes that we recently discovered and use it for application purpose. So a case molecule that has been synthesized in our lab. So I have not shown the synthesis point here because it's I think there are better synthesis chemists in this room right now who can tell us more about it. But my aspect is to show you what we can do with the application of supramolecular chemistry, because that was also a Nobel Prize winning topic back in 1986 when Jean-Marie Land from France got his Nobel Prize. When we developed a hydrophilic cage molecule, our concern is what to do with that. So we decided to get a very small molecule which can be used as a anti-cancer drug. So 5-fluorouracil is used as a prodrug actually in skin cancer. So our initial thought was to encapsulate the drug inside the molecular cavity and release it in the solution. However, to release it, there should be an interaction or repulsion between the gas molecule as well as the host molecule. However, our gas molecule in this situation is so small that it binds very well and it does not come out because there is no repulsion between the molecules and the host molecule. It was confirmed by NMR titration that you can see that when we studied when we observed the shift in peaks in proton NMR, we saw that the binding constant of this gas molecule inside the supramolecular cavity is around 10 to the 4. But we were not able to do any cell imaging because we were not able to get out or not able to release the drugs out of the system. So our focus then turned into another aspects of using photosensitizer. So some of you, if you have focused on Professor Utpal Gautam's talk today, so he talked about using singlet oxygen generation. Now, the reason we use this photosensitizer, which is diphenyl porphyrin, or you can also use porphyrin. So these are actually photosensitizers. So these can absorb light and it can generate singlet oxygen and it can actually kill your cancer cells. So that's the application that we had in our mind. But our first focus is to find whether the molecule can be introduced inside the cavity of this cage. So we did NMR titration, and from the curve that you see, we found a very nice NMR shifts, and from the binding curve, we were able to get at around 10 to the 4 binding constant inside the molecule, inside the cage molecule. So now you're successful in getting it in chemistry lab, but let's go to the biology lab and see whether we can see whether the cells are viable in that solution or not. So the Q3 that I'm referring now is just the horseshoe that we say is just the precursor of the case, and the Q4 is the actual case that we are using. So when we treated the cells, so these are breast cancer cells that we treated here in our lab. So when we treated these molecules in water solution, so we used the chloride salt so that we can dissolve it in water, and we treated this with breast cancer cell. And during the time when we studied it, we saw that the case can be actually visualized under the microscope. Now, this is because you know that our cases are actually cationic cases since we are using the chloride salts. However, cells are anionic, so it can actually allow you to sit in a surface. The other picture that you see that here we are actually using some dyes just to generate the fluorescence a little better for imaging purpose. So the blue one we use something called lysotracer blue, and the other one is lysotracer green. And when we see its composite pictures in cell imaging confocal microscopy, we saw that these can be detected very well. But our main aim is not to just to encapsulate it and and see the microscopic images. As a biological aspect of this paper or of this work, we wanted to see whether we can release the drug molecule into the solution, or our main goal or our long-term goal is that whether we can encapsulate the drug, or after that we can actually release the drug in the body, right? Now, in order to do that, we were very successful in getting it because we are having a photosensitizer. So photosensitizer can actually accept electron energy or light energy. So the first graph that you see is the cell viability experiment with only the cage molecule. And then when you treat it with the cells, you see the cells are not toxic. So if you see the higher cell viability, that means the cells are not toxic. However, when I irradiated the light for 10 minutes, we saw that the cells become toxic. So it means that cells are getting killed. This is because of the porphyrin molecule will actually absorb light from the source of light that we use, and it generates singlet oxygen. So the singlet oxygen kills the cancer cells. And these other graphs shows you at different concentration how much singlet oxygen you can generate. However, as a chemist, it is our main, I mean, I feel pain if I do not do the same, if I cannot prove it as a chemist other than doing the biology. So I have a very simple experiment everybody does, like fluorescence, right? So what we did that, first of all, we took the complex molecule, that means the case, as well as the gas molecule inside it, and we saw the fluorescence of it. We couldn't find a fluorescent there. This molecule, this yellow graph, you see that there is no fluorescence. However, when I maintain the pH at 4.5, what happened? It becomes there. It poses some interaction between the cages and the porphyrin molecule, because the porphyrin nitrogen gets protonated, so it gets repulsion between the supramolecular case and it gets released. The moment it gets released, so you see now here in the picture, your no fluorescent compounds become slightly fluorescent. What it suggests you that you can actually release the drug. You can also encapsulate the drug, and you can also release the drug. In order to do that, we did the same. We have to replicate the same system in the biology, even though these are not in vivo study, I would say, but these are done in actual cancer cells. So when we use the complex, if you see carefully, we saw the cyan image and red image is very clearly. This is because of the fluorescent image of fluorescent image of the drugs at lysosomes. What happened is that in our body, in cells, the lysosome pH is around 4 and 5. So this correlates to the theory that I proved in the fluorescent experiment. So in the fluorescent experiment, when I use pH 4.5, I can see the fluorescence. So that same happened in the lysosome cells. So at that pH range, it actually released the porphyrin ring, and that is the reason why you see the red image and the yellow image. So this wavelength is also exists for the porphyrin. So that now we can actually say that the imaging of red and cyan actually coming from the released porphyrin drug from the supramolecular system. So I hope I was able to tell you a little about how I moved my career from small fluorescent molecule to supramolecular drugs, supramolecular systems, and now we are able to encapsulate drug molecules, both small as well as big drug molecules like porphyrins. And since at pH 4.5 in vitro, we were able to study or we were able to convince you that the drug can be released, as well as in the cells the drug can be released, and it can be visualized by the fluorescent microscopy images. And this happened because of the singlet oxygenation, because we are using a photosensitizer, DPP, diphenyl porphyrin molecule. So this cage or the supramolecular host system, nowadays supramolecular systems are also closed fluorescent molecular containers. It also gives us in future for studying catalysis because of its cavity. So at last, I would just like to thank my my supervisor here at Northwestern, Fraser, and this is our group, quite a big group at Northwestern that we have been working with. And thanks for Northwestern for funding, as well as Tezpur University and all the colleagues there for allowing me and listening my talk. Yeah, so if you have any questions, just let me know. Thank you.
Thank you, Mr. Das, for this very interesting and illuminating lecture. So indeed, it's a very different whatever we have heard so far. So it's a combination of both chemistry and biology, the applications in biology. So the point that the drug is, I mean, the porphyrin is released, so it's a pH dependent, right?
Yeah, it's a pH dependent. So it's a very simple, BSc chemistry, I guess. So once you protonate this, so the nitrogen will get protonated at high pH. So because of the repulsion between the, the gas molecule and host molecule, it gets released from the system. The energy will be very high.
So that means we can take it orally.
We did, as a chemist, I do not claim that, because we did not do it in vivo. But yes, our main aim in the paper, we will actually try to write in that angle. Yeah, I agree with you. But as a chemist, I do not claim
Yeah,
that.
yeah, because you have to do a lot more experiments. But going by the pH dependence, which is a high pH is required, so stomach provides that high pH. So that from that point, actually, I am telling you.
Yeah.
Yes, very good and interesting piece of work. So, any other questions from audiences?
Hello, this is Dr. Shashwati Adhikari. So I had one just clarification. So as Professor has asked that it can be consumed orally or not. So as far as I know, that photodynamic therapy or photothermal therapy, this cannot be taken orally. It can be injected in locally. So it is not taken by orally.
Yeah,
It is not a oral. It is not a oral drug.
Yeah, it's not an oral drug.
So that molecule can be designed in that basis that can goes the selective cancer target cells only, leaving the normal cells unaffected. And at after localization in the cancering site, just a particular wavelength of light can be incident in that area, and for that cancer cells will die. That is called like photodynamic or photothermal therapy.
Yes.
Yeah, you are right. But at the same time, the pH dependent is also there. In order to release the porphyrin from this supramolecular complex.
You are asking me? Sorry?
No, you were right.
Yeah, I totally agree with that. So this is more into photodynamic therapy. So I did not talk about in that angle. So I have more results on that area.
That is understood because you have already explained how this porphyrin is released, because it's in the presence of your this light, and at the same time the generation of singlet oxygen.
Yes.
So that's a driving force for release of porphyrin.
Yeah.
Yes, very good. Thank you.
Okay, thank you, Partha. So now we have one more colleague in US. They are just in the very late morning, late night, maybe in 4 o'clock, 5 o'clock, I think. So Sunny Nandi, I request Sunny Nandi to proceed. Then we will come back to Assam, and all our colleagues from Assam will present accordingly.
Thank you, sir, for giving me an opportunity. It's quite late, but I could not stop myself to give a presentation here. So I'm just sharing my slide.
Okay, please go ahead. So you will have total 10 minutes, and you complete by 7 to 8 minutes and 2 minutes for discussion. Okay.
Okay, sure, sir. Is my slide visible?
Yes.
Okay. So the title of my talk is Towards a Low-Cost Rechargeable Aqueous Aluminum Metal Battery. My name is Sunny Nandi. I'm a PhD student at the Department of Physics, Tezpur University. Currently, I'm doing a part of my research objective at the University of California, Los Angeles under the Fulbright Fellowship. So these are the outline of my presentation. So as we know, there are different types of renewable energy sources around us, starting from wind, geothermal, and hydrothermal, but the main objective of such type of renewable energy sources is to generate electricity, right? So you can imagine if there is no electricity in our life, we will go back to the pre-medieval period. But to install such type of renewable energy sources, we need a very large geographical area, which is not cost effective. So an alternative way to store energy is to use a battery. So if you see in today's area, like most of the devices come with lithium-ion battery. And lithium-ion battery was awarded the Nobel Prize in 2019. So it consists of anode and the cathode, and we have an electrolyte. Usually it happens if you see the working principle of a lithium-ion battery in your mobile phone. So when we are charging the mobile phone, we are actually trying the lithium ions to migrate from the cathode to the anode, and that's how the battery is full. But as you plug it out, it goes to discharge. That means the ions start moving from the anode to the cathode. And the Nobel laureate, good enough, he mentioned in his paper that there is a lot of disadvantage in lithium-ion battery. Lithium is very expensive, and we cannot assemble this device in an open environment. And even the liquid that is used, it is quite flammable. And a lot of people are working on to improve the lifetime of a lithium-ion battery. So we can compare the lifetime of a lithium-ion battery as a human being, right? When we are very young, we can do a lot of tasks, but when we become old, we could not complete the task at a single time. Now, so my area is based on aluminum-ion battery, and the reason why I choose aluminum is that it is the third most abundant element in the earth crust, and it is very cheap. Also, I work on aqueous electrolyte. It is a water-based solution, so we don't need an external environment to assemble such device. We can do in our own lab, so it is non-flammable and it is easy to handle. And if you compare the gravimetric energy density with lithium and aluminum turned out to be much better. So as a preliminary investigation, I have carried out my work using aluminum foil, and you have seen this type of foil in your lab or maybe in restaurant. So I initially took aluminum as an anode and graphite as a cathode. And I do the charge discharge experiment, as you have seen in figure C and figure D. What I mean by charge discharge experiment is that to see how much performance you can get in terms of this battery. And we have seen that what we assemble, the battery is very low. So in order to improve the performance, our hypothesis was how to improve the performance. So we come up with an idea, and it is well known that exfoliation of graphite has been seen in various ways. So we use electrochemical exfoliation, where we use aluminum chloride as the electrolyte, aluminum foil as an anode, and graphite as a cathode, and we apply a voltage of 4 volt for 5 minutes. You may be thinking that why do I apply a voltage of 4 volt and why I choose 5 minutes? I will come to this question. Now, when we exfoliate this graphite with aluminum foil for 5 minutes, we have seen there is an increase in the capacity, as you have seen in figure A. In our previous slide, the capacity was 8, but as we exfoliate the graphite with aluminum foil, we could get a capacity of around 20 milliampere hour per gram at 100 cycle. And this is the cycling stability for 100 cycle, and this is the CV. The CV shows that the voltage we have achieved is 1.8 volt, and it clearly matches with the voltage plateau in figure A. However, the capacity is very low. Is there any way to improve the performance? We come up with an idea is that we exfoliate the graphite with copper, and then we could improve the capacity. As we have seen here, the question arises that how could we improve the capacity when we exfoliate the graphite with copper? So we did the EIS experiment. It is the electrochemical impedance spectroscopy, which clearly tell you that what is the charge transfer resistance between the electrode and the electrolyte. So we have seen that when we exfoliate the graphite with copper, the charge transfer resistance is very low, and there is a way like more aluminiums can be accommodated, and that is the reason why the capacity was we can achieve a capacity of around 50. Now, it is the SEM and TM images, and we have seen that when we exfoliate the graphite with copper, the thickness is 1.74, and when we exfoliate the graphite with aluminum, the thickness is around 0.74. It actually tells you about that when we increase the surface area of graphite with copper, more aluminiums can intercalate inside the graphite layers, and that is one of the reasons why we could achieve a capacity of around 50. The question that I asked before is that we actually choose different voltage like 1 volt and 2.5 volt, but we haven't seen any change in the performance. Also, we choose 5 minutes because there is no, when we choose a different time duration, we have seen there is no change in the capacity. So as for our convenant, we have choose 5 minutes, and we have performed the rest of the experiment. Interestingly, after several cycles, the aluminum foil got corroded. And if you see the SEM images, the graphite SEM, the morphology of graphite still remained the same. So we come up with an idea that how to improve the cycling stability. So what we do is that we remove the aluminum foil after it got corroded. So we replace the aluminum foil with a fresh aluminum foil. So we could run for 3 cells. Usually, you have seen in your home, the lead acid batteries, we always change the electrolyte. With that concept, we change the aluminum foil after several cycles. And a part of this work was published in SES Sustainable Chemistry and Engineering. Now the question arises that how to explain the mechanism, since from a chemistry, since this presentation, this conference is on chemistry more or less. So to understand the mechanism, after several cycles, we took the graphite sheet, we inhale at a higher temperature, and it is well known that if aluminum is oxidized, it forms to aluminum oxide. So we collect this white powder, and we did the XRD. The XRD matches with the JCPDOs of aluminum oxide. Now the question arises that is it the only aluminum that is participating inside the electrolyte, means inside the graphite? So we have done XPS, and we have seen the aluminum peak after the 5th discharge. But interestingly, when we do the XC2-XRD, this XC2-XRD matches very well with the work reported by Professor Dai from Stanford University. They have used aluminum chloride based on non-aqueous electrolyte. So during discharging, we haven't seen any change in the peak. However, during charging, we have seen the 002 peak split into 2 ways. So it actually signifies that it's not only aluminum that is actually participating inside the intercalating and deintercalating. There are like presence of anions. Since we use aluminum chloride, the only anion that is present in our electrolyte is chlorine. So we come up with the hypothesis, with the mechanism is that during discharging, aluminum is actually coming out and going to the graphite, but during charging, it does not goes to the aluminum foil, and that is the reason why the aluminum foil got corroded due to the presence of chlorine. And we could also make a prototype in our lab. This is TU. TU stands for Tezpur University. And the selling point of this work is that we have used aluminum chloride. It is very cheap compared to the non-aqueous electrolyte that has been reported so far. Also, since the theme of this conference was about clean energy, so we have made this device in our lab, and it is very safe. And this work is a part of now MSc people are doing on this work. Also, we could make a prototype, and this work actually gives a platform for future studies in aqueous aluminum metal battery. So overall, it is about cost effective, its safety, application, and inspiration. And recently, we could improve the performance. What we do is that we took the graphite, accelerated graphite, we heat it at a higher temperature, and then we increase the graphite layers. So you have seen that in our previous study, the capacity was 40, and we could improve the capacity by using this thermally accelerated graphite. This is the SEM images, and this is the EIS, which actually told about the charge transfer resistance between the electrode and the electrolyte. So the aluminum graphite, when we accelerated with TEG, we have seen a higher capacity. And this is the beautiful image of our campus right now at UCLA. Thank you. If there is any question, I will be happy to take it.
Thank you, Mr. Nandi.
Thank you.
So can you repeat what was your best result?
Sir, for the first time, we have reported that graphite has the possibility to intercalate aluminum, although we have also seen the presence of chlorine. So we have reported that aluminum and chlorine both can go inside the graphite layers. And there has been well reported that graphite has the possibility to intercalate larger anions. So the anion that is present in our graphite, in our electrolyte, was chlorine.
No, if you compare with this lithium battery.
Yes, sir.
So where do you see? Where do you stand?
Actually, sir, it's a very nice question. Now, if you have seen in most of our electronic devices, we use lithium-ion battery, and we cannot compete with lithium-ion battery. But there are a lot of researchers still working on to find an alternative to lithium-ion battery. And John Goodenough, he has mentioned already in one of his paper, like if you go to a market and if you see a price of Apple costs 250 and a price of Apple costs 150, we always try to go to the lower price. And for sustainable, if you see, although if we can give a hand to lithium-ion battery, so aluminum-ion battery will be acting as an alternative to lithium-ion battery. And if I remember, the company in Australia, this graphene manufacturing company, they are going to launch a car which is made of aluminum graphene battery. So the car will be running with aluminum graphene battery. So I think in future, aluminum will be acting as an alternative to lithium-ion battery.
Hopefully. So this will also change the world economy, which is say lithium-ion battery centric.
Yes, sir. I'm also working on recycling of lithium-ion battery. That is one of the most important topic right now. And I'm working with Professor Yuzhang Li. I am working on two projects. One is on recycling, and I'm working on aluminum, to improve the capacity.
All the best.
Hello,
Thank you, sir.
Hello, sir. I wanted to ask one question.
Yeah, sure.
Sir, if you're talking about the lifespan, if you compare lithium-ion batteries, there are different kinds. And if you're talking about aluminum-ion batteries, then which would have a better lifespan if we speak about that?
Okay, it's a very nice question, Shweta, I think. Yeah. So the lifetime of a lithium-ion battery is that if you see the future of lithium-ion battery will be a solid-state battery. But the present lithium-ion battery, there is a dendrite formation, right? So you have seen or you have heard about the news where the battery gets fired. Now, if you talk about in case of aluminum-ion battery, the cycling stability, and if you see the volumetric energy density of aluminum, it is 7 times higher than lithium. The only problem right now in aluminum-ion battery is that it carries a charge of 3. If you see the lithium, it can transfer 1, electron per cation, but in aluminum it can transfer 3. So we need a cathode material that can capture these 3 electrons. So far the cathode material that we have seen, like I work on graphite and transition metal oxide, I haven't could improve the cycling stability, which is about the cycle life. But a lot of work is still going on, and one of the objective that is the question that you asked me, I'm trying to improve the cycling stability and the cycle life. So far, I could run around 25,000 cycles, but the capacity I could not control it. So I'm still trying an alternative to improve the capacity. But you can run a lot of cycles number if you use non-aqueous electrolyte, that is non-aqueous aluminum electrolyte, and it is very expensive, and we need a glove box to fabricate such type of device. So I think if you talk about the sustainability and clean energy, I think it will be a good way if we use water solution rather than using ionic liquid, if you wanted to increase the economy of our country. I think I answered your question. I'm not sure.
Yes, sir. Yeah. Thank you so much.
Okay, welcome. Thank you.
Okay, thank you, Sunny. We will now go to the next presentation. Dr. R. Kishore, are you present here? So I think he is not present. Now I request Pranoy Sharma.
Good evening, sir.
Oh yes, please go ahead with your presentation. You will have 7 minutes for presentation and 3 minutes for discussion. Okay, please go ahead.
Okay, sir. Is my slides visible?
Yes, visible.
Okay. So I am Pranoy Sharma. I am a research scholar in the Department of Chemistry, Cotton University. Today I am going to discuss about structural topologies involving unconventional nitrile-based synthons in coordination compounds, their experimental and theoretical studies. So the design and synthesis of coordination compounds with desired structural topologies in crystal engineering have received so much emphasis in recent times because of their wide potential applications in wide range of field. In this context, the selection of suitable organic moieties as ligands have played the decisive role in developing the coordination compounds. Organic moieties with nitrile group has emerged as potential ligands to develop various coordination compounds with various dimensionalities. The supramolecular interactions involving the nitrile group are of particular interest because they can exhibit local dipole moment. And as a polar functional group, it can also engage in dipole-dipole interactions and also can serve as an hydrogen bond acceptor. Among them, one such interaction is nitrile-nitrile interaction, which can be of 3 types: antiparallel, parallel, and T-shaped nitrile-nitrile interactions. So the presence of such interactions in coordination compounds can be confirmed by using various computational studies, such as density functional theory, which is a computational quantum modeling method used to investigate the total energy of an overall system. Similarly, molecular electrostatic potential, it helps us to understand the electron-rich and electron-poor region of a molecule, and it also allows us to compute the map values in each region of a molecule. Non-covalent index analysis is also a computational tool which gives us the qualitative mapping of non-covalent interaction zone in real space. The presence of green isosurface between these 2 aromatic rings indicates that the presence of attractive pi-stacking interaction between them. Similarly, QTIM analysis also allows us to justify the presence of covalent bonds and non-covalent interactions by the presence of various critical points such as bond critical point, ring critical points, and case critical points. So in our study, to visualize the interplay of non-covalent interactions in nitrile group, we have synthesized 3 coordination compounds involving cyanopyridine ligands. For the first compound, we have used manganese chloride salt, oxalic acid, and 4-cyanopyridine in room temperature in water medium. And we have obtained a manganese 3 coordination polymer. It is interesting to see that this 4-cyanopyridine ligand is basic enough to oxidize this manganese 2 metal salt to manganese 3 in this coordination polymer. Similarly, for compound 2 and compound 3, we have used manganese sulfate and zinc chloride metal salts with 4-cyanopyridine and 3-cyanopyridine ligands, and we have obtained compound 2 and 3. All the compounds are soluble in water and common organic solvents. This is the crystal structure of the first compound, where its manganese 3 center is hexa-coordinated with 3 bridging oxygen atoms of the oxalate moiety, 2 chlorido ligand, and 1 water molecule. Moreover, 2 cyanopyridine ligands are also present in the crystal lattice. Now, to investigate the presence of manganese 3 center, we have carried out X-ray photoelectron spectroscopy of the compound, and the peaks in 642 and 655.4 electron volt indicates the presence of 2p 3x2 and 2p half levels of manganese 2p orbital, indicating the presence of manganese 3 center. And the intensity ratio of 2:1 also suggests the presence of 4 and 2 electrons in 2p 3x2 and 2p half levels respectively. The crystal structure analysis of the compound reveals the presence of 2 different supramolecular dimers. The first one is assisted by oxygen pi hole interaction, anion pi interaction, and OH-Cl hydrogen bonding, whereas the second one is stabilized by antiparallel nitrile-nitrile and CH and hydrogen bonding interactions. And this is the map surface analysis of the free 4-cyanopyridine ligand. The map value over the carbon atom and the nitrogen atom of the cyanopyridine group is positive and negative respectively, which suggests the possibility of formation of antiparallel nitrile-nitrile interactions between them. Now we have calculated the overall supramolecular energy by using DFT calculation, and which is found to be minus 5.8 kilocalorie per mole. And from this QTIM analysis, we have investigated the energy of each hydrogen bond, which is found to be 1 kilocalorie per mole. By subtracting this value from the overall supramolecular energy, we have found the contribution of this nitrile-nitrile interaction, which is found to be minus 3.8 kilocalorie per mole, which is quite significant. Further, the presence of green isosurface between this nitrile moiety also suggests the presence of this nitrile-nitrile interaction in the dimer. This is the crystal structure of compound 2, where the manganese center is hexacoordinated with 3 coordinated water molecules, 2 monodentate 4-cyanopyridine ligand, and 1 monodentate sulfate moiety. Moreover, 1 lattice water molecule is also present in the crystal lattice. Here also we have analyzed the crystal structure analysis, and we have found that unconventional T-shaped nitrile-nitrile interaction is present in the supramolecular dimer, which is further established by NCI plot and QTIM computational tools. This is the crystal structure of compound 3, where the zinc center is tetracoordinated with 2 3-cyanopyridine and 2 chlorido ligands. Here also crystal structure analysis reveals the presence of 2 different supramolecular dimers. First one is assisted by pi-pi, anion pi, and CH pi nitrile interaction, whereas the second one is assisted by nitrile-nitrile and CH and hydrogen bonding interactions. By using QTIM analysis, we have further established the presence of this non-covalent interaction in these dimers, and by using the similar technique, we have investigated the stabilization energy of this nitrile-nitrile interaction, which is found to be quite significant, that is minus 5.9 kilocalorie per mole. We have also recorded the electronic spectra of the compounds in both solid and solution phase, and the similarity of the absorption peaks in both the phases indicate that our compounds do not undergo any structural distortion in the aqueous phase. And finally, we have carried out the application part, that is the in vitro antiproliferative evaluation of the compounds by using these 4 techniques. The first one is MDT cell viability assay, apoptosis study. Both are actually experimental technique, and the last 2, one molecular docking simulation and pharmacophore modeling, are theoretical techniques. Due to lack of time, I will not be able to discuss all the methodologies of these techniques. I will just highlight the results obtained for our compounds. The MDT cell viability assay as well as apoptosis assay reveal that our compounds induce significant concentration-dependent cytotoxicity in Delpons lymphoma malignant cancer cell lines with negligible cytotoxicity in normal PBMC cells. Further, we have carried out molecular docking study with our compounds with the active site of BCL family proteins, and it indicates that our compounds are quite capable of interacting the active site of the BCL family proteins. And finally, we have identified the pharmacophore features of all the 3 compounds, which are actually responsible for their biological activities. And finally, I would like to conclude. We have synthesized 3 coordination compounds of manganese 3, manganese 2, and zinc 2 involving cyanopyridine ligands, and we have investigated their crystal structure analysis and we have obtained various unconventional interactions. And finally, we have carried out in vitro anti-cancer activities of the compounds. And all the findings of these 3 compounds have been published very recently in these 3 particular journals. And I want to acknowledge Professor Manjit Bhattacharya sir for his constant inspiration, invaluable guidance, and constructive advices. I would like to thank Professor Antonio Frontera for collaborating with us for the theoretical study. And I would like to acknowledge Dr. Kalesh Kumar Verma sir for allowing us to carry out the biological study in his laboratory. I would also like to thank all my lab mates, and I would particularly like to thank Department of Chemistry IIT Guwahati for providing this single crystal XRD data. I would also like to thank Department of Chemical Sciences, Tezpur University for allowing me to present this presentation. Thank you.
So this presentation is now open for discussion. So if you don't have any question, Professor Thakur, please go ahead.
Mr. Pranay Sharma.
Yeah, yes, sir.
This biological activity, this test, so you carried out, or it was in the zoology department you were referring to?
No, actually we have done it, but we have performed this study in his laboratory.
Yeah. Okay. So do you have any kind of information that such molecules will be effective for such kind of biological activity?
Actually, if we go through the literature, actually we have found various coordination compounds involving these ligands. Various people, various research groups have already explored various in vitro as well as in vivo studies. Therefore, this literature review actually prompted us to carry out this biological study of the compounds.
Okay, so based on literature.
Yeah. Yes.
And with the cell lines, you talked about what kind of cell lines?
We have used Dalton's lymphoma malignant cancer cell line. It is a T cell lymphoma type cancer cell line actually, and we have therefore it is a malignant cancer cell. Therefore, we have chosen this particular cell line to perform that activity.
All right, very good.
Thank you, sir.
So next, I would like to invite Dr. Sansoita Raskwa for her presentation. Dr. Raskwa, please go ahead.
Yes, sir. So are my slides visible?
Yes.
Yes, thank you. A very good afternoon, everyone. Today, I'm going to give an oral presentation of our work consisting of a biophysical study on interaction mechanism of vithanol and vithaferin A with lysozyme, human serum albumin, and human hemoglobin. These are the topics, contents. Ashwagandha, it is one of the most important plants of South Asia, especially in India, with established therapeutic potentials and has been widely used in different forms of drug preparation. This is mainly due to the presence of various active moieties having a steroidal lactone ring in their structure, which is called as the vithanolid. There are almost 35 vithanolids, but of these 35 vithanolids, vithanol and vithaferin A, they serve as a neuroprotective agent and show anti-cancer, anti-stress, antioxidant, immunomodulatory, and also anti-leishmanial properties. And recently, it has been explored in some research which shows it might be conclusive against COVID-19 as a preventive drug. Now, carrier proteins are the principal structural and functional proteins which play a major role in active transport, and they facilitate diffusion. These processes encourage apportion of drugs and other molecules to their respective drug targets and consequently have been utilized in numerous drug delivery processes. Therefore, to perceive the molecular recognition mechanism for the delivery of vithanol and vithaferin A by carrier proteins, we have studied its interaction with three carrier proteins like the human lysozyme, the human serum albumin, and the human hemoglobin using various computational tools. For our study, we have extensively used molecular docking study to understand the stability of the complexes and molecular dynamics simulation to understand the dynamical properties at different time frames. These are some of the tools that we have used for our study. These are the methods. So, both the compounds, the vithanol and vithaferin A, they were docked onto the different considered proteins. And these are the minimum dock poses for both vithanol and vithaferin A. So these are, this is for dock poses for both vithanol and vithaferin A. This slide shows the figures of the RMSD plot from the molecular dynamics simulation studies. As you can see in the as you can see from the slides, that in case of HSA, the highest number of fluctuations can be seen in this blue color, the blue color being the complex of HSA and vitaferin A, whereas the lowest fluctuations were seen in the orange color, and which is the native HSA. However, Withanon, when in complex with HSA, was also showing a better stability. Then, in case of vitaferin, in case of hemoglobin, you can see that the highest number of fluctuations can be seen when hemoglobin was in a complex with Withanon, whereas the fluctuations became much lower and the structure became was much stable when in complex with the vitaferin A. Similarly, in case of HL also, the highest stability could be seen in vitaferin A. Now, in order to understand what kind of fluctuations, what are the substituent groups or why the fluctuations are occurring, the RMSF plot was performed. The RMSF plot, this is the figure showing the RMSF plot of the structurally, of the stretch that is functionally important. So the entire proteins are not shown here. These are only the residues which consist the binding site. And here you can see that in case of HL, in number 1, in case of HL, lysozyme, when it was in complex with vitaferin A, it showed comparable fluctuations as of the native protein. Also, this was also what we observed in case of hemoglobin, that the fluctuations were almost comparable to that of the native protein. However, in case of HSA, the fluctuations were much better and comparable to the native protein when it was in complex with Withanon. Now, after the fluctuations, we wanted to look further about the compactness of the protein, how compact the protein is. So we performed the RG plot, and from the radius of gyration, it can be seen that in case of Withanon also, this is consistent with our other results. So in case of Withanon, the protein seemed to be much more compact, whereas in case of hemoglobin, the native protein was seen to be more compact. However, vitaferin A was also showing a good result. And then in case of HL also, you can see that vitaferin was showing a better compactness when in complex with HL and vitaferin A. So this is an average solvent accessible surface area graph, wherein you can see that how much of the accessible solvent accessible surface area, how the trend is changing. So it is believed that the accessible area should be less for the binding to be better. So in case of the average also, we can see that Withanon in complex with HSA had the lowest accessible surface area, whereas in case of HB, although the figures show it is comparable, but you can see that in HB in complex with vitaferin A is comparable to the native protein. And in HL, when bound to vitaferin A, the compactness, the SASA, it decreased drastically. Therefore, our results are in sync with the RG plots. To see if the ligands are attaining more stability and not coming out of the binding site, we have performed the hydrogen bond analysis, and from this figure it can be seen that in case of HSA, the number of H bonds were increasing when in complex with Withanon. However, in case of hemoglobin, although there was a trend of increasing H bonds in case of HB vitaferin A, but towards the 100 nanosecond simulation, it became almost equal. And then in case of lysozyme as well, although there was a trend of increasing, but slowly we can see that there are certain fluctuations. So we went further to see the hydrophobic interactions, and from hydrophobic interactions we found that Withanol is obviously looking very stable with HSA, and Vithoferin A is showing a stability with hemoglobin, and Vithoferin A again is showing a very good stability with the lysozyme. We have also performed the MMPBSA analysis, and our results were in consistency with all the other experiments that we have done. In conclusion, it can be said that our study has provided a substantial insight into the binding of the bioactive compounds Withanol and Vithoferin A with the carrier proteins. Further, study may be undertaken for collecting details suitable for interactions of proteins and ligands, which can prove as essential in comparable molecules or their derivatives. The importance of this work lies in the fact that since Withanol and Vithoferin A are known to have a wide range of pharmacological effects having multiple target cells or tissues, this computational study sheds light on the stability of Withanol and Vithoferin A with the different carrier proteins, thus opening new ideas about the transport reaction and reaction mechanism with the concerned targets. For example, since HSA was showing stability with Withanol, now HSA is abundantly found in proteins such as protein kinase C. So this kind of protein, this is one of the known targets of anti-leishmanial drug. Therefore, if ever you want to design an anti-leishmanial drug, then it should be a derivative of a Withanol. Only then it will be bound to HSA, and this HSA will be able to carry it to this kind of targets. Similarly, since HL had showed the stability with Vithoferin A, therefore HL may be able to carry Vithoferin A or its derivatives to certain anti-cancer targets like the TPX2, the Aurora kinase A, the HSP90, etc. And further studies can be performed towards this area. Similarly, in case of HB also, hemoglobin, since it was showing the highest stability with Vithoferin A, therefore it can be able to carry Vithoferin A or its derivatives to certain targets. Suppose the transmembrane protease serine 2, which is found in the epithelial cells of the respiratory tract. So HB will be able to carry it to this target. Hence, if we are interested in designing an anti-COVID drug, then it should be an derivative of Vithoferin A. With this, I'm ending my presentation. These are the references that we have used to make the slides. Thank you.
Thank you, Dr. Raskwa. Now this session is open for discussion. So if anybody has any question, please go ahead. I think there is no any question. So thank you, Dr. Raskwa. Now we'll go to the second presentation by Sudipta Shutia.
Yes, sir.
Sudipta?
Yes, sir. Present, sir.
Yes, please go ahead.
Yes, sir. Sir, my slide is visible. Is my slide is visible, sir?
No, we can't see.
Okay. Yes. Okay. So is my slide is visible, sir?
Yes, we can see.
Okay.
So you can make it full screen. Yes,
Okay.
yes.
Yeah.
Good.
Good evening, sir. Now, my name is Sudipta Sutia. I'm a research scholar from Guwahati University, and I do my research work under the supervision of Dr. Kondorfa Bhukan sir in the college. So now I'm going to represent one of my research topic, which actually I'm going to basically synthesize a binary composite, conductive binary composite by in situ oxidative polymerization method, the polyaniline and betel nut fiber. So this is my presentation outline. Now I'm directly go to the introduction part. So at first I introduce the betel nut fiber. Why I choose this nacelle fiber? Because the abundance of this fiber is very high in Assam or in India. And it is also the cost effectiveness and biodegradability and sustainability. Next thing is the fiber contain the betel nut husk contains about 40 to 60% fiber, which is very good, and hemicellulose contains 35 to 64%, lignin 13 to 26% up to. So, and one of the most important thing is that the fiber contains two types. In betel nut husk, there are two types of fiber contents. One is very rougher part, and one is rough part, and one is fine part. And I took the fine part to prepare my composite. Next one, polyaniline. Polyaniline, we know about the polyaniline is a conducting polymer, who is first introduced in 1862, as known as a aniline black because of its dark green color. So it's known as a aniline black. And then the advantage of this conductive polymer is very cheap, easy to pursue, and easy to synthesize. And also it has variable oxidation state. So the conducting form of polyaniline is the emerging salt form, which was partially oxidized and partially reduced, which I shown in my slide. Then there is a lots of literature where the nacelle fiber and pani are composite, prepare composite in situ via in situ oxidative polymerization to study about the electrical conductivity character. But till now, I am not found any literature about the BNF and pani composite. So I choose this. One of the main reasons why I choose this nacelle fiber. Then methodology. How I prepare my composite. At first, we modify the betel nut fiber. So because of betel nut fiber contains in husk, so we collected husk from local shops. Then we soaked in a water for 20 days. Then we dried the wet husk in a room temperature. After that, manually we collected the fine part of this fine fiber of the betel nut husk containing. So this fine fiber, after that this collected the fine fiber, we treated with 4% sodium hydroxide for 3 hours at 95 degrees centigrade. This process is also known as a mercerization process. We did this because to eliminate the impurities and foreign elements. So after that, we prepared the betel nut fiber. Then we used this raw material to with pani composite. So here I saw a schematic diagram where we saw that the betel nut fiber, where the OH group present, but the impurities also present here. But after the mercerization process or treatment process, we saw that little orange color of this fiber, and the cleanness of this fiber surface was very good. Then the aniline carbon tetrachloride solution prepared previously. Then after that, we add this fiber, which individually. I'm trying to fill the fiber individually, like each fiber first, then another fiber. Then we after 15 minutes stir, we add ammonium persulfate as an oxidizing agent, which uses the oxidizing agent, which prepare the HCl solution, and then dropwise we added in the APS aniline carbon tetrachloride with plus BNF solution. The temperature maintained up to 0 to 5 degrees centigrade. So this is the how we synthesize the composite. After that, we characterized or we analysis analysis about the composite. At first, we know about the functional group, what the interaction, how the interaction will be observed. So, to comparison between the Pani BNF and BNF Pani composite, we first see the black curve of FTIR. We see there the OS peak, which is a broad OS peak because of free OS in containing in cellulosic BNF. Then then CH and C double bond O, G to acetyl, the containing acetylene group of hemicellulose was shown in 2902 and 1730 centimeter inverse. After that, the aromatic lignin also shows at 1633. But in case of Pani, the benzenoid and quinoid shows 1492 and 1560. After that, the main important peak shows by this Pani is 1160, which basically gives the conductive nature. In composite, this conductive nature peak will be shifted to 1113 centimeter inverse. In my IR spectrogram or IR spectra analysis, I found a very interesting conclusion that the hydrogen, the doping hydrogen atom, protonated the nitrogen atom or quinoid or benzenoid, both half oxidized and half reduced part, act as a bridging between polyalenine and BNF. So they throw the interaction through the hydrogen bond interaction. After that, we analyzed the thermal stability of composite compared with the BNF. Then we saw there is a three main clear degradation in thermograms. The first one is 100 degrees centigrade, where BNF and both BNF and composite with at 100 degrees centigrade loss of moisture because of breakdown the hydrogen bond. At 258 degrees centigrade, we saw that the hemicellulose decomposition of hemicellulose lignin and cellulosic part of this containing the BNF. But the last degradation was occurred in only composite because of the Pani content, decomposition of Pani, which is not present in the BNF. So it actually gives information about the composite that the Pani will stabilize the composite more compared with the BNF, and deposition of Pani also we can say that the deposition of Pani on BNF surface is very good. In XRD, the structural feature was analyzed by the XRD, where we found in mid BNF we found two peaks, 2 theta value and 15.4 and 22.4 respectively. These two plane 101 and 002 is the crystallographic plane of raw BNF. But when we analyze the composite XRD graph, we saw that two new peaks will be obtained at 2 theta 26.6 and 33.84, which represents that the crystallographic plane, these crystallographic planes respectively signify the deposition of polyalenine on the betannate fiber. One more important thing is this Pani is the form of emarlyl salt. And the morphology analysis by the same image, we found that in the raw BNF there is lots of fracture and microporous, also the surface is rough. But when we saw the micrographs B 5B, then we saw that the uniform coating above the uniform coating on the surface, and the microporous will be disappear. But the cross section will explain that the Pani deposited only on the surface, not the bulk of the fiber. This explained by the cross section of the composite. Then the UV visible spectra, where the UV visible spectra, basically we saw about we want to calculate the band gap, but here we observe one thing, that polyaniline basically gives 3 peak at pi to pi star, 3 to 366, okay, to 266, and polaron to pi star 386, and pi to polaron 378. But here the 386 the second peak, 386 is the main focusing peak, because this is because of this observed because of emergent sol. Due to emergent sol is a conductive part of polyaniline, so we saw that numbers of my experiment where we continuously increasing my fiber amount, then we found that at limited amount we saw the second peak gives red shift, with the wavelength will be increases. So that explains that it will be the red shift, and the band gap at the same time the band gap will be decreases, which I shown in next slide. So band gap we calculated by the Proc relation, where we found that net pani exhibits at 3.92 eV. But when we increases the amount of BNF at 0.22 gram, the BNF band gap will be decreases up to 0.99. And also this band gap is directly related with the conductivity, which I discuss on later, that the band gap decreases means the conductivity will be increases. So when I used, then after that I will measure the AC conductivity through EIS, electrochemical impedance spectroscopy, that we found that the polyaniline gives at room temperature the AC conductivity for 2.48 into 10 to the power minus 47 per centimeter. But at the same time, the at the room temperature, the composite show 2.76 into 10 to the power minus 4%. That explains that the composite gives better, good AC conductivity than the comparator pani. After that, I would know to the temperature effect in the conductivity. Then I saw that the temperature when increases from 30 to 70, the AC conductivity will continuously increases, but after 70 it will jump, because I think because of this is elimination of water, which I explained in the TGA graph. So at 70 to 80, now we found that the conductivity will be generally increases from 4.57 into 10 to the power 7 per centimeter. So that explains that the from temperature increases also increases the conductivity of the composites. So it is we can say this is a good this is the behavior of the semiconductor. Those behave as a semiconductor. So at last, the conclusion, I found that the BNF pani composite synthesis process in situ is a good process because of it. It gives uniform deposition of pani in BNF fiber. After that, the thermal stability of BNF pani composite is higher than the BNF. The UV visible spectrum also explained that the red shift of the polaron to pi tension particularly, and also the optical band gap will be decreases the amount of fiber increases, and that explains that the AC conductivity of BNF and pani composite increases from 2.67 into 10 to the power minus 47 per centimeter to 4.57 into 10 to the power minus 7, which increases with the temperature. This all conclusion gives me information that this composite, biocompatible composite, is efficient to use in chemical sensor and electronic device in further our experiments. Thank you.
So thank you, Sudipta. So if anybody has any question, please go ahead. So if there is no any question, we will go to the next presentation, and I request Hemen Gogoi to present his paper.
Yes, sir.
Am I audible, sir?
Yes.
Are my slides visible, sir?
Not.
Okay, some problem is there. Yeah, actually some problem is happening with my system, so please excuse. Yeah, sir, could you proceed with the other presenter so that I can rectify the problem?
Okay, no problem. Then I request Ishita Chakraborty. Ishita Chakraborty.
Yes, sir, I'm present.
Please go ahead. So Haman has some technical issue.
Sure,
please.
sure. I hope my slides are visible.
Yes.
Shall I start the presentation?
Yes.
A very good afternoon or good evening to one and all present here for this session. I am Ishita Chakraborty, research scholar from the Department of Biophysics, Manipal School of Life Sciences, Manipal Academy of Higher Education, Karnataka. I am working under the guidance of Dr. Nirmal Majumdar, who is an assistant professor here. The title of my today's presentation is Sustainable Starch-Based Bioplastic for a Better Future. So bioplastics are basically biodegradable materials that come from renewable biomass and can be used to reduce the problem of plastic waste that is suffocating the planet and contaminating the environment. Starch-based bioplastics are currently gaining wide attention. Starch is a natural biopolymer consisting predominantly of two polymer types of glucose, namely amylose and amylopectin. The advantages of starch for bioplastic production include its renewability, good oxygen barrier abundance, low cost and biodegradability. The long-standing quest of developing starch-based biodegradable plastics has witnessed the use of different starches in many forms, such as native granular starch, modified starch, plasticized starch, and in blends with many synthetic polymers for the purpose of achieving a cost-effective and for the purpose of achieving cost effectiveness and biodegradation. However, most starch-based composites exhibit poor material properties, and therefore scientific inquiries towards improving the production of these promising starch-based biocomposites through starch modification, reinforcements, and processing conditions have been used, all in the hope of realizing renewable biodegradable substitutes for conventional plastics. Cross-linking is the most widely used method for modification of native starch. Citric acid is a weak organic acid which is found in citrus fruits, and it acts as both a cross-linking agent and a plasticizer while developing starch films. It can form strong hydrogen bonds interaction with starch and improve the thermal and water stability. Starch-based bioplastics can be processed through several techniques like casting, compression, or injection molding. Now, casting is a process where the molten plastic is introduced into a mold, allowed to solidify within the mold, and then ejected or broken out. So here what we have done is we have developed bioplastic films from starch, where they were prepared from a combination of rice and potato starch by casting method, where also citric acid was added in different increasing concentrations, that is 10%, 30%, and 50%. The resulting suspension was stirred with a magnetic stirring bar and heated till 85 degrees Celsius for effective cross-linking. And the blend was then cast onto the silicon mold, dried at room temperature for about 7 days. As we know that both rice and potato are extremely rich sources of starch. So as we can see here, the first figure shows the digital images of the synthesized bioplastics. The first the image A is the bioplastic which was without the addition of any citric acid, followed by the bioplastics developed with 10, 30, and 50% of citric acid. The synthesized bioplastics were transparent, odorless, flexible, non-porous, and non-sticky. Next, the initial morphological characterization was conducted with the help of scanning electron microscopy. The SEM images on the left exhibit the surface and the cross-sectional view of the developed polymers. Scanning electron microscope pictures of the control and the cross-linked films do not show any appreciable changes in the surface morphology due to cross-linking. The films are homogeneous without any pores or cracks. The cross-sectional view of the cross-linked films was continuous, indicating that the integrity of the integrity and structure of the developed bioplastics and the good compatibility of starch and citric acid. Next, we can see the three-dimensional images of the bioplastic surface, which was obtained by atomic force microscopy under tapping mode. The RMS roughness values are also indicated in the figure. The root mean square or the RMS roughness was the highest for the bioplastic without any cross-linking. That was around 145 nm, whereas it was the lowest for bioplastics cross-linked with 50% of citric acid, and it stood around somewhere 43.2 nm. Next, we did performed structural characterization for the bioplastics. The figure on the left shows the FTIR spectra, where we can see that the cross-linked film shows an extra peak at around 1716 centimeter inverse, which is marked by the black arrows, and indicates the formation of the ester carbonyl bonds, which is introduced because of the cross-linking by citric acid. And on the right, we can see the XRD diffractogram, from which it is evident that the bioplastics retain their semi-crystalline nature because of the presence of certain amount of peaks. However, there is a fall in the crystallinity index, which was calculated. It can be inferred from this that at higher concentration, citric acid also hydrolyzes the starch apart from cross-linking it as a side reaction. Next, we also conducted a thermal stability, studied the thermal characteristics of the developed bioplastics. The thermal stability of these bioplastics was studied using two methods, that is differential scanning calorimetry, DSC, and thermogravimetric analysis, that is TGA. The DSC and the TGA analysis revealed that the bioplastic with 50% of citric acid exhibited the highest melting point and the lowest weight loss compared to the bioplastics with lower concentrations of citric acid. Finally, we also checked the antimicrobial activity of the bioplastics. We used strains of E. coli, S. aureus, S. typhimurium, P. aeruginosa, Candida albicans. It was observed that the addition of citric acid to the bioplastics resulted in an antimicrobial properties, whereas the bioplastic which was not cross-linked or did not have any citric acid and was used as control did not show any antimicrobial activity. The highest activity was seen against S. E. coli based on the zone of inhibition that is displayed in the figure below and also in the table. So in order to conclude, from all the characterization experiments, we concluded that citric acid is an organic acid that can be effectively used for cross-linking of starch and to develop a bioplastic with the desirable functional properties. Although citric acid has not been explored or used much for the starch cross-linking, it has been reported that it forms strong hydrogen bond interactions with starch and improves the thermal and water stability of starch, moisture holding capacities of starch, and also it inhibits or prohibits starch retrogradation, which are desired properties while developing any bioplastic. I would like to acknowledge Department of Science and Technology, DST, Government of Karnataka, India for the PhD fellowship. I would also like to sincerely thank my guide, Dr. Nirmal Majumdar, from the Department of Biophysics for his support and guidance. And we would like to thank DST, Government of India, as well as ICMR for the financial support during carrying out this work. Thank you.
Thank you, Isita. So we are running out of time. Therefore, I go to the next presentation. Hemen, are you ready?
Yes, sir.
Okay, please go ahead.
Yeah.
Yes, it is now visible.
Yes, sir.
Go ahead.
Yeah. Good afternoon, everyone. I am Hemen Gogoi, a PhD student from Department of Chemistry, IIT Bombay, under the supervision of Professor Anindya Datta. So today I'm going to talk about the role of solvent in electron phonon relaxation dynamics in core cell gold silica nanoparticles. So gold nanoparticles shows the phenomenon of localized surface plasmon resonance, LSPR, which is basically the result of resonance of the oscillation frequency of the free conduction band electron and the frequency of the incoming radiation. Because of this, a sharp absorption band appears. That is called the plasmonic band, and the position of that plasmonic band basically depends upon the size, shape, and the surrounding environment of the nanoparticles. Out of the noble metals, gold and silver nanoparticles show LSPR in the visible region of the spectrum. The motivation for our works comes from the fact that this core cell gold silica nanoparticles, here the gold core has the property like inert, it has inert surface, it is biocompatible in nature. The optical properties like LSPR is shape dependent, and we can also tune the surface plasmon resonance. The main application being in the photothermal therapy. And a silica cell that not only stabilizes the gold core, but it is also biocompatible. It is chemically inert, optically transparent, also stable in colloidal suspensions, and one of the application is in chemotherapy because this surface can be used to functionalize with different important drug molecules. The core cell nanoparticle synthesis basically involves 3 steps. First is sodium citrate. In presence of sodium citrate, gold salt is reduced to get the gold nanoparticles. Then gold nanoparticle is coated with polyethylene glycol at room temperature to get the polyethylene glycol coated gold nanoparticles. It is then treated with the silica precursor, which is tetraethyl orthosilicate at room temperature catalyzed by ammonia to get the core shell gold silica nanoparticles. The synthesized nanoparticle has been characterized with transmission electron microscopy. Here this image shows the synthesized nanoparticles, and from the size distribution of around 200 nanoparticles shows that it has a uniform core with a uniform thickness of the shell. Now, in order to study the effect of surrounding environment on the relaxation dynamics in these nanoparticles, we have used 4 different solvents, namely water, methanol, acetonitrile, and DMF. This is basically this image shows the surface plasmon band in the different solvents. Here, if we look very carefully at this image, we can see a slight shift with a change in solvent from water to DMF. This change is basically because of the change in the refractive index of the solvent from water to DMF. Now, in order to study the relaxation dynamics in these nanostructures, a technique called femtosecond palm probe spectroscopy, which is also called transient absorption spectroscopy, has been used. In this technique, a strong pump has been used to excite the molecules into their excited state. Then their excited state evolution has been probed by a weak probe pulse. This is basically a pump probe process, and by considering the absorption change in presence of pump and in absence of pump, we could get the signal which tells us about how these excited states are evolving with time. And depending upon different signatures that we obtain from the characteristic spectral features, there are different signals like ground state bleach, stimulated emission, and excited state absorption. So,
आप already चले गए क्या? निकल गए
excuse me, somebody can mute, please.
अच्छा.
So, Ishita Chakraborty, could you please mute yourself? Ishita Chakraborty.
हाँ, ठीक है. Okay. Thank you.
Ishita, kindly mute yourself. Hemant, go ahead.
Yeah. So, this is the spectra. This is the transient absorption spectra of gold silica nanoparticle. Here, if you look at the spectra, here 3 distinct features appear. The feature at around 520 nanometer is due to the ground state bleach, which appear in the same position like the plasmonic band in the absorption spectra. The band at around 470 nanometer is due to the electron interband transition, while the band at around 600 nanometer is due to electron intraband transition. Now, we have studied how the relaxation dynamics in this nanostructure changes with variation of different excitation power and variation of solvent. For this power variation study, we have employed 5 different powers actually, and for solvents we employed water, acetonitrile, methanol, and DMF. These are the decay traces which has been used to extract the time constant of relaxation, and in these actually, if we look at these decay traces, here 2 time constant basically appears. One is electron phonon scattering, and one is phonon scattering. So when we excite this nanostructure with a strong pump pulse, there are 3 actually different processes through which the electron can relax. One is electron scattering, which takes place in a few femtosecond time scale, followed by electron phonon coupling, which takes place in 1 to 10 picosecond time scale, and that followed by phonon coupling, which takes place in more than 10 picosecond time scale. And electron phonon scattering, as you can see, like it is a few femtosecond time scale phenomenon, so because of which it could not be resolved with the instruments that we are using. Now, from the decay traces that I have shown in the previous slide, by fitting of those decay traces, we could get the time constant of electron phonon coupling and phonon coupling. So here with the in this figure, the first panel shows how this electron phonon coupling constant changes with the pump energy. Here we can see that with the increase in pump energy, the electron phonon coupling constant increases, while the phonon is not changing. That is mainly because of the fact that electron temperature are actually excitation power dependent, because of which when we are using more powers, then that means we are disturbing the equilibrium more, because of which it will take more time to come in thermal equilibrium, come to its initial position. The higher the power, higher will be the time taken by these electrons to come back to their initial position, because of which we we see an increase in electron phonon time constant with increase in power. And in the second panel, what we could see is that with the increase in thermal conductivity of the solvent, electron phonon time constant actually decreases. That is because of the fact that higher the thermal conductivity of the solvent, higher will be its capacity to dissipate the heat accumulated in the on the nanoparticles. Because of which, when the thermal conductivity of the solvent is increasing, the electron phonon time constant is found to be smaller. That means it is dissipating fast, while phonon-phonon relaxation time has not been found to be changed. So in conclusion, we have synthesized gold nanoparticles, then coated with silica to get the core cell nanoparticles. And this synthesized nanoparticle has been dispersed in different solvents with different thermal conductivities, and their relaxation dynamics has been followed with the pump spectroscopy, where the electron phonon relaxation is showing to be dependent upon the pump fluence and the higher thermal conductivity of the solvent, while phonon-phonon relaxation is not changing with time. I'd like to acknowledge my supervisor, Professor Anindya Datta, and Department of Chemistry, SAFE, IIT Bombay, IITB Monash Research Academy, Mumbai, all my lab mates and friends, and at last but not the least, Department of Chemical Sciences, Tezpur University, for giving me this opportunity to share my research. Thank you.
Thank you, Hemen, for your nice presentation. Yes, so as we are running out of time, there will be no interaction now. Next, I would like to request Dr. Saswati Adhikari. Dr. Adhikari, are you there?
Yes, I'm here.
So please go ahead.
Yes. Is it visible? Hello?
Yes, it's visible.
Okay. So, this is Dr. Saswati Adhikari. It's my distinct honor and pleasure that I can discuss my research work on this reputed platform, National Conference on Sustainability, Medicine and Clean Energy, organized by the Department of Chemical Science, Tezpur University. So, very beginning, I'm thankful for them. So let's start my talk entitled Explorations of Small Organic Biofluorophores using one-pot Arabic green synthetic methodology. So from my title, you can understand that it is having the two parts, that is the biofluorophores and the green synthetic methodology. Now, what does the biofluorophores means? So biofluorophores can have different aspects. That cell is a unit of any living body, so which is responsible for different biochemical reactions in it. Not only that, inside the cell, different subcellular organelles are there, like a mitochondria, lysosome, cytoplasm, nucleus, etc. are there. So each and every subcellular organelles have their own functions. Not only that, there are number, positions, relative locations. It is not fixed. It differs from different physiological as well as different disease conditions. So by imaging all these cell as well as different subcellular organelles, we can get different informations, which is very significant. We can gather all these informations, which may be different physiological.
Your slides are not moving.
Oh, just 1 minute. So now is it visible?
Yes.
Okay. So by imaging of this study, we can get different information regarding the subcellular organelles as well as the cells. So one more example is that, so if one can design like a cancer cell targeting compound, which can localize inside the cancer cell, particularly by injecting of the compound, the accumulations of inside the cancer cell target. After accumulations of the cancer target, the photodynamic or photothermal therapies can be done, which can be by which the particularly cancer cell can be destroyed. So these are simple examples of the biofluorophores. So here have some examples of the biofluorophores like mitotracker dye and lysotracker's dye, which is having some drawbacks. And what is the drawbacks? Like mitotracker dye, it is having the reactive site in it, which can readily react with the peptides or enzyme SH group of the mitochondria and having a different cytotoxic effect. that means it is not biocompatible. So the using of this dye, it is not good for the imaging purposes. Not only that, all this large molecule is synthetically very complex, and also there are some issues of the photostability. So how to design the small organic fluorophores as a subcellular probes. So for designing organic biofluorophores, basic information regarding the respective organelles very necessary, like lysosome. It is an acidic pH, and inside it different enzymes is there that is responsible for the breakdowns of different macromolecules like peptide, proteins, etc. And for as it is a acidic organelles, the different basic moieties like amine can be readily located inside the lysosomes. And what about mitochondria? Mitochondria is a negatively charged membrane. So mitochondria can produce ATP, which is the energy currency of any living bodies. And for that, mitochondria produce negatively charged membrane outside. And as it's a negatively charged membrane, so positively charged molecule can be readily relocate inside the mitochondria. So this is the information regarding the respective organelles. So now the conjugations of these organelle targetable groups with the fluorophores can trigger the subcellular organelles, particularly by which we can get different informations which may be the disease related or with different physiological context. Now the synthesis of the dye. How can we synthesize the dye? So by using simple green synthetic strategy. From the readily available starting materials, so 1,2-dicarbonyl compound or alpha-hydroxycarbonyl compound using benzyl, different substituted benzyl amine, and iodine as a catalyst, discarding the use of different organic solvent. I used water as a solvent and potassium carbonate act as a base. So this reaction is toxic transition metal free. As we all know that a transition metals having severe drawbacks for environment as well as for the living bodies, and this reactions is a one pot, so it is a time saving process. It is an open air aerobic SPTCH functionalization, cost effective, having broad substrate scope, and also this different diversified small organic molecules are oxygens and imidazole is shown here. Can be synthesized from easily available starting materials. And next one is when benzyl amine is used, one equivalent oxazole is synthesized. XO is here, that is from oxazoles, and when benzyl amine is used, two equivalent imidazole molecule is synthesized. So now next one can be by using this methodology, we can tune the targeting group. What is that? Let's discuss. So here we can see the structures of the lysosome targeting group, which are the amine. By using simple methyl iodide, the nitrogens can readily alkylated, and for that, this end can be generate positively charged. So this one molecules can be used as a lysosome targeting group, and this one can be used as a mitochondria targeting group. So by using the simple methodology, we can synthesize different subcellular organelles biofluorophores. So I have synthesized the library of the molecules. Among them, 4 of the molecules has been given here for restrictions of the time. First L1 and L2 is for the lysosome targeting fluorophores. Next one is the cytoplasm targeting, and the latter one is for the mitochondria targeting fluorophores.
Your slide is not moving. Only it's visible in the second slide only.
Okay. Okay. So now is it visible? Hello?
Yes.
Okay. So let's discuss about the photophysical studies of the compound L2, this one. So the photophysical properties of these molecules revealed in different organic solvent reveals that these molecules having intermolecular charge transfer spectra, as proved by the fluorescence peak shifting from left to right, more red shifting with increasing the polarity of the solvent. Not only this, I have scrutinized the pH buffer in different pH buffer. So it shows that with decreasing the pH of the solution, that molecules become much more brightness, and these features is very necessary for a lysosome targeting. So it can be readily visible under the microscopy. And last of all, that this molecule is showing very good photo stability. And next one, to understand the colocalization studies inside the lysosome, confocal imaging microscopic studies has been performed using the HeLa cell, which is a human cancer cell lines, as well as a mutant cell line by using the living cell imaging studies. And all these studies reveals that very high Pearson coefficient with respect to the marketed dye lysotracker. It's almost tends to 1. At a 95% overlap with respect to the lysotracker dye. So all these studies reveals that these small organic molecules can be used as a lysosome targeting groups. So next one have been used for the mitotracker molecules. So here is the photophysical studies in different organic solvents. Here also the studies reveals that these molecules MO1 having intramolecular charge transfers inside it, as they are two with electron donating, and this one is electron withdrawing group. So it is having the intramolecular charge transfer molecules, and in the pH buffer solutions, fluorescence spectroscopy reveal that these molecules is stable in different pH. Different pH of the buffer, and photostability study reveals that this molecule is stable in with respect to the even marketed dye mitotracker deep red also. And the confocal imaging study by using the breast cancer cell line reveals that these molecules Pearson correlation coefficient is 93% with respect to the mitotracker deep red. So these small organic molecules can be used for imaging mitochondria even in the live cell. So next one have next molecule has been synthesized for cytoplasm imaging study, and this was confirmed by the microscopic confocal imaging microscopic. And here from the pictures it is very clear that these molecules can be readily imaged by the inside the cytoplasms also. So all these molecules can be readily penetrate inside the cell lines also, and having less cytotoxicity effect, and is very biocompatible. So last of all, so all these molecules has been synthesized by transition metal free iodine catalyzed water mediated using green synthetic methodology approach from the very easily available starting materials. All these methodologies is operationally very simple, cost effective, one per respective stage functionalizations, and by using this simple methodology, or different organelle targetable biofluorophores can be readily synthesized, which can be tuned accordingly. And next one, I want to acknowledge thanks to my guide, PhD guide, Dr. Vishwadhi Banerjee, Senior Principal Scientist, CSIR ICB, Kolkata, Professor Chitra Mondol, ma'am, for giving me the biological support, the Tezpur University, but Professor Ullas Poltur Sitaram, Typer, for giving me the opportunity to understand the biological work very nicely, and last of all, family, friends, and lab mates. And next one, I want to thank all of you for your time.
Thank you, Dr. Odhikari, for your nice presentation. But due to constraint of time, now we will move to the next speaker. It's Sikharani Hazarika. Hazarika, please go ahead.
Yes, sir. Okay, sir.
Are my slides visible, sir? Hello? Are my slides visible, sir?
No, slides are not yet visible.
Is it visible now, sir?
No.
Is it visible now, sir?
No. Your slides are not coming.
Okay, let me give in. So just for 1 minute.
Okay, no problem. Yes, now I can see your slide.
Okay, sir. Good evening to everyone present. Myself, Sekharani Hazarika. I'm a PhD research scholar of Department of Chemistry, Dibrugarh University, under the supervision of Professor Gitika Bora, HOD, Department of Chemistry, Dibrugarh University. The paper is a highly effective silica-supported cobalt ferrite nanocatalyst with magnetic recyclability for hydration of nitriles. The contents of my paper includes introduction, experimental, recent discussion, conclusion, and references. We all know that the amides are very important class of compounds having both academic and industrial significance. But the conventional procedure for amide synthesis involves the use of strong acids and bases, which result in the formation of various byproducts along with the formation of carbon. In this context, we report here a magnetically separable, recyclable, and versatile silica-supported cobalt ferrite nanocatalyst with using an inert atmosphere for selective hydration of nitriles amides. In recent years, the synthesis of magnetic spinel nanoparticle is a growing field of research where magnetic nanoparticles offer significantly increased surface area, chemical reactivity, unique electronic and magnetic properties, and unparalleled efficiency compared to their conventional counterparts. However, spinel magnetic nanoparticles, particularly the cobalt ferrites, have some limitations due to the natural agglomeration of these particles into larger counterparts. Hence, to overcome this problem, we have used silica as coating material to the surface of cobalt ferrite nanoparticles, which avoid unwanted contacts with the core, improving its stability and preventing particle agglomeration. And the some basic features of the synthesized catalyst are: it is non-toxic, non-corrosive, economical, it is thermally stable, magnetically recyclable, the cost is low, and the surface area of the catalyst is also large. Next, let us move to the experimental section. This is the flowchart for the synthesis of silica-supported cobalt ferrite nanocatalyst. And to synthesize this catalyst, first we have mixed 0.04 molar ferric chloride and 0.02 molar cobalt chloride solution in a Rambutan flux, and that is stirred for 1 hour at room temperature. And then 0.5 molar sodium chloride solution was added dropwise to the solution, followed by addition of 1 molar sodium hydroxide solution dropwise with constant stirring until the pH of the solution reached 9 to 10. And then again stirred for another 5 hours until complete precipitation. Then 2 milliliter of tetraethyl orthosilicate and 1 milliliter of ammonia solution was added dropwise to the mixer, and the resultant mixer was somicated for 1 hour, followed by stirring at room temperature for 12 hours. And then the resultant precipitate was magnetically separated by using an external magnet and washed several times with water and ethanol. And finally, it was dried in an oven at 80 degrees centigrade to yield the desired silica-supported cobalt ferrite nanocomposite. And the resultant catalyst was then characterized by several analytical techniques, which include XRD, XPS, ICP-AES, then SAM, TEM, etc. First, let us see the XRD pattern of the synthesized catalyst, and which is shown in this figure, and it indicates the formation of silica-supported cobalt ferrite nanocatalyst. The broad, highly dispersed peak with 2 theta values at 23.1 degree indicates the presence of amorphous nanosilica, and the diffraction peaks with 2 theta values at 36.1 degree, 45 degree, and 57.2 degree, and 62.5 degree, corresponding to the crystal planes 311, 400, 511, and 440 respectively, resemble the characteristic peaks of cobalt ferrite, and this confirms the successful incorporation of silica over cobalt ferrite nanocatalyst. Then we have performed the XPS analysis, and the XPS spectrum of cobalt in cobalt ferrite silica supported cobalt ferrite nanocatalyst is presented here, in which cobalt contains cobalt 2p 3 by 2 and cobalt 2p half lines with a binding energy of 781.5 electron volt and 796.9 electron volt respectively, and the satellite peaks corresponding to the binding energy 787.2 electron volt and 802.4 electron volt respectively, so the presence of cobalt plus 2 oxidation state in the compound. These are the XPS spectrum of iron in silica supported cobalt ferrite nanocatalyst. And the peak for iron 2p 3 by 2 and iron 2p half with a binding energy of 711.9 electron volt and 725.5 electron volt respectively, having satellite peak at 716.1 electron volt, confirms the presence of iron plus 2 oxidation state in the compound. This is the SAM-ADX spectrum of silica supported cobalt ferrite nanocatalyst, and the same image of the catalyst clearly shows that the particles are of uniform size with spherical morphology. And from the EDX spectrum, it clearly indicates the presence of cobalt, iron, silicon, and oxygen element in the as-prepared catalyst. This is the TEM image of the synthesized catalyst, and the SAD pattern confirms the crystalline nature of silica-supported ferrite nanocatalyst. Next, we have done the BET measurement, and from the BET measurement, it has been observed that when cobalt ferrite is immobilized on the surface of silica, then the specific surface area of the catalyst decreases to 22.108 meters square per gram, which is lower than that of the silica, and this indicates the successful grafting of cobalt ferrite on the surface of silica. This is the VSM, that is magnetic hysteresis loop of silica supported cobalt ferrite nanocatalyst, and to check the magnetic nature of the synthesized catalyst, we have performed the VSM analysis and the nature of the magnetization curve asserting the characteristic pattern of ferromagnetic behavior. And upon removal of driving field, the composite still had a corrosivity value of 110.87 OE and a remanence value of 5.185 EMU per gram. And the saturation magnetization value of the nanocatalyst was found to be 39.7855 EMU per gram. And this behavior certainly supports the presence of ferromagnetic component in the material. And in order to investigate the catalytic activity of the silica-supported cobalt ferrite nanocatalyst, we performed a reaction for the hydration of nitriles, so taking 1 millimeter benzonitrile as the model substrate, isopropyl alcohol as the solvent, 3 milligram of the catalyst, and 1 millimole of the base. First, we have done the optimization of base, and we have examined the reaction with various bases and noticed that mild bases like sodium carbonate, cesium carbonate, and potassium carbonate did not show any satisfactory results, whereas with strong bases like sodium hydroxide and potassium hydroxide, as shown in entry 4 to 9, they show good to excellent yield of products. And however, taking potassium hydroxide as a base, it requires longer reaction time and also high temperature as compared to sodium hydroxide. And similarly, we have also optimized the amount of catalyst, temperature, and solvent. And from our investigations, it reveals that 1 millimole of base, 3 milligram of the catalyst, 5 milliliter of the solvent, that is isopropanol, at 50 degrees centigrade is the best reaction condition for hydration of nitriles to amides, which is shown in entry 7. After optimizing the reaction conditions, next we had explored the scope of the catalyst by using these optimized reaction conditions for hydration of various nitriles, including aromatic, heteroaromatic, and aliphatic nitriles having either electron donating group or electron withdrawing groups. And from our observations, we noticed that heteroaromatic nitriles, as shown in entry 9 and 10, and aliphatic nitriles, as shown in entry 11, this gives moderate isolated yield of the products, while benzonitriles having either electron withdrawing or electron donating groups undergo reaction effectively to produce amides in excellent yields. And to study the reusability of the catalyst, we have performed the reaction of 2-methoxybenzonitrile under optimized reaction conditions. And the catalyst could be isolated from the reaction mixer after completion of the reaction by an external magnet washed with dry ethyl ether and then dried in an oven. And the dried catalyst was then reused for successive experiments up to 5 times. And the product yield indicated that the catalyst can be reused up to 5 consecutive cycles without losing its activity. This is the plausible mechanism for the hydration of nitriles to amides. Now let us see the conclusion of our research work. And the present work reports the synthesis of a magnetically separable heterogeneous cobalt ferrite nanocomposite by co-precipitation method, and the catalyst was found to be highly effective for hydration of nitriles to amides. And the catalyst was found to be crystalline, and it is an efficient low-cost catalyst which could be recycled and reused for at least 5 consecutive runs. And some apparent advantages of the present procedure are the easy catalyst preparation, low metal loading, simple reaction setup, no requirement of specialized equipments, use of green solvents, short reaction time, high product yield, and easy recovery of the catalyst. These are the references, and I thank you all for your kind attention. Thank you.
Thank you for your nice presentation. So next we'll go for a short presentation of Dr. Minal Soikia. Minal Soikia?
Am I?
Oh yes, please go ahead.
Hello. Is it my screen is visible?
He's not clearly, but
just a minute.
you are presenting from mobile phone?
Yes, yes.
Not properly aligned actually.
Okay.
नहीं ऑनलाइन चल रहा है.
Is it visible now?
not properly aligned.
Oh. Just a minute. Is it visible now? Hello?
Yes, now visible but very small. The slide is very small. Zoom it, zoom it.
Okay. Is it visible?
Not yes, now it's okay. It's okay. Okay.
Okay. Thank you very much. Myself, Dr. Minal Soika, Assistant Professor, Department of Chemistry, DKT College, Dergaon. The title of my presentation is Gold Supported Composite Material. This is gold NH2MIL101, an efficient catalyst for one-pot synthesis of propagylamines. So basically the metal organic frameworks are nothing but a high surface area material, and nowadays these MOFs are basically used for gas storage, heterogeneous catalysis, separation, drug delivery, sensing due to its high surface area, porosity and tunable chemical properties. So in my work, I have actually supported gold nanoparticles by taking the advantage of high surface area material, that is amine functionalized MIL101, by a simple solution approach. The resulting material is then characterized by using various analytical tools like powder XRD, XPS, TEM, FESCM, EDS, TGA, etc. The catalytic activity of the synthesized material has been explored for one-pot synthesis of propagylamines via a A3 coupling. This is a three-component condensation reaction between aldehyde amines and alkynes under suitable reaction conditions. Now coming to the synthesis part, I have synthesized this material by taking NH2MIL101 as a support material and then chloroauric acid in presence of trisodium citrate dihydrate as a stabilizing agent and using sodium borohydride as an reducing agent for 6 hours. Now the characterization of gold supported this amine functionalized MIL101. The powder XRD pattern shows the FCC. This is the FCC crystals of gold nanoparticles. The blue one is the unsupported. This is the neat amine functionalized MIL101. The red is the functionalized, means gold supported. If you see, the picture appears in red one, and the black one is the recovered catalyst XRD. The surface area analysis shows that after supported the gold nanoparticles, the surface area is decreases from around 1500, this is the 1500 centimeter square per gram to 1100 centimeter square per gram. The TEM images shows the clear dispersion of the gold nanoparticles on the supports and the very narrow size distribution around 2 to 10 nanometer. The HRTEM images shows the gold 111 plan, and the lattice fringe distance is around 0.23 nanometer, which clearly indicates the FCC crystals of gold nanoparticles synthesized on amine functionalized MIL101. Now the AT coupling reactions. Here I have studied the effect of various catalyst doses, temperatures and solvents to optimize the reaction conditions. 0.5 mole% is the suitable catalyst doses for these catalytic transformations. Then 100 degrees temperature is the optimized temperature, and toluene is the ideal solvent for these catalytic reactions. Now I have checked the versatility of the catalyst by putting various aldehydes incorporating electron donating as well as electron withdrawing as well as aliphatic aldehydes. Then we got a very good yield for all these substrates. Now coming to the proposed mechanism of the AT coupling reactions, the reaction proceeds with the CH activations of the terminal alkynes, which forms a complex with the support molecules, which finally react with the iminium. This is a generation of iminium ion, then form the propagylamines, and finally the cycles goes on. And I have checked the recyclability of the catalyst. My catalyst is recycled up to 5 catalytic cycles. The TEM in the image of the recovered catalyst is also shown a good dispersions after recycle of the gold nanoparticles. Although some sort of aggregation is there in the pictures, but still I got a very good dispersion of the recovered catalyst. So this good dispersion is the main reasons for high catalytic activity of these gold nanoparticles supported on this amine functionalized MIL101. Now in summary, so I have synthesized these gold nanoparticles on the support by using a simple solution approach. The synthesized materials has a good catalytic activity for 1.3 component condensation reaction between aldehydes, amines and alkynes, and the catalyst can be recovered and recycled up to 5 catalytic cycles without significant loss in catalytic activity. With this, I thank you all.
Thank you, Dr. Soikia. Next, I request Dr. Puri Buragohai to present her paper.
Okay, sir. My skin is visible?
Visible, not visible.
Now I think my skin is visible.
No. Now visible.
Okay.
It's visible now, so you can go to the slideshow mode and please go ahead for your presentation.
Okay. A very good evening to all of you. Myself, Dr. Puri Buragohai. I am currently working as an assistant professor at the DKD College. There go. Today, my topic of presentation is synthesis of new artemisinin derivatives having antifungal properties. First of all, I would like to give a very brief introduction about artemisinin molecule. Artemisinin and its derivatives are outstanding antimalarial agent, and it was first isolated from artemisinin NY in 1972. Traditionally, this molecule was used for antimalarial activity, but recently it was found that this molecule shows anti-cancer properties also. And recently we found that artemisinin molecule shows some antifungal properties also. Chemically, if you see the structure, this molecule has a stable endoperoxide linkage, and that linkage is responsible for its outstanding antimalarial activity. So as there is always a potential threat about the drug resistance, people always tries to synthesize new molecule. Keeping in mind, we tried to prepare some new artemisinin derivatives by application of Sonogacera and Suzuki-Cross coupling reaction. So to prepare those compounds, first we prepared some starting material and we first prepared compound 2, which is known as dihydroartemisinin, and we prepared compound 2 dihydroartemisinin from artemisinin by reducing its sodium borohydride. Then we prepared some terminal alkyl of artemisinin, which is shown as a compound 3 and compound 4 here, by using propazyl and homopropazyl alcohols. Then we prepared
compound 5 using that compound 4 taking as a starting material by using sonogastric cross coupling reactions, and compound 5 we again use as a starting material to synthesize new derivatives of artemisinin. We also use compound 3 and 4, and we prepared some new derivatives, compound 8 by using sonogastric cross coupling reactions. And these are the structure of all these compounds. We totally synthesized 9 compounds. All these compounds are fluoroiodine compound, and we tested all these compounds again. Fungal pathogen Fusarium oxysporums. It is an opportunistic fungal pathogen, and we studied their activity. We found that unmodified artemisinin shows 78.5% GOAT inhibitions, and rest of the molecules also show some good activity, and their inhibition rate is up to 72%. We tested all these compounds in different concentration, 5 different concentration. We found that 1000 ppm concentration is good enough for the inhibition purpose. And with this, I conclude my presentation. Thank you all.
Thank you, Dr. Bora Gohai. Next, I request Orindam Vikas Neok to present his paper.
Okay, sir. Sir, are my slides visible?
No, not visible.
Okay.
There is okay, now it is coming.
Okay, sir.
It is visible now.
Okay, sir. So, good evening, everyone. Today, I'm going to present a new topic, which is nanofluidics characteristics of vanadium pentoxide. So, first of all, let me introduce myself. I am Orindam Vikas Neok, currently working as an assistant professor in the Department of Chemistry, DKT College, as well as I am also carrying out my PhD research work under the guidance of Dr. Kalyan Rajongya at Indian Institute of Technology, Guwahati. So, the topic of my presentation is tailor-cut nanofluidic characteristics of vanadium pentoxide and channels. So, before going to the details of the work, I would like to just briefly define what is nanofluidics. So, nanofluidics is nothing but the study of the transport of fluids confined to nanometer scale structures. So, this has been a very recent topic. So, first of all, this topic was published in the journal JACS in 2012, which was followed by certain other publications in very reputed journals. So some of the main fabrication techniques of making nanofluidic devices is using track etching method and electron beam lithography, as well as etching, bonding, nanoparticle crystal, and nanoporous materials. So in this topic, what we have done is that we have used 2D nanochannels using restacked membrane. So this first work was published using restacked membrane in the year 2012 by Huang et al. So, and later it was followed by works in Nature Communication and JACS in the year 2015 and 17 simultaneously. So, first of all, I would like to give a brief description of how this 2D membrane is made. First of all, what we have done is that we have taken just a powder form of vanadium pentoxide, which was treated with an oxidizing agent hydrogen peroxide, and finally we have got this beautiful brown dispersion. And on taking the TEM as well as AFM images, we can see this little nanoseeds in the range of like 200 to 400 nanometer range. So when we have filtered this vacuum dispersion, when we have vacuum filtered it on top of a PTFE membrane, we have seen this beautiful lamellar membrane, which also is characterized using FESM as well as FESM characterization, which we can see this beautiful cross-sectional images as well as its topography on the top side. So we have studied the surface charge governed ionic transport using this membrane, but we have cut a rectangular piece of this membrane, and what we have done is that we have cut out two reservoirs to place about like 0.5 ml of our electrolyte, and we have done this IV curve study using a source meter instrument. For that, we have connected the two ends using this silver electrode. So we have seen that this shows typical nanofluidic behavior. Nanofluidic behavior is nothing but the behavior is that in case of bulk, the conductivity decreases as and when we decrease the concentration of the electrolyte. But in case of this nanofluidic transfer, what happens is that below a certain level of concentration, this conductivity remains same irrespective of the concentration of the electrolyte. This is a typical behavior of nanofluidic devices. So we have found that in this study, the proton conductivity was found to be highest, and this highest reported conductivity, it is highest among the reported membranes till now. So we have thought that this could be due to the contribution from electrical phenomenon, and that is why we have studied the contribution of electrical conductivity to this overall conductivity. And for that, we have made this type of devices and calculated the electrical conductivity from this relative humidity versus conductivity curve, and this lowest point was calculated as the electrical conductivity. Even after subtracting this electrical conductivity from the total conductivity, we have found that this conductivity will be again in the range of 0.01 Siemens centimeter adverse. And with this, we can conclude that this membrane was shows the highest proton conductivity among the 2D reported membranes. So the mechanism of proton transport was then studied using a certain type of lab-made device, and we have calculated this activation energy to be about 0.066 electron volt, which shows that this mechanism of this proton conductivity is followed it follows Grotha's type of mechanism and not the vehicle mechanism. So apart from this, we have studied the ionic current rectification, and for that, in this time, we have cut a triangular shape of this membrane instead of the rectangular shape. We have to, for getting this ionic current rectification, the main thing is that we have to maintain this asymmetry. That is, one side should be a slightly longer than the other side. So in this case, what we have got is that if we now place the similar type of electrodes and record the electrical conductivity, we found that it shows a different kind of behavior. That is, higher current in case of the positive bias and lower current in case of the negative bias, which was completely opposite in case of the rectangular device. Okay, this phenomenon is also observed only in the surface charge governed region, that is in lower conductivity region. Again, if we have taken high concentration of electrolyte on both the sides, that is 1 molar potassium chloride, we see that it shows the similar linear behavior. But as and when the conductivity of electrolyte is maintained at surface charge governed regime, we can see this beautiful ICR type of mechanism. So we have recorded the ICR against KCl electrolyte concentration, and we have seen that after 10 to the minus 3 molar concentration, the ICR ratio was found to be constant. So this mechanism of ICR can be discussed as follows. Like, this device is a rectangular device, and as and when we have disturbed the asymmetry of the device, that is converted this rectangular device to this triangular device, this linear IV curve has converted into a diode-like IV curve. And this can be maintained by this asymmetry ratio, which is the length of the base divided by the length of the tip. So as you can see in this normalized current, the forward bias current has always greater value than that of the reverse bias current. Similarly, as when this 14 value depicts that of the asymmetry. So to prove this phenomenon, we have cut two devices, that is one for the 14 case and one for the 6 case, and we have seen that in the forward bias case, in both devices, we have got higher forward bias than that of the reverse bias, which suggests this that ICR is taking on due to this geometrical asymmetry. Furthermore, this is the mechanism of ICR is that how it happens is that this is the base side, that is the entry is very large as compared to this exit. Exit is the tip side, which is very slow. So as and when we apply a forward bias, the particular counter ions enters from this exit towards this entrance. Okay, then what happens is that in this phenomenon, as and when there is greater space for movement of these ions, so they aggregate in the tip region. So as in due to this, the concentration of the ions at the tip side increases and we get diode-like behavior. But as and when this concentration is in the normal bulk concentration, this type of behavior is not found and we get linear curve. So this is the triangular device, schematic illustration of the triangular device. We can see that when we have maintained this triangular device and we have given the zero mean electrical potential, we can see that we have got an average that is in positive for about 1000 concentration. Above 1000-fold concentration difference, we get this overall linear negative curve. That is, I mean to say that about till 1000-fold concentration difference, we can pump these ions against concentration gradient. That is from even low to high concentration. But only above 1000-fold concentration gradient, only this ions flows from high concentration to low concentration. To prove this, we have also.
Your slide is not moving.
Okay, sir. Is it moving now?
Yes.
Okay. So this is the triangular ion pump. For proving this experiment, we have made this type of devices. We have connected 6 triangular devices, and we have used high concentration on the tip side and low concentration on the base side. We have found that when we have given concentration difference of about 1000-fold, this low concentration side concentration has further decreased and the high concentration side has further increased its concentration, which proves our ionic current rectification behavior. So in conclusion, I would like to say that in this work, we have tried to prepare a freestanding and flexible membrane which shows nanofluidic ionic transport, and this membrane has highest proton conductivity among the reported 2D membranes as well as highest proton mobility, and it exhibits shape-dependent nanofluidic characteristic. That is, it shows ICR current rectification, and also this type of devices has can show triangular nanofluidic device which can pump ion against concentration gradient of about 1000-fold. So at last, before ending my presentation, I'd like to acknowledge my supervisor guide, Dr. Kalyan Radunga sir of IIT Guwahati, my lab mates, Indian Institute of Technology Guwahati, Department of Chemistry IIT Guwahati, Central Instrument Facility IIT Guwahati, as well as I'd like to thank Department of Chemical Sciences, Tezpur University for giving me this platform to present my work, and I'm very thankful to the entire chemistry department. At last, I would like to thank all the participants as well as organizers and for giving me this opportunity as well as for your kind attention. Thank you.
Thank you, Orindam, for your nice presentation. We now go to the next and last presentation of this session, Parthapratim Sharma.
Yes, sir.
Parthapratim Sharma, are you present here?
Yes, sir. Yes, sir.
Okay.
Am I audible? Am I audible, sir?
Yes, now it is coming.
Sir, is my slide visible?
Yes.
Okay. Good evening, everyone. My name is Parthapratim Sharma. Today, in this presentation, I would like to present on development of plant-based nanoemulsion with antioxidant and antimicrobial properties to deliver active compounds in food matrix to act as a natural preservative. Plant bioactive compounds possessing the antimicrobial properties can play an important role to preserve the food against the microbes through a green process. In this concern, nanoemulsion can play a crucial role for the incorporation of the bioactive compounds into food matrices. Our work aimed to deliver the plant-based active compounds with antimicrobial activity in the food matrix to act as a food preservative. Materials and methods. First step is the extraction of fruit juice from apple. Here, 2 different batches of fruit juice were prepared. One batch was prepared with preservative benzoic acid as a control, which was represented as T1, and another batch represented as T2 was formulated using both 200 ppm benzoic acid and nanoemulsion in the ratio of 0.1:10 to reduce the dose of benzoic acid in the fruit juice. Next, formulation of active compound-loaded nanoemulsion. Here, nanoemulsion was prepared by using the extracted from the leaves of Okium tenuiflurum, rhizome of Ginger officinalis, and flower of Syzygium aromaticum. And in non-ionic surfactant, 280 was used as a surfactant. Next, extraction of bioactive compound, the leaves of Okium tenuiflurum, rhizome of Ginger officinalis, and flower of Syzygium aromaticum were dried using oven, and after grinding, the dried powder was mixed in 1:1:1 ratio and dissolved in 5 gram of the extract dissolved in ethanol for 6 hours. After the centrifugation of the superintendent was collected and stored in refrigeration. Results and discussion. During the storage time, comparative physicochemical studies of both the formulation T1 and T2 was carried out, which is directly associated with the quality of processed food. Change in these properties indicate quality compromise. Here, pH, titrable acidity, and total soluble solid were analyzed. Here, pH of the fruit juice is inversely proportional to acid content, and minor increase in pH is because of the hydrolysis of polysaccharide and the formation of monosaccharide and disaccharide. The total titrable acidity decreased significantly during the storage of 30 days, and almost similar changes are obtained in both the cases. A slight increase in total soluble solid during the storage is acceptable for quality improvement. TSS increases may be due to the solubilization or hydrolysis of acid and formation of sugar. Next, nanoemulsion had gone through an observation period of 30 days at room temperature. Here, 8 different types of nanoemulsion were prepared based on various composition of extract, surfactant, and water. And data were collected at a regular interval of 5 days. From the data, we can conclude that low extract concentration with high surfactant concentration is more stable as compared to high extract concentration and low surfactant concentration. The next is antimicrobial activity test. For the antimicrobial activity test, the test of the nanoemulsion agar division method was adopted. Here, 3 microbial species were selected. One is fungus, Candida albicans. Other 2 are one is gram-positive S. aureus, and one is gram-negative E. coli bacteria. The highest inhibition zone was found against C. albicans and then the gram-positive S. aureus. The inhibition zone is directly related to the quantity of the nanoemulsion. Different volume of nanoemulsion were added in the plate, and the antimicrobial activity was studied. Next, characterization of the nanoemulsion. The zeta potential of the analysis was found to be minus 18.6 MB, which indicate that nanoemulsion was very stable. Again, after completion of 30 days of storage, this stable nanoemulsion without phase separation was analyzed, and the droplet size was found to be less than 100 nanometer, which indicate that the synthesized nanoparticle has high stability. At last, we can conclude that the dose of benzoic acid was reduced to 200 ppm, and the nanoemulsion played an important role to preserve the fruit juice. The quality of the fruit juice was maintained during the storage time because of the formulated nanoemulsion contained natural antibacterial and antioxidant compounds, which play a crucial role to preserve the fruit juice. The ratio of nanoemulsion and fruit juice is 0.1:10, which was good enough to preserve the fruit juice due to the presence of active compound in the nanoemulsion. At last, I would like to acknowledge my supervisor, Dr. Pranjal Kumar Bora sir, and the Department of Chemistry, Guwahati University, Institute of Advanced Study in Science and Technology, GYST, Guwahati, for providing sophisticated analytical instruments facility for the analysis of the sample. And last of all, I would like to thank Tezpur University for giving me the opportunity to participate in the presentation. With this, I would like to conclude my speech. Thank you.
Thank you, Partha. With this, we conclude this session. So that actually we have some prizes for the presentation, for online presentation here, ongoing offline presentation and poster presentation. So all will be announced in our conference site. Please visit that. And for outstation participants, we will send the certificate. The soft copy of the certificate can be sent. Okay. If some of you need a hard copy, then please you can contact us. Okay. So thank you to all of you, and with this I conclude this session. Thank you.